of regenerative growth, of regeneration, or growth and repair. The phenomenon of regeneration, or the restoration of lost or amputated parts, is a particular case of growth which deserves separate consideration. It is a property manifested in a high degree among invertebrates and many cold-blooded vertebrates, diminishing as we ascend the scale, until it lessens down in the warm-blooded animals to that vis medicatrix heals a wound. Ever since the days of Aristotle, and still more since the experiments of Tremblay, Réaumur, and Spallanzani in the 18th century, physiologists and psychologists alike have recognized that the phenomenon is both perplexing and important. Its discovery, said Spallanzani, was an immense addition to the riches of organic philosophy, and an inexhaustible source of meditation for the philosopher. The general phenomenon is amply treated of elsewhere. The general phenomenon is amply treated of elsewhere. And we need only deal with it in its immediate relation to growth. Regeneration, like growth in other cases, proceeds with a velocity which varies according to a definite law. The rate varies with the time, and we may study it as velocity and as acceleration. Let us take as an instance, Miss ML, Durbin's measurements of the rate of regeneration of tadpoles' tails, the rate being measured in terms of length or longitudinal increment, from a number of tadpoles whose average length was in one experiment 34 millimeters and in another 49 millimeters. About half the tail was cut off, and the average amounts regenerated in successive periods are shown as follows. The table lists days 3, 5, 7, 10, 12, 14, 17, 24, 28, and 30, with the amount regenerated in millimeters for a first experiment and a second experiment, showing a steady increase over time, with the second experiment generally yielding slightly larger regenerated lengths by the later days. View page 286, the rate of growth. Both experiments give us fairly smooth curves of growth within the period of the observations, and with a slight and easy extrapolation, both curves draw to the baseline at 0, figure 84. Figure 84 for curve of regenerative growth in tadpoles' tails. From M.L. Durbin's data, figure 85. Tadpoles' tails, amount regenerated daily in millimeters, smooth curve. Moreover, if from the smooth curves we deduce the daily increments, we get figure 85, a bell-shaped curve similar to, or to all appearance identical with, a skew curve of error. In point of fact, this instance of regeneration is a very ordinary example of growth, with its Dupich 287 S-shaped curve of integration and its bell-shaped differential curve, just as we have seen it in simple cases of simple phase, of the growth of a population or an individual. If we amputate one limb of a pair in some animal with rapid powers of regeneration, we may compare from time to time the dimensions of the regenerating limb with those of its uninjured fellow, and so deal with a relative rather than an absolute velocity. The legs of insect larvae are easily restored, but after pupation no further growth or regeneration takes place. An easy experiment, then, is to remove a limb in larvae of various ages, and to compare at leisure in the pupa the dimensions of the new limb with the old. Figure 86, regenerative growth in mealworms' legs. The following much abbreviated table shows the gradual increase of a regenerating limb in a mealworm, up to final equality with the normal limb, the rate varying according to the usual S-shaped curve, figure 86. Rate of regeneration in the mealworm, Tenebrio molitor larva. The table compares days after amputation with the percentage ratio of new limb to old, showing a steady rise from 0% soon after amputation to 100% by 100% by 121 days. Some writers have found the curve of regenerative growth to be different from the curve of ordinary growth, and have commented on the apparent difference, but they have been misled, as it seems to me, by the fact that regeneration is seen from the start, or very nearly so, while the ordinary curves of growth, as they are usually presented to us, date not from the beginning of growth, but from the comparatively late and unimportant, and even fallacious epoch of birth. A complete curve of growth starting from 0 has the same essential characteristics as the regeneration curve. Indeed, the more we consider the phenomenon of regeneration, the more plainly does it show itself to us as but a particular case of the general phenomenon of growth, following the same lines, obeying the same laws, and merely started into activity by the special stimulus, direct or indirect, caused by the infliction of a wound. Neither more nor less than in other problems of physiology are we called upon, in the case of regeneration, to indulge in metaphysical speculation, or to dwell upon the beneficent purpose which seemingly underlies this process of healing and repair. It is a very general rule, though not a universal one, that regeneration tends to fall somewhat short of a complete restoration of the lost part. A certain percentage only of the lost tissues is restored. This fact was well known to some of those old investigators who, like the Abbé Tremblay and like Voltaire, found a fascination in the study of artificial injury and the regeneration which followed it. Sir John Graham Dalziel, for instance, says, in the course of an admirable paragraph on regeneration, the reproductive faculty is not confined to one portion, but may extend over many, and it may ensue even in relation to the regenerated portion more than once. Nevertheless, the faculty gradually weakens, so that in general every successive regeneration is smaller and more imperfect than the organization preceding it, and at length it is exhausted. Such as the infusoria, in which the capacity for regeneration is so great that the entire animal may be restored from a mere fragment. It becomes of great interest to discover whether there be some definite size at which the fragment ceases to display this power. This question has been studied by Lilly, who found that in Stentor, while still smaller fragments were capable of surviving for days, the smallest portions capable of regeneration were of a size equal to a sphere of about 80 microns in diameter. That is to say, of a volume equal to about 1/27th of the average entire animal. He arrives at the remarkable conclusion that for this, and for all other species of animals, there is a minimal organization mass, that is to say, a minimal mass of definite size consisting of nucleus and cytoplasm, within which the organization of the species can just find its latent expression. And in like manner, Boveri has shown that the fragment of a sea urchin's egg capable of growing up into a new embryo, and so discharging the complete functions of an entire and uninjured ovum, reaches its limit at about 1/20th of the original egg, other writers having found a limit at about 1/4. These magnitudes, small as they are, represent objects easily visible under a low power of the microscope, and so stand in a very different category to the minimal magnitudes in which life itself can be manifested, and which we have discussed in another chapter. The Bermuda life plant, Bryophyllum calicinum, has so remarkable a power of regeneration that a single leaf kept damp sprouts into fresh leaves and rootlets which only need nourishment to grow into a new plant. If a stem bearing two opposite leaves be split asunder, the two co-equal sister leaves will produce, as we might indeed expect, equal masses of shoots in equal time, whether these shoots be many or few. And if one leaf of the pair have part cut off it and the other be left intact, the amount of new growth, page 290, the rate of growth, will be in direct and precise proportion to the mass of the leaf from which it grew. The leaf is all the while a living tissue, manufacturing material to build its own offshoots. And we have a simple case of the law of mass action in the relation between the mass of the leaf, with its included chlorophyll, and that of its regenerated offshoot. Figure 87 shows the relation between the percentage amount of tail removed, the percentage restored, and the time required for its restoration. The horizontal axis measures time in days from 0 to 9. The vertical axis measures percentage removed from 0 to 80. A family of curves shows that as the percentage restored rises toward about 80%, the time taken depends on how much was removed, with curves labeled 5, 10, 15, 20, 25, 30, 35, Fort Y, and 45% restored. A number of phenomena connected with the linear rate of regeneration are illustrated and epitomized in the accompanying diagram, figure 87, which I have constructed from certain data given by Ellis in a paper on the relation of the amount of tail regenerated to the amount removed in tadpoles. These data are summarized in the next table. The tadpoles were all very much page 291 on the sides, about 40 millimeters. The average length of tail was very near to 26 millimeters, or 65%, of the whole body length, and in 4 series of experiments, about 10, 20, 40, and 60% of the tail were severally removed. The amount regenerated in successive intervals of 3 days is shown in our table. By plotting the actual amounts, regenerated against these 3-day intervals of time, we may interpolate values for the time taken to regenerate definite percentage amounts, 5%, 10%, etc. And my diagram is constructed from the 4 sets of values thus obtained, that is to say, from the 4 sets of experiments, which differed from one another in the amount of tail amputated. To these, we have to add the general result of a 5th series of experiments, which showed that when as much as 75% of the tail was cut off, no regeneration took place at all, but the animal presently died. In our diagram, then, each curve indicates the time taken to regenerate n% of the amount removed. All the curves converge towards infinity of time, when the amount removed approaches 75% of the whole, and all start from 0, for nothing is regenerated where nothing had been destroyed. The rate of regenerative growth in tadpoles' tails. The table summarizes 4 experimental series, giving average body and tail lengths, the amount, and percentage of tail removed, and the percentage regenerated after 3, 6, 9, 12, 15, 18, and 32 days. The amount regenerated varies also with the age of the tadpole and with other factors, such as temperature in short. In short, for any given age or size of tadpole and for various temperatures, and doubtless for other varying physical conditions. A similar diagram might be constructed. The power of reproducing or regenerating a lost limb is par page 292, the rate of growth, particularly well developed in arthropod animals and is sometimes accompanied by remarkable modification of the form of the regenerated limb. A case in point, which has attracted much attention, occurs in connection with the claws of certain crustacea. In many of these, we have an asymmetry of the great claws, one being larger than the other and also more or less different in form. For instance, in the common lobster, one claw, the larger of the two, is provided with a few great crushing teeth, while the smaller claw has more numerous teeth, small and serrated. Though Aristotle thought otherwise, it appears that the crushing claw may be on the right or left side indifferently. Whether it be on one or the other is a matter of chance. It is otherwise in many other crustacea, where the larger and more powerful claw is always left or right, as the case may be according to the species, where, in other words, the probability of the large or the small claw being left or being right is tantamount to certainty. As we have already seen, the one claw is the larger because it has grown the faster. It has a higher coefficient of growth, and accordingly, as age advances, the disproportion between the two claws becomes more and more evident. Moreover, we must assume that the characteristic form of the claw is a function of its magnitude. The knobbiness is a phenomenon coincident with growth, and we never, under any circumstances, find the smaller claw with big crushing teeth and the big claw with little serrate ones. There are many other somewhat similar cases where size and form are manifestly correlated, and we have already seen, to some extent, how the phenomenon of growth is often accompanied by such ratios of velocity as lead inevitably to changes of form. Meanwhile, then, we must simply assume that the essential difference between the two claws is one of magnitude, with which a certain differentiation of form is inseparably associated. As often happens, the crab casts it off. It undergoes a process of regeneration. It grows anew, and does so with an accelerated velocity, which ceases when equilibrium of the parts is once more attained. The accelerated velocity being a case in point to illustrate that vis revulsionis of Haller, to which we have already referred. With the help of this principle, Pshibram accounts for certain curious phenomena which accompany the process of regeneration. As his experiments and those of Morgan show, if the large or knobby claw be removed, there are certain cases, for example, the common lobster, where it is directly regenerated. In other cases, for example, Alpheus, the other claw B assumes the size and form of that which was amputated, while the latter regenerates itself in the form of the lesser and weaker one. A and B have apparently changed places. In a third case, as in the hermit crabs, the A claw regenerates itself as a small or B claw, but the B claw remains for a time unaltered, though slowly, and in the course of repeated molts, it later on assumes the large and heavily toothed A form. Much has been written on this phenomenon, but in essence, it is very simple. It depends upon the respective rates of growth, upon a ratio between the rate of regeneration and the rate of growth of the uninjured limb, that is to say, on the familiar phenomenon of unequal growth, or, as it has been called, heterogeny. It is complicated a little, however, by the possibility of the uninjured limb growing all the faster for a time after the animal has been relieved of the other. From the time of amputation, say of A, it begins to grow from zero with a high regenerative velocity, while B, starting from a definite magnitude, continues to increase or perhaps somewhat accelerated velocity. The ratio between the two velocities of growth will determine whether, by a given time, A has equaled, outstripped, or still fallen short of the magnitude of B. That this is the gist of the whole problem is confirmed, if confirmation be necessary, by certain experiments of Wilson's. It is IPH 294, the rate of growth. It is known that by section of the nerve to a crab's claw, its growth is retarded, and as the general growth of the animal proceeds, the claw comes to appear stunted or dwarfed. Now, in such a case as that of Alpheus, we have seen that the rate of regenerative growth in an amputated large claw fails to let it reach or overtake the magnitude of the growing little claw, which latter, in short, now appears as the big one. But if at the same time as we amputate the big claw, we also sever the nerve to the lesser one, we so far slow down the latter's growth that the other is able to make up to it. And in this case, the two claws continue to grow at approximately equal rates, or in other words, continue of co-equal size. The phenomenon of regeneration goes some little way towards helping us to comprehend the phenomenon of multiplication by fission, as it is exemplified in its simpler cases in many worms and worm-like animals. For physical reasons which we shall have to study in another chapter, there is a natural tendency for any tube, if it have the properties of a fluid or semi-fluid substance, to break up into segments after it comes to a certain length. And nothing can prevent its doing so except the presence of some controlling force, such for instance as may be due to the pressure of some external support, or some superficial thickening or other intrinsic rigidity of its own substance. If we add to this natural tendency towards fission of a cylindrical or tubular worm, the ordinary phenomenon of regeneration, we have all that is essentially implied in reproduction by fission. And insofar as the process rests upon a physical principle, natural tendency, we may account for its occurrence in a great variety of animals, zoologically dissimilar, and for its presence here and absence there in forms which are materially different in a physical sense, though zoologically speaking, they are very closely allied. But the phenomena of regeneration, like all the other phenomena of growth, soon carry us far afield, and we must draw this long discussion to a close. Page 295, the rate of growth. Summary and conclusion. For the main features which appear to be common to all curves of growth, we may hope to have someday a simple explanation. In particular, we should like to know the plain meaning of that point of inflection, or abrupt change from an increasing to a decreasing velocity of growth, which all our curves, and especially our acceleration curves, demonstrate the existence of, provided only that they include the initial stages of the whole phenomenon. Just as we should also like to have a full physical or physiological explanation of the gradually diminishing velocity of growth which follows, and which, though subject to temporary interruption or abeyance, is on the whole characteristic of growth in all cases whatsoever. In short, the characteristic form of the curve of growth in length or any other linear dimension is a phenomenon which we are at present little able to explain, but which presents us with a definite and attractive problem for future solution. It would look as though the abrupt change in velocity must be due, either to a change in that pressure outwards from within by which the forces of growth make themselves manifest, or to a change in the resistances against which they act. That is to say, the tension of the surface, and this latter force we do not by any means limit to surface tension proper, but may extend to the development of a more or less resistant membrane or skin, or even to the resistance of fibers or other histological elements binding the boundary layers to the parts within. I take it that the sudden arrest of velocity is much more likely to be due to a sudden increase of resistance than to a sudden diminution of internal energies. In other words, I suspect that it is coincident with some notable event of histological differentiation, such as the rapid formation of a comparatively firm skin, and that the dwindling of velocities or the negative acceleration which follows is the resultant or composite effect of waning forces of growth on the one hand and increasing superficial resistance on the other, page 296, 282, the rate of growth change on the other. This is as much as to say that growth, while its own energy tends to increase, leads also after a while to the establishment of resistances, which check its own further increase. Our knowledge of the whole complex phenomenon of growth is so scanty that it may seem rash to advance even this tentative suggestion. But yet there are one or two known facts which seem to bear upon the question, and to indicate at least the manner in which a varying resistance to expansion may affect the velocity of growth. For instance, it has been shown by Frazane that electrical stimulation of tadpoles, with small current density and low voltage, increases the rate of regenerative growth. As just such an electrification would tend to lower the surface tension and accordingly decrease the external resistance, the experiment would seem to support in some slight degree the suggestion which I have made. To another important aspect of regeneration, we can do no more than allude. The planarian worms rival Hydra itself in their powers of regeneration, and in both cases even small bits of the animal are likely to include endoderm cells capable of intracellular digestion, whereby the fragment is enabled to live and to grow. Now, if a planarian worm be cut in separate pieces and these be suffered to grow and regenerate, they do so in a definite and orderly way. That part of a sheet or fragment which had been nearer TQ, the original head, will develop a head, and a tail will be regenerated at the opposite end of the same fragment, the end which had been tailward in the beginning. The amputated fragments possess sides and ends, a front end and a hind end, like the entire worm. In short, they retain their polarity. This remarkable discovery is due to Child, who has amplified and extended it in various instructive ways. The existence of two poles, positive and negative, implies a gradient between them. It means that one part leads and another follows, that one part is dominant or prepotent over the rest, whether in regenerative growth or embryonic development. We may summarize as follows. The main results of the foregoing discussion: 1. Except in certain minute organisms, whose form H-Key-That-Jern, Esperzulzeven, P47, 1909. Page 297, Illo summary and conclusion, 283 of A Drop of Water, is due to the direct action of the molecular forces. We may look upon the form of an organism as a function of growth, or a direct consequence of growth whose rate varies in its different directions. In a newer language, we might call the form of an organism an event in space-time and not merely a configuration in space. 2. Growth varies in rate in an orderly way or is subject, like other physiological activities, all to definite laws. The rates differ in degree, or form gradients, from one point of an organism to another. The rates in different parts and in different directions tend to maintain more or less constant ratios to one another in each organism. And to the regularity and constancy of these relative rates of growth is due the fact that the form of the organism is in general regular and constant. 3. Nevertheless, the ratio of velocities in different directions is not absolutely constant, but tends to alter in course of time or to fluctuate in an orderly way. And to these progressive changes are due the changes of form which accompany development and the slower changes which continue perceptibly in after HFE. 4. Rate of growth depends on the age of the organism. It has a maximum somewhat early in HFE, after which epoch of maximum it slowly declines. 5. Rate of growth is directly affected by temperature and by other physical conditions, the influence of temperature being notably large in the case of cold-blooded or post-halothermic animals. Growth tends in these latter to be asymptotic, becoming slower but never ending with old age. 6. It is markedly affected in the way of acceleration or retardation at certain physiological epochs of HFE, such as birth, puberty, or metamorphosis. 7. Under certain circumstances, growth may be negative, the organism growing smaller, and such negative growth is a common accompaniment of metamorphosis and a frequent concomitant of old age. 8. The phenomenon of regeneration is associated with a large transitory increase in the rate of growth or acceleration of growth in the region of HFE. In other respects, regenerative growth is similar to ordinary growth in all its essential phenomena. GPH 284. The rate of growth cheat. In this discussion of growth, we have left out of account a vast number of processes or phenomena in the physiological mechanism of the body by which growth is effected and controlled. We have dealt with growth in its relation to magnitude, and to that relativity of magnitudes which constitutes form. And so we have studied it as a phenomenon which stands at the beginning of a morphological, rather than at the end of a physiological inquiry. Under these restrictions, we have treated it as far as possible, or in such fashion as our present knowledge permits, on strictly physical lines. That is to say, we rule heredity or any such concept out of our present account. However true, however important, however indispensable in another setting of the story, such a concept may be. In physics, on admet que l'état actuel du monde ne dépend que du passé plus proche, sans être influencé, pour ainsi dire, par le souvenir d'un passé lointain. This is the concept to which the differential equation gives expression. It is the step which Newton took when he left Kepler behind. In all its aspects, and not least in its relation to form, the growth of organisms has many analogies, some close, some more remote, among inanimate things. As the waves grow when the winds strive with the other forces which govern the movements of the surface of the sea, as the heap grows when we pour corn out of a sack, as the crystal grows when from the surrounding solution the proper molecules fall into their appropriate places. So in all these cases, very much as in the organism itself, is growth accompanied by change of form and by a development of definite shapes and contours. And in these cases, as in all other mechanical phenomena, we are led to equate our various magnitudes with time, and so to recognize that growth is essentially a question of rate or of velocity. The differences of form and changes of form, which are brought about by varying rates or laws of growth, are essentially the same phenomenon whether they be episodes in the life history of the individual, or manifest themselves as the distinctive characteristics of what we call separate species of the race.
From one form, or one ratio of magnitude, to another, there is but one straight and direct road of transformation. Be the journey taken fast or EGFH Poincaré, La physique générale et la physique mathématique, Reverend G.D. des Sciences, GPI. 167, 1900, LPH 299, Illo summary and conclusion, 285 slow. And if the transformation take place at all, it will in all likelihood proceed in the self-same way. Whether it occur within the UEFA time of an individual or during the long ancestral history of a race. That the individual organism tends to pass through the phases characteristic of ancestors, or the individual tends to recapitulate the ancestral history of its race, lies wrapped up in this simple account of the relation between growth and form. But enough of this discussion. Let us leave for a while the subject of the growth of the organism and attempt to study the conformation within and without of the individual cell. In the early days of the cell theory, 100 years ago, Goodseer was wont to speak of cells as centers of growth or centers of nutrition, and to consider them as essentially centers of force, when that is to say, minute anatomy should be studied in its dynamical aspect. When this branch of inquiry, he says, shall have been opened up, we shall expect to have a science of organic forces, having direct relation to anatomy, the science of organic forms. And likewise, long afterwards, Giard contemplated a science of morphodynamique, but still looked upon it as forming so guarded and hidden a territoire scientifique, que la plupart des naturalistes de nos jours ne le verront que comme Moïse vit la terre promise, seulement de loin et sans pouvoir y entrer, to the external forms of cells, and to the forces which produce and modify these forms. We shall pay attention in a later chapter. But there are forms and configurations of matter within the cell, which also deserve to be studied with due regard to the forces, known or unknown, of whose resultant they are the visible expression. Page. In the long interval since Goodsire's day, the visible structure, the conformation, and configuration of the cell has been studied far more abundantly than the purely dynamic problems which are associated therewith. The overwhelming progress of microscopic observation has multiplied our knowledge of cellular and intracellular structure. And to the multitude of visible structures, it has been often easier to attribute virtues than to ascribe intelligible functions or modes of action. But here and there, nevertheless, throughout the whole literature of the subject,
we find recognition of the inevitable fact that dynamical problems lie behind the morphological problems of the cell. Bütschli pointed out 60 years ago, with emphatic clearness, the failure of morphological methods and the need for physical methods if we were to penetrate deeper into the essential nature of the cell. And such men as Loeb and Whitman, Driesch and Roux, and not a few besides, have pursued the same train of thought and similar methods of inquiry. Whitman, for instance, puts the case in a nutshell when, in speaking of the so-called karyokinetic phenomena of nuclear division, he reminds us that the leading idea in the term karyokinesis is motion viewed as an exponent of forces residing in or acting upon the nucleus.
It regards the nucleus as a seat of energy which displays itself in phenomena of motion. In short, it would seem evident that, except in relation to a dynamical investigation,
the mere study of cell structure has but UPH 302 on the internal form, little value of its own. A given cell, an ovum for instance, contains this or that visible substance or structure, germinal vesicle or germinal spot, chromatin or achromatin, chromosomes or centrosomes, obviously gives no explanation of the activities of the cell. And in all such hypotheses as that of pangenesis, in all the theories which attribute specific properties to micellae, chromosomes, idioplasts, IDs, or other constituent particles of protoplasm or of the cell, we are apt to fall into the error of attributing to matter what is due to energy and is manifested in force, or more strictly speaking, attributing to material particles individually what is due to the energy of their collocation. The tendency is a very natural one, as knowledge of structure increases, to ascribe particular virtues to the material structures themselves, and the error is one into which the disciple is likely to fall, but of which we need not suspect the mastermind.
the dynamical aspect of the case was in all probability kept well in view by those who, like Goodzier himself, first attacked the problem of the cell and originated our conceptions of its nature and functions. If we speak, as Weismann and others speak, of an hereditary substance, a substance which is split off from the parent body and which hands on to the new generation the characteristics of the old, we can only justify our mode of speech by the assumption that that particular portion of matter is the essential vehicle of a particular charge or distribution of energy in which is involved, capable of producing motion or of doing work. For, as Newton said, to tell us that a thing is endowed with an occult specific quality by which it acts and produces manifest effects is to tell us nothing. But to derive 2 or 3 general principles of motion from Voipy, page 303, and it would be a very great step in philosophy. Though the causes of those principles were not yet discovered, the things which we see in the cell are less important than the actions which we recognize in the cell, and these latter we must especially scrutinize, in the hope of discovering how far they may be attributed to the simple and well-known physical forces, and how far they be relevant or irrelevant to the phenomena which we associate with, and deem essential to the manifestation of life. It may be that in this way we shall in time draw nigh to the recognition of a specific and ultimate residuum, and lacking, as we still do lack, direct knowledge of the actual forces in the cell, we may yet learn something of their distribution, if not also of their nature, from the outward and inward configuration of the cell, and from the changes taking place in this configuration. That is to say, from the movements of matter, the kinetic phenomena which the forces in action set up. The fact that the germ cell develops into a very complex structure is no absolute proof that the cell itself is structurally a very complicated mechanism, nor yet does it prove, though this is somewhat less obvious, that the forces at work or latent within it are especially numerous and complex. If we blow into a bowl of soapsuds and raise a great mass of many-hued and variously shaped bubbles, if we explode a rocket and watch the regular and beautiful configuration of its falling streamers, if we consider the wonders of a limestone cavern which a filtering stream has filled with stalactites, we soon perceive that in all these cases we have begun with an initial system of very slight complexity, whose structure in no way foreshadowed the result, and whose comparatively simple intrinsic forces only play their part by complex interaction with the equally simple forces of the surrounding medium. In an earlier age, men sought for the visible embryo, even for the homunculus, within the reproductive cells, and to this day we scrutinize these cells for visible structure,
unable to free ourselves from that old doctrine of preformation. Moreover, the microscope seemed to substantiate the idea, which, page 304 of the internal form, we may trace back to Leibniz and to Hobbes, that there is no limit to the mechanical complexity which we may postulate in an organism, and no limit, therefore, to the hypotheses which we may rest thereon. But no microscopical examination of a stick of sealing wax, no study of the material of which it is composed, can enlighten us as to its electrical manifestations or properties. Matter of itself has no power to do, to make, or to become. It is in energy that all these potentialities reside, energy invisibly associated with the material system, and in interaction with the energies of the surrounding universe. Oh! That function presupposes structure has been declared an accepted axiom of biology. Who it was that so formulated the aphorism, I do not know. But as regards the structure of the cell, it harks back to Brooke, with whose demand for a mechanism or an organization within the cell histologists have ever since been trying to comply. But unless we mean to include thereby invisible and merely chemical or molecular structure, we come at once on dangerous ground. For we have seen in a former chapter that organisms are known of magnitudes so nearly approaching the molecular, that everything which the morphologist is accustomed to conceive as structure has become physically impossible, and recent research tends to reduce rather than to extend our conceptions of the visible structure necessarily inherent in living protoplasm. The microscopic structure, which in the last resort page 305 of the 4V and structure of the cell 291, or in the simplest cases it seems to show, is that of a more or less viscous colloid, or rather, mixtomy of colloids, and nothing more. Now, as Clerk Maxwell puts it in discussing this very problem, one material system can differ from another only in the configuration and motion which it has at a given instant. If we cannot assume differences in structure or configuration, we must assume differences in motion, that is to say, in energy. And if we cannot do this, then indeed we are thrown back upon modes of reasoning unauthorized in physical science, and shall find ourselves constrained to assume or to admit that the properties of a germ are not those of a purely material system. But we are by no means necessarily in this dilemma. For though we come perilously near to it when we contemplate the lowest orders of magnitude to which Fe has been attributed, yet in the case of the ordinary cell, or ordinary egg or germ, which is going to develop into a complex organ, if we have no reason to assume or to behave that it comprises an intricate mechanism, we MGI be quite sure, both on direct and indirect evidence, that HK the powder in our rocket, it is very heterogeneous in its structure. It is a mixture of substances of various kinds, more or less fluid, more or less mobile, influenced in various ways by chemical, electrical, osmotic, and other forces, and in their admixture separated by a multitude of surfaces or boundaries, at which these or certain of these forces are made manifest. Indeed, such an arrangement as this is already enough to constitute a mechanism. For we must be very careful not to let our physical or physiological concept of mechanism be narrowed to an interpretation of the term derived from the confiscated contrivances of high man skill. From the physical point of view, we understand by a mechanism W whatsoever checks or controls and guides into determinate paths the workings of energy. At a stage short of that ultimate degradation which lapses in uniformly diffused heat, this, as Warburg has well explained, is the general effect or function of the physiological machine, and in particular of that part of it which we call cell G, precisely as in the luration concursus, modus, or datura, figura, whereby bodies mutato, ordin mutant natura. The normal muscle cell is something which turns energy, derived from oxidation, into work. It is a mechanism which arrests and utilizes the chemical energy of oxidation in its downward course. But the same cell, when injured or disintegrated, loses its usefulness and sets free a greatly increased proportion of its energy in the form of heat. It was a saying of Faraday's that even a life is but a chemical act prolonged. If death occur, the more rapidly oxygen and the affinities run on to their final state. Very great and wonderful things are done by means of a mechanism, whether natural or artificial, of extreme simplicity. A pool of water, by virtue of its surface, is an admirable mechanism for the making of waves. With a lump of ice in it, it becomes an efficient and self-contained mechanism for the making of currents. Music itself is made of simple things: a reed, a pipe, a string.
The great cosmic mechanisms are stupendous in their simplicity. And, in point of fact, every great or little aggregate of heterogeneous matter, not identical in phase, involves, ipso facto, the essentials of a mechanism.
Even a non-living colloid, from its intrinsic heterogeneity, is in this sense a mechanism, and one in which energy is manifested in the movement and ceaseless rearrangement of the constituent particles. For this reason, Graham speaks somewhere or other of the colloid state as the dynamic state of matter. In the same philosopher's phrase, it possesses inertia. Let us turn then to consider briefly and diagrammatically the structure of the cell. A fertilized germ cell, or ovum for instance, not in any vain attempt to correlate this structure with the structure or properties of the resulting and yet distant organism, but merely to see how far, by the study of its form and its changing internal configuration, we may throw light on certain forces which are for the time being at work within it. We may say at once that we can scarcely hope to learn more of these forces in the first instance than a few facts regarding their EPH 307 and structure of the cell. Direction and magnitude. The nature and specific identity of the force or forces is a very different matter. This latter problem is likely to be difficult of elucidation, for the reason, among others, that very different forces are often much alike in their outward and visible manifestation. So it has come to pass that we have a multitude of discordant hypotheses as to the nature of the forces acting within the cell, and producing in cell division the karyokinetic figures of which we are about to speak. One student may, like Rumbler, choose to account for them by an hypothesis of mechanical traction acting on a reticular web of protoplasm. Another, like Leduc, may show us how, in many of their most striking features, they may be admirably simulated by salts diffusing in a colloid medium. Others, like Lamb and Graham Cannon, have compared them to the streamlines produced and the field of force set up by bodies vibrating in a fluid. Others, like Gallardo and Rumbler, in his earlier papers, insisted on their resemblance to certain phenomena of electricity and magnetism, while Hartog believed that the force in question is only analogous to these and has a specific identity of its own. All these conflicting views are of secondary importance, so long as we seek only to account for certain configurations which reveal the direction, rather than the nature of a force. One and the same system of lines of force may appear in a field of magnetic or of electrical energy, of the osmotic energy of diffusion, of the gravitational energy of a flowing stream. In short, we may expect to learn something of the pure or abstract dynamics long before we can deal with the special physics of the EPH 308 cell. For indeed, just as uniform expansion about a single center, to whatsoever physical cause it may be due will lead to the configuration of a sphere, so will any two centers or foci of potential of whatsoever kind lead to the configurations with which Faraday first made us familiar under the name of lines of force. And this is as much as to say that the phenomenon, though physical in the concrete, is in the abstract purely mathematical, and in its very essence is neither more nor less than a property of three-dimensional space. But as a matter of fact, in this instance, that is to say, in trying to explain the leading phenomena of the karyokinetic division of the cell, we shall soon perceive that any explanation which is based, like Rumbler's, on mere mechanical traction, is obviously inadequate, and we shall find ourselves limited to the hypothesis of some polarized and polarizing force, such as we deal with. For instance, in magnetism or electricity, or in certain less familiar phenomena of hydrodynamics, let us speak first of the cell itself, as it appears in a state of rest, and let us proceed afterward to study the more active phenomena which accompany its division. Our typical cell is a spherical body. That is to say, the uniform surface tension at its boundary is balanced by the outward resistance of uniform forces within. But at times, the surface tension may be a fluctuating quantity, as when it produces the rhythmical contractions or Ransom's waves on the surface of a trout's egg. Or again, the surface tension may be locally unequal and variable, giving rise to an amoeboid figure, as in the egg of Hydra. Within the cell is a nucleus or germinal vesicle, also spherical TP's 309, and consisting of portions of each chromatin, aggregated together within a more fluid drop. The fact has often been commented upon that, in cells generally, there is no correlation of form,
though there apparently is of size, between the nucleus and the cytoplasm, or main body of the cell. So Whitman remarks that, except during the process of division, the nucleus seldom departs from its typical spherical form. It divides and subdivides, ever returning to the same round or oval form. How different with the cell? It preserves the spherical form as rarely as the nucleus departs from it. Variation in form marks the beginning and the end of every important chapter in its history. On simple dynamical grounds, the contrast is easily explained. So long as the fluid substance of the nucleus is qualitatively different from and incapable of mixing with the fluid or semi-fluid protoplasm surrounding it, we shall expect it to be, as it almost always is, of spherical form. For on the one hand, it has a surface of its own whose surface tension is presumably uniform. And on the other, it is immersed in a medium which transmits on all sides a uniform fluid or hydrostatic pressure. Thus, the case of the spherical nucleus is closely akin to that of the spherical yolk within the bird's egg. Again, for a similar reason, the contractile vacuole of a protozoon is spherical. It is just a drop of fluid, bounded by a pH 310 uniform surface tension, and through whose boundary film diffusion is taking place. But here, owing to the small difference between the fluid constituting and that surrounding the drop, the surface tension, equilibrium, is somewhat unstable. It is apt to vanish, and the rounded outline of the drop disappears like a burst bubble in a moment. If, on the other hand, the substance of the cell acquire a greater solidity, as for instance in a muscle cell, or by reason of mucus accumulations in an epithelium cell, then the laws of fluid pressure no longer apply. The pressure on the nucleus tends to become unsymmetrical, and its shape is modified accordingly. Amoeboid movements may be set up in the nucleus by anything which disturbs the symmetry of its own surface tension, and where nuclear material is scattered in small portions throughout the cell, as in many rhizopods. Instead of being aggregated in a single nucleus, the simple explanation probably is that the phase difference, as the chemists say, between the nuclear and the protoplasmic substance is comparatively slight, and the surface tension which tends to keep them separate is correspondingly small. Apart from that invisible or ultramicroscopic heterogeneity which is inseparable from our notion of a colloid, there is a visible heterogeneity of structure within both the nucleus and the outer protoplasm. The former contains, for it, a rounded nucleolus or germinal spot, certain conspicuous granules or strands of the peculiar substance called chromatin, and a coarse meshwork of a protoplasmic material known as lion or chromatin. The outer protoplasm or cytoplasm is generally believed to consist throughout of a spongework or rather alveolar meshwork of more and less fluid substances. It may contain mitochondria appearing in tissue cultures as small amoeboid bodies. And lastly, there are generally to be detected in the animal, rarely in the vegetable kingdom, one or more very minute bodies, usually in the cytoplasm, sometimes within the nucleus, known as the centrosome. PM the 311, the Fordu in structure of the cell, 297. The morphologist is accustomed to speak of a polarity of the cell, meaning thereby a symmetry of visible structure about a particular axis. For instance, whenever we can recognize in a cell both a nucleus and a centrosome, we may consider a knee drawn through the two as the morphological axis of polarity. An epithelium cell is morphologically symmetrical about a median axis passing from its free surface to its attached base. Again, by an extension of the term polarity, as is customary in dynamics, we may have a radial polarity between center and periphery. And lastly, we may have several apparently independent centers of polarity within the single cell. Only in cells of quite irregular or amoeboid form do we fail to recognize a definite and symmetrical polarity. The morphological polarity is accompanied by and is but the outward expression, or part of it, of a true dynamical polarity, or distribution of forces, and the hues of force are, or may be, rendered visible by concatenation of particles of matter, such as come under the influence of the forces in action. When none is of force stream inwards from the periphery towards a point in the interior of the cell, particles susceptible of attraction either crowd towards the surface of the cell, or, when retarded by friction, are seen forming lines or fibrili, which radiate outwards from the center. In the cells of columnar or C-hated epithelium, where the sides of the cell are symmetrically disposed to their neighbors, but the free and attached surfaces are very diverse from one another in their external relations. It is these latter surfaces which constitute the opposite poles.
And in accordance with the parallel lines of force so set up, we very frequently see parallel lines of granules which have ranged themselves perpendicularly to the free surface of the cell. CFF Fig 149. A simple manifestation of polarity may be well illustrated by the phenomenon of diffusion, where we may conceive and may automatically reproduce a field of force with its poles and its visible lines of equipotential, very much as in Faraday's conception of the field of force of a magnetic system. Thus, in one of Leduc's experiments, if we spread a layer of salt solution over a level plate of glass and let fall into the middle of it a drop of Indian ink or of blood, we shall find the colored particles traveling. Théorie physico-chimique de la vie, 1910, p. 73, page 312, 298. On the internal form H, outwards from the central pole of concentration along the lines of diffusive force, and so mapping out for us a monopolar field of diffusion, and if we set two such drops side by side, their lines of diffusion will oppose and repel one another. Or instead of the uniform layer of salt solution, we may place at a little distance from one another a grain of salt and a drop of blood, representing two opposite poles, and so obtain a picture of a bipolar field of diffusion. In either case, we obtain results closely analogous to the morphological but really dynamical polarity of the organic cell. But in all probability, the dynamical polarity or asymmetry of the cell is a very complicated phenomenon, for the obvious reason that in any system, one asymmetry will tend to beget another. A chemical asymmetry will induce an inequality of surface tension, which will lead directly to a modification of form. The chemical asymmetry may in turn be due to a process of electrolysis in a polarized electrical field. And again, the chemical heterogeneity may be intensified into a chemical polarity by the tendency of certain substances to seek a locus of greater or less surface energy. We need not attempt to grapple with a subject so complicated and leading to so many problems which lie beyond the sphere of interest of the morphologist. But yet the morphologist, in his study of the cell, cannot quite evade these important issues, and we shall return to them again when we have dealt somewhat with the form of the cell, and have taken account of some of its simpler phenomena. We are now ready, and in some measure prepared, to study the numerous and complex phenomena which accompany the division of the cell, for instance of the fertilized egg. But it is no easy task to epitomize the facts of the case, and none the easier that of late new methods have shown us new things, and have cast doubt on not a little that we have been accustomed to believe. Division of the cell is of necessity accompanied or preceded by a change from a radial or monopolar to a definitely bipolar symmetry. In the hitherto quiescent or apparently quiescent cell, we perceive certain movements, which correspond precisely to what must accompany and result from a polarization of forces within, of forces which, whatever be their specific nature, are at least end page 313 capable of polarization, and of producing consequent attraction or repulsion between charged particles. The opposing forces which are distributed in equilibrium throughout the cell become focused in two centrosomes, which may or may not be already visible. It generally happens that, in the egg, one of these centrosomes is near to, and the other far from the animal pole, which is both visibly and chemically different from the other, and is where the more conspicuous developmental changes will presently begin. Between the two centrosomes, in stained preparations, a spindle-shaped figure appears, figure 88, whose striking resemblance to the lines of force, made visible by iron filings between the poles of a magnet, was at once recognized by Hermann Fohl in 1873, when he witnessed the phenomenon for the first time. On the farther side of the centrosomes are seen star-like figures, or asters, in which we seem to recognize the broken lines of force which run externally to those stronger lines which lie nearer to the axis, and constitute the spindle. The lines of force are rendered visible or materialized, just as in the experiment of the iron filings, by the fact that in the heterogeneous substance of the cell, certain portions, figure 88, karyokinetic figure in a dividing cell or blastomere of a trout's egg. After print from a preparation by Professor Bouin on page 314 on the internal form,
of matter are more permeable to the acting force than others become themselves polarized after the fashion of a magnetic or paramagnetic body, arrange themselves in an orderly way between the two poles of the field of force, seem to cling to one another as it were in threads, and are only prevented by the friction of the surrounding medium from approaching and congregating around the adjacent poles. As the field of force strengthens, the more will the lines of force be drawn in towards the interpolar axis, and the less evident will be those remoter lines which constitute the terminal or extrapolar asters. A clear space, free from materialized lines of force, may thus tend to be set up on either side of the spindle, the so-called Büchli space of the histologists. On the other hand, the lines of force constituting the spindle will be less concentrated if they find a path of less resistance at the periphery of the cell. As happens in our experiment of the iron filings when we encircle the field of force with an iron ring. On this principle, the difference is observed between cells in which the spindle is well developed and the asters small, and others in which the spindle is weak and the asters greatly developed might easily be explained by variations in the potential of the field, the large. Conspicuous asters being correlated in turn with a marked permeability of the surface of the cell. The visible field of force, though often called the nuclear spindle, is formed outside of, but usually near to, the nucleus. Page 315. Let us look a little more closely into the structure of this body and into the changes which it presently undergoes. Within its spherical outline, figure 89A, it contains an alveolar meshwork, often described from its appearance and optical section as a reticulum consisting of more solid substances with more fluid matter filling up the interalveolar spaces. This phenomenon, familiar to the colloid chemist, is what he calls a two-phase system, one substance or phase forming a continuum through which the other is dispersed. It is closely allied to what we call in ordinary language a froth or a foam. Save that in these latter, the dispersed phase is represented by air. It is a surface tension phenomenon due to the interaction of two intermixed fluids not very different in density as they strive to separate. Of precisely the same kind, as Büchli was the first to show, are the minute alveolar networks which are to be discerned in the cytoplasm of the cell, figure 89bi, page 316, and which we now know to be not inherent in the nature of protoplasm, nor of living matter in general, but to be due to various causes natural as well as artificial. The microscopic honeycomb structure of cast metal under various conditions of cooling is an example of similar surface tensio phenomena. Such then, in briefest outline, is the typical structure commonly ascribed to a cell when its latent energies are about to manifest themselves in the phenomenon of cell division. The account is based on observation not of the living cell, but of the dead, on the assumption, that is to say, that fixed and stained material gives a true picture of reality. But in Robert Chambers' method of microdissection, the living cell is manipulated with fine glass needles under a high magnification and shews us many interesting things. Chambers assures us that the spindle fibers never make their appearance as visible structures until coagulation has set in, and that astral rays are, or appear to be, channels in which the more fluid content of the cell flows towards the centrosome. Within the bounds to which we are at present keeping, these things are of no great moment. For whether the spindle appear early or late, it still bears witness to the fact that matter has arranged itself along bipolar lines of force. And even if the astral rays be only streams or currents, on lines of force they still approximately lie. Yet the change from the old story to the new is important and may make a world of difference when we attempt to define the forces consistent. All our descriptions, all our interpretations are bound to be influenced by our conception of the mechanism before us. And he in page 317 and structure of the cell. Who sees threads where another sees channels is likely to tell a different story about neighboring and associated things. It has also been suggested that the spindle is somehow due to a rearrangement of protein macromolecules or micelles. That such changes of orientation of large colloid particles may be a widespread phenomenon, and that coagulation itself is but a polymerization of larger and larger macromolecules. But here we have touched the brink of a subject so important that we must not pass it by, without a word, and yet so contentious that we must not enter into its details. The question involved is simply whether the great mass of recorded observations and accepted beliefs with regard to the visible structure of protoplasm and of the cell constitute a fair picture of the actual living cell, or be based on appearances which are incident to death itself and to the artificial treatment which the microscopist is accustomed to apply. The great bulk of histological work is done by methods which involve the sudden killing of the cell or organism by strong reagents. The assumption being that death is so rapid that the visible phenomena exhibited during life are retained or fixed in our preparations. Hermann Fuhl struck a warning note full 60 years ago. Il importe à l'avenir de l'histologie de combattre la tendance à tirer des conclusions des images obtenues par des moyens artificiels et à leur donner une valeur intrinsèque sans que ces images aient été contrôlées. Fuhl was thinking especially of cell membranes and the delimitation of cells. But still more difficult and precarious is the interpretation of the minute internal networks, granules, etc., which represent the alleged structure of protoplasm. A colloid body or colloid solution is ipso facto heterogeneous. It has after some fashion a structure of its own. And this structure chemical action under the microscope may demonstrate or emphasize or alter and disguise. As Hardy put it, it is notorious that the various fixing reagents are coagulants of organic colloids, and that the figure varies according to the reagent used. A case in point is that of the vitreous humor, to which some histologists have ascribed a fairly complex structure, seeing in it a framework of fibers with the meshes filled with fluid. But it is really a true gel without any structure in the usual sense of the word. The fibers, seen in ordinary microscopic preparations, are due to the coagulation of micellae by the fixative employed. Under the ultramicroscope, the vitreous is optically empty to begin with. Then innumerable minute fibrillae appear in the beam of light, crisscrossing one another. Soon these break down into strings of beads and end page 318 on the internal form. Finally, only separate dots are seen. Other sources of error arise from the optical principles concerned in microscopic vision. For the diffraction pattern, which we call the image, may, under certain circumstances, be very different from the actual object. Furthermore, the optical properties of living protoplasm are especially complicated and imperfectly known, as in general those of colloids may be said to be. The minute aggregates of the dispersed phase of gels produce a scattering action on light, leading to appearances of turbidity, etc., with no other or more real basis. So it comes to pass that some writers have altogether denied the existence in the living cell protoplasm of a network or alveolar foam. Others have cast doubts on the main tenets of recent histology regarding nuclear structure, and Hardy, discussing the structure of certain gland cells, declared that there is no evidence that the structure discoverable in the cell substance of these cells after fixation has any counterpart in the cell when living. A large part of it, he went on to say, is an artifact. The profound difference in the minute structure of a secretory cell of a mucous gland, according to the reagent which is used to fix, would, it seems to me, almost suffice to establish this statement in the absence of other evidence. Nevertheless, histological study proceeds, especially on the part of the morphologist, with but little change in theory or in method, in spite of these and many other warnings, that certain visible structures, nucleus, back walls, attraction spheres, or centrosomes, etc., are actually present in the living cell we know for certain. And to this class belong the majority of structures with which we are at present concerned. That many ODR alleged structures are artificial has also been placed beyond a doubt. But where to draw the dividing line we often do not know. The following is a brief epitome of the visible changes undergone by a typical cell, subsequent to the resting stage, leading up to the act of segmentation, and constituting the phenomenon of mitosis or karyokinetic division. In the fertilized egg of a sea urchin, we see with almost diagrammatic completeness, in fixed and stained specimens, what is set forth here. Page 319 in structure of the cell. 1. The chromatin, which to begin with had been dimly seen as granules on a vague achromatic reticulum, figures 89, 90, perhaps no more than an histological artifact, concentrates to form a skein or spiring, often looked on as a continuous thread. but perhaps discontinuous or fragmented from the first. It, or its several fragments, will presently split asunder, for it is essentially double and may even be seen as a double thread or pair of chromatids from an early stage. The chromosomes are portions of this double thread, which shorten down to form little rods, straight or curved, often bent into a V, sometimes ovoid, round, or even annular, and which in the living cell are frequently seen in active, writhing movement, like eels in a box. They keep apart from one another as by some repulsion and tend to move outward towards the nuclear membrane. Certain deeply staining masses, the nucleoli, may be present in the resting nucleus, but take no part, at least as a rule, in the formation of the chromosomes. They are either cast out of the nucleus and dissolved in the cytoplasm, or else fade away in situ. pH 320. But this rule does not always hold, for they persist in many protozoa. And now and then the nucleolus remains and becomes itself a chromosome, as in the spermagonia of certain insects. Meanwhile, a certain deeply staining granule, here extranuclear, known as the centrosome, has divided into two godiae. It is all but universally visible, save in the higher plants. Perhaps less stress is laid on it than at one time, but Bouverie called it the dynamic center of the cell. The two resulting granules travel to opposite poles of the nucleus, and there each becomes surrounded by a star-like figure, the aster, of which we have spoken already. Immediately around the centrosome is a clear space, the centrosphere. Between the two centrosomes, or the two asters, stretches the spindle. It lies in the long axis, if there be one of the cell, a rule laid down nearly 60 years ago, and still remembered as Hertwig's law. But the rule is as much, and no more than to say that the spindle sets in the direction of least resistance. Where the egg is laden with food yolk, as often happens, the latter is heavier than the cytoplasm, and gravity, by orienting the egg itself, thus influences, though only indirectly, the first planes of segmentation. The definite nuclear outline is soon lost, for the chemical phase difference between nucleus and cytoplasm has broken down, and where the nucleus was, the chromosomes now lie. The lines of the spindle become visible. The chromosomes arrange themselves midway between its poles to form the equatorial plate and are spaced out evenly around the central spindle, again a simple result of mutual repulsion. 4. Each chromosome separates longitudinally into two, usually at this stage, but it is to be noted that the splitting may have taken place as early as the Speiermann stage, page 321, and structure of the cell. The halves of the split chromosomes now separate from and apparently repel one another, traveling in opposite directions towards the two poles, figure 92b, for all the world as though they were being pulled sunder by actual threads. Figure 91a, figure 91b, equatorial plate, spindle fibers, aster, figure 92a, nucleolus, split chromosome, figure 92b, central spindle, mantle fibers, nucleolus 6. Presently, the spindle itself changes shape, lengthens and contracts, and seems as it were to push the two groups of daughter, page 322, on the internal form chromosomes into their new places. And its chromosomes form once more an alveolar reticulum and may occasionally form another spirem at this stage. A boundary surface, or at least a recognizable phase difference, now develops around each reconstructed nuclear mass, and the spindle disappears. The centrosome remains, as a rule, outside the nucleus. 7. On the central spindle, in the position of the equatorial plate, a cell plate, consisting of deeply staining thickenings, has made its appearance during the migration of the chromosomes. This cell plate is more conspicuous in plant cells. Figure 93a, figure 93b8. Meanwhile, a constriction has appeared in the cytoplasm, and the cell divides through the equatorial plane. In plant cells, the line of this division is foreshadowed by the cell plate, which extends from the spindle across the entire cell, and splits into two layers, between which appears the membrane by which the daughter cells are cleft asunder. In animal cells, the cell plate does not attain such dimensions, and no cell wall is formed. The whole process takes from half an hour to an hour, and this extreme slowness is not the least remarkable part of the phenomenon, from a physical point of view. The two halves of the B page 323 and structure of the cell. Dividing centrosome while moving apart takes some 20 minutes to travel a distance of 20 mil, or at the rate, say, of 2 years to a yard. It is a question of inertia, and the inertia of the system must be very large. The beautiful technique of cell culture in vitro has, of late years, let this whole succession of phenomena, once only to be deduced from sections, be easily followed as it proceeds within the living tissue or cell. The vivid accounts which have been given of this spectacle add little to the older account as we have related it, save that when the equatorial constriction begins and the halves of the split chromosomes drift apart, the protoplasm begins to show a curious and even violent activity. The cytoplasm is thrust in and out in bulging pustules or balloons, and the granules and fat globules stream in and out as the pustules rise and fall away. At length, the turmoil dies down, and now each half of the cell, not an ovum but a tissue cell or fibroblast, pushes out large pseudopodia, flattens into an amoeboid phase, the connecting thread of protoplasm snaps in the divided cell, and the daughter cells fall apart and crawl away. The two groups of chromosomes, on reaching the poles of the spindle, turn into bunches of short, thick rods. These grow diffuse and form a network of chromatin within a nucleus. And at last, the chromosomes, having lost their identity, disappear entirely, and two or more nucleoli are all that is to be seen within the cell, the whole, or very nearly the whole. Of these nuclear phenomena may be brought into relation with some such polarization of forces in the cell as a whole, as is indicated by the spindle and asters of which we have already spoken. Certain particular phenomena, directly attributable to surface tension and diffusion, taking place in more or less obvious and inevitable dependence upon the polar system. At the same time, in attempting to explain the phenomena, we cannot say too clearly, or too often, that all that we are meanwhile justified in doing is to try to show that such and such actions lie within the range of known physical actions and phenomena, or that known physical phenomena produce effects similar to them. We feel that the whole phenomenon is not sui generis, but is somehow or other capable of being referred to dynamical laws, and to page 324 on the internal form, the general principles of physical science. But when we speak of some particular force or mode of action, using it as an illustrative hypothesis, we stop far short of the implication that this or that force is necessarily the very one which is actually at work within the living cell. And certainly we need not attempt the formidable task of trying to reconcile or choose between the various hypotheses which have already been enunciated, or the several assumptions on which they depend. Many other things happen within the cell, especially in the germ cell, both before and after fertilization. They also have a physical element or a mechanical aspect, like the phenomena of cell division which we are speaking of. But the narrow bounds to which we are keeping hold difficulties enough. Any region of space within which action is manifested is a field of force. And a simple example is a bipolar field, in which the action is symmetrical with reference to the line joining 2 points or poles, and with reference also to the equatorial plane equidistant from both. We have such a field of force in T, the neighborhood of the centrosome of the ripe cell or ovum, when it is about to divide, and by the time the centrosome has divided, the field is definitely a bipole. The quality of a medium filling the field of force may be uniform, or it may vary from point to point. In particular, it may depend upon the magnitude of the field, and the quality of one medium may differ from that of another. Such variation of quality within one medium, or from one medium to another, is capable of diagrammatic representation by a variation of the direction or the strength of the field, other conditions being the same, from the state manifested in some uniform medium taken as a standard. The medium is said to be permeable to the force in greater or less degree in the standard medium, according as the variation of the density of the lines of force from the standard case, under otherwise identical conditions, is in excess or defect. A body placed in the medium will tend to move towards regions of greater or less force, according as its page 325 and structure of the cell. Permeability is greater or less than that of the surrounding. In the common experiment of placing iron filings between the two poles of a magnetic field, the filings have a very high permeability, and not only do they themselves become polarized so as to attract one another, but they tend to be attracted from the weaker to the stronger parts of the field. And as we have seen, they would soon gather together around the nearest pole, were it not for friction or some other resistance. But if we repeat the same experiment with such a metal as bismuth, which is very little permeable to the magnetic force, then the conditions are reversed, and the particles, being repelled from the stronger to the weaker parts of the field, tend to take up their position as far from the poles as possible. The particles have become polarized, but in a sense opposite to that of the surrounding or adjacent field. Now, in the field of force, whose opposite poles are marked by the centrosomes, we may imagine the nucleus to act as a more or less permeable body, as a body more permeable than the surrounding medium, that is to say, the cytoplasm of the cell. It is accordingly attracted by and drawn into the field of force and tries, as it were, to set itself between the poles and as far as possible from both of them. In other words, the centrosome foci will be apparently drawn over its surface until the nucleus as a whole is involved within the field of force, which is visibly marked out by the spindle Fig 90b type. If the field of force be electrical or act in a fashion analogous to an electrical field, the charged nucleus will have its surface tensions diminished, with the double result that the inner alveolar meshwork will be broken up, part 1, and that the spherical boundary of the whole nucleus will disappear, part 2. The breakup of the alveoli by thinning and rupture of their partition walls, page 326 on the internal form, leads to the formation of a net, and the further breakup of the net may lead to the unraveling of a thread or spire. Here there comes into play a fundamental principle which, insofar as we require to understand it, can be explained in simple words. The effect, and we might even say the object, of drawing the more permeable body in between the poles is to obtain an easier path by which the lines of force may travel. But it is obvious that a longer route through the more permeable body may at length be found less advantageous than a shorter route through the less permeable medium. That is to say, a more permeable body will only tend to be drawn into the field of force until a point is reached where, so to speak, the way round and the way through are equally advantageous. We should accordingly expect that, on our hypothesis, there would be found cases in which the nucleus was wholly, and others in which it was only partially, and in greater or less degree, drawn into the field between the centrosomes. This is precisely what is found to occur in actual fact. Figures 90A and B represent two so-called types of a phase, which follows that represented in figure 89. According to the usual descriptions, we are told that, in such a case as figure 90B, the primary spindle disappears and the centrosomes diverge to opposite poles of the nucleus, such a condition being found in many plant cells and in the cleavage stages of many eggs. In figure 90A, on the other hand, the primary spindle persists and subsequently comes to form the main or central spindle, while at the same time we see the fading away of the nuclear membrane, the breaking up of the spire into separate chromosomes, and an ingrowth into the nuclear area of the astral rays, all as in figure 91A, which represents the next succeeding phase of figure 90B. This condition of figure 91A occurs in a variety of cases. It is well seen in the epidermal cells of the salamander, and is also on the whole characteristic of the mode of formation of the polar bodies. It is clear and obvious that the two types correspond to mere differences of degree, page 327, and are such as would naturally be brought about by differences in the relative permeabilities of the nuclear mass and of the surrounding cytoplasm, or even by differences in the magnitude of the former body. But now an important change takes place, or rather an important difference appears. For whereas the nucleus as a whole tended to be drawn into the stronger parts of the field, when it comes to breakup, we find, on the contrary, that its contained spirema thread or separate chromosomes tend to be repelled to the weaker parts, whatever this difference may be due, whether, for instance, to actual differences of permeability, or possibly to differences in surface charge or to other causes. The fact is that the chromatin substank E now behaves after the fashion of a diamagnetic body, and is repelled from the stronger to the weaker parts of the field. In other words, its particles, lying in the interpolar field, tend to travel towards the equatorial plane thereof, figures 91, 92, and further tend to move outwards towards the periphery of that plane, towards what the histologist calls the mantle fibers, or outermost of the lines of force of which the spindle is made up, paragraph 5, figure 91bf. And if this comparatively non-permeable chromatin substance come to consist of separate portions, more or less elongated in form, these portions or separate chromosomes will adjust themselves longitudinally in a peripheral equatorial circle. Figures 92a-b. This is precisely what actually takes place. Moreover, before the breaking up of the nucleus, long before the chromatin material has broken up into separate chromosomes, and at the very time when it is being fashioned into a spireme, this body already lies in a polar field and must already have a tendency to set itself in the equatorial plane thereof. But the long, continuous spirum thread is unable, so long as the nucleus retains its spherical boundary wall, to adjust itself in a simple equatorial annulus. In striving to do so, it must tend to coil and kink itself, and in so doing, if all this be, it must tend to assume the characteristic convolutions of the spirome. And here they tend to set themselves in a symmetrical arrangement, figure 94, such as makes for still better equilibrium. D page 328 on the internal form. The particles may be rounded or linear, straight or bent, sometimes annular. They may be all alike, or one or more may differ from the rest, lying as they do in a semi-fluid medium, and subject, doubtless, to some symmetrical play of forces. It is not to be wondered at that they arrange themselves in a symmetrical configuration, and the field of force seems simple enough to let us predict, to some extent, the symmetries open to them. We do not know, we cannot safely surmise, the nature of the forces involved. In discussing Brouwer's observations on the splitting of the chromatic filament, and on the symmetrical arrangement of the separate granules in Ascaris megalocephala, Lilly remarks, this behavior, figure 94, chromosomes, undergoing splitting and separation, after Hatchek and Fleming diagrammatized, is strongly suggestive of the division of a colloidal particle under the influence of its surface electrical charge, and of the effects of mutual repulsion in keeping the products of division apart. It is probable that surface tensions between the particles and the surrounding protoplasm would bring about an identical result, and would sufficiently account for the obvious, and at first sight very curious symmetry. If we float a couple of matches in water, we know that they tend to approach one another till they lie close together, side by side. And if we lay upon a smooth, wet plate 4 matches, half broken across, a similar attraction brings the 4 matches together in the form of a symmetrical cross. Whether one of these or yet another be the explanation of the phenomenon, the explanation. Page 329 to 42, and structure of the cell 315. It is at least plain that by some physical cause, some mutual attraction or common repulsion of the particles, we must seek to account for the symmetry of the so-called tetrads and other more or less familiar configurations. The remarkable annular chromosomes shown in Fig. 95 can be closely imitated by loops of thread upon a soapy film. When the film within the annulus is broken or its tension reduced, the balance of forces is here a simple one, between the uniform capillary tension which tends to widen out the ring and the uniform cohesion of its particles which keeps it together. We may find other cases, at once simpler and more varied, where the chromosomes are bodies of rounded form and more or less Fig. 95. Annular chromosomes formed in the spermatogenesis of the mole cruciate. From Wilson after vom Rath. Uniform size. These also find their way to an equatorial plate, we gather, and Lamb assures us that they are repelled from the centrosomes. They may go near the equatorial periphery, but they are not driven there, and we infer that some bond of mutual attraction holds them together. If they be free to move in a fluid medium, subject both to some common repulsion and some mutual attraction, then their circumstances are much like those of Mayer's well-known experiment of the floating magnets. A number of magnetized needles stuck in corks, all with like poles upwards, are set afloat in a basin. They repel one another and scatter away to the sides, but bring a strong magnet of unlike pole overhead, and the little magnets gather in under its common attraction, while still keeping asunder through their own mutual repulsion. The symmetry of forces leads to a symmetrical configuration, which is G page 330, 316 on the internal form at start. The mathematical expression of a physical equilibrium and is the not too remote counterpart of the arrangement of the electrons in an atom. Be that as it may, it is found that a group of 3, 4 or 5 identical magnets arrange themselves at the corners of an equilateral triangle, square, or pentagon.
but a sixth passes within the ring and comes to rest in the center of symmetry of the pentagon. If there be 7 magnets, 6 form the ring and the 7th occupies the center. If there be 10, there is a ring of 8 and 2 within it, and so on, as follows. Number of magnets, p. page 331, which give rise to the appearance of rays, or striae, around the nucleus. And through increasing diffusion and weakening surface tension, the rounded outline of the nucleus F finale disappears. As we study these manifold phenomena in the individual cases of particular plants and animals, we recognize a close identity of type coupled with almost endless variation of specific detail. And in particular, the order of succession in which certain of the phenomena occur is variable and irregular. The precise order of the phenomena, the time of longitudinal and of transverse fission of the chromatin thread, of the breakup of the nuclear wall, and so forth, will depend upon various minor contingencies and interferences. And it is worthy of particular note that these variations in the order of events and in other subordinate details, while end page 332 on the internal form, doubtless attributable to specific physical conditions, would seem to be without any obvious classificatory meaning or other biological significance. So far as we have now gone, there is no great difficulty in pointing to simple and familiar examples of a field of force which are similar or comparable to the phenomena which we witness within the cell. But among these latter phenomena, there are others for which it is not so easy to suggest, in accordance with known laws, a simple mode of physical causation. It is not at once obvious how in any system of symmetrical forces, the chromosomes, which had at first been apparently repelled from the poles towards the equatorial plane, should then be split asunder and should presently be attracted in opposite directions, some to one pole and some to the other. Remembering that it is not our purpose to assert that some one particular mode of action is at work, but merely to show that there do exist physical forces, or distributions of force which are capable of producing the required result. I give the following suggestive hypothesis, which I owe to my colleague, Professor W. Petty, as we have begun by supposing that the nuclear or chromosomal matter differs in permeability from the medium, that is to say, the cytoplasm in which it lies.
Let us now make the further assumption that its permeability is variable and depends upon the strength of the field. In Fig. 97, we have a field of force representing our cell, consisting of a homogeneous medium and including 2 opposite poles. Lines of force are indicated by full lines, and loci of constant magnitude of force are shown by dotted lines, these latter being what are known as Cayley's equipotential curves. Let us now consider a body whose permeability mu depends on the strength of the field F at 2 field strengths, such as F sub A, F sub B. Let the permeability of the body be equal to that of the medium, and let the curved line in Fig. 98 represent generally its permeability at other field strengths, and let the outer and inner dotted curves in Fig. 97 represent respectively the loci of the field strengths, F sub B. Page 333 for structure of the cell 319, and F at the body. If it be placed in the medium within either branch of the inner curve or outside the outer curve, will tend to move into the neighborhood of the adjacent pole. If it be placed FB Fig. 97, Fig. 98, in the region intermediate to the 2 dotted curves, it will tend to move towards regions of weaker field strength. The locus fly is therefore a locus of stable position, towards which the body tends to move. The locus FFA is a locus of unstable position, from which it tends to move. If the body were placed across FGT page 334, it might be torn asunder into 2 portions, the split coinciding with the locus FA suppose a number of such bodies to be scattered throughout the medium. Let at first the regions FA and FB be entirely outside the space where the bodies are situated, and in making this supposition we may, if we please, suppose that the loci, which we are calling FA and FB, are meanwhile situated somewhat farther from the axis than in our figure. That, for instance, FA is situated where we have drawn FB, and that FB is still farther out. The bodies then tend towards the poles, but the tendency may be very small if in Fig. 98, the curve and its intersecting straight line do not diverge very far from one another beyond FA. In other words, if, when situated in this region, the permeability of the bodies is not very much in excess of that of the medium. Figure 99.
Let the poles now tend to separate farther and farther from one another, the strength of each pole remaining unaltered. In other words, let the centrosome foci recede from one another, as they actually do, drawing out the spindle threads between them. The loci FA, FB will close in to nearer relative distances from the poles. In doing so, when the locus F crosses one of the bodies, the body may be torn asunder, if the body be of elongated shape, and be crossed at more points than one. The forces at work will tend to exaggerate its foldings, and the tendency to rupture is greatest when FA is in some median position, phi 99, when the locus FA has passed entirely over the body. The body tends to move towards regions of weaker force, but when, in turn, the locus FB has crossed it, then the body again moves towards regions of stronger force, that is to say, towards the nearest pole. P hours 335 for the and structure of the cell 321, and in thus moving towards a pole, it will do so as appears actually to be the case in the dividing cell along the course of the outer hues of force, i.e. male fibers of the histologist. Such considerations as these give general results, easily open to modification in detail by a change of any of the arbitrary postulates which have been made for the sake of simplicity. Doubtless, there are other assumptions which would meet the case, for instance, that during the active phase of the chromatin molecule, when it decomposes and sets free nucleic acid, it carries a charge opposite to that which it bears during its resting, or alkyne phase. And it would accordingly move towards different poles under the influence of a current wandering with its negative charge in an alkali fluid during its acid phase to the anode, and to the cathode during its alkali phase. A whole field of speculation is opened up when we begin to consider the cell not merely as a polarized electrical field, but also as an electrolytic field full of wandering ions. Indeed, it is high time we reminded ourselves that we have perhaps been dealing too much with ordinary physical analogies, and that our whole field of force within the cell is of an order of magnitude where these grosser analogies may fail to serve us, and might even play us false or lead us astray. But our sole object, meanwhile, as I have said more than once, is to demonstrate, by such illustrations as these, that, whatever be the actual and as yet unknown modus operandi,
There are physical conditions and distributions of force which could produce just such phenomena of movement as we see taking place within the living cell. This and no more
is precisely what Descartes is said to have claimed for his description of the human body as a mechanism F, while it can scarcely be too often repeated that our inquiry is not directed towards the solution of physiological problems,
save only insofar as they are inseparable from the problems presented by the visible configurations of form and structure, and while we try as far as possible to evade the difficult question of what when we have not taken account in the above paragraphs of the obvious fact that the supposed symmetrical field of force is distorted by the presence in it of the more or less permeable bodies. Nor is it necessary for us to do so, for to that distorted field the above argument continues to apply, word for word. T. Michael Foster, Lectures on the History of Physiology, 1901, p. 62. Page 336. Particular forces are at work when the mere visible forms produced are such as to leave this an open question. Yet, in this particular case, we have been drawn into the use of electrical analogies, and we are bound to justify, if possible, our resort to this particular mode of physical action. There's an important paper by R.S. Lilly on the electrical convection of certain free cells in nuclei, which, while I cannot quote it in direct support of the suggestions which I have made, yet gives just the evidence we need in order to show that electrical forces act upon the constituents of the cell, and that their action discriminates between the two species of colloids represented by the cytoplasm and the nuclear chromatin. And the difference is such that in the presence of an electrical current, the cell substance and the nuclei, including sperm cells, tend to migrate, the former on the whole with the positive, the latter with the negative stream. A difference of electrical potential being thus indicated between the particle and the surrounding medium, just as in the case of minute suspended particles of various kinds in various feebly conducting media. And the electrical difference is doubtless greatest in the case of the cell constituents, just at the period of mitosis, when the chromatin is invariably in its most deeply staining, most strongly acid, and therefore, presumably,
in its most electrically negative phase. In short, Lilly comes easily to the conclusion that electrical theories of mitosis are entitled to more careful consideration than they have hitherto received. Page 337, among other investigations, all leading towards the same general conclusion. All leading to, namely, that differences of electric potential play their part in the phenomena of cell division. I would mention a noteworthy paper by Ida H. Hyde, in which the writer shews, among other important observations, that not only is there a measurable difference of potential between the animal and vegetative poles of a fertilized egg, fundulus, toad, turtle, etc., but also that this difference fluctuates, or actually reverses its direction, periodically, at epochs coinciding with successive acts of segmentation or other important phases in the development of the egg, just as other physical rhythms, for instance, in the production of carbon dioxide, had already been shown to do. Figure 100, final stage in the first segmentation of the egg of Cerebratulus. From Prenant, after Co., figure 101. Diagram of field of force with two similar poles. Hence, we need not be surprised to find that the materialized lines of force, which in the earlier stages formed the E-page 338 on the internal form, convergent curves of the spindle, are replaced in the later phases of karyokinesis by divergent curves, indicating that the two foci, which are marked out in the field by the divided and reconstituted nuclei, are now alike in their polarity. 100, 101. The foregoing account is based on the provisional assumption that the phenomena of karyokinesis are analogous to those of a bipolar electrical field, a comparison which seems to offer a helpful and instructive series of analogies. But there are other forces which lead to similar configurations. For instance, some of Leduc's diffusion experiments offer very remarkable analogies to the diagrammatic phenomena of karyokinesis, as shown in Fig. 102. Figure 102. Artificial karyokinesis, after Leduc, for comparison with Fig. 88, page 299. Here we have two identical, not opposite, poles of osmotic concentration, formed by placing a drop of Indian ink in salt water, and then on either side of this central drop, a hypertonic drop of salt solution, more lightly colored. On either side, the pigment of the central drop has been drawn towards the focus nearest to it, but in the middle line, the pigment is drawn in opposite directions by equal forces, and so tends to remain undisturbed, in the form of an equatorial plate. To account for the same metotic phenomena, an elegant hypothesis has been put forward by A.B. Lamb and developed by Graham in page 339 canon. It depends on certain investigations of the Bjerknes, father and son, which prove that bodies pulsating or oscillating in a fluid set up a field of force precisely comparable with the lines of force in a magnetic field. Certain old and even familiar observations had pointed towards this phenomenon. Gaia had noticed that bits of paper were attracted towards a vibrating tuning fork, and Shellbach found that a sounding board so acts on bodies in its neighborhood as to attract those which are heavier and repel those which are lighter than the surrounding medium. In air, bits of paper are attracted, and a gas flame is repelled. To explain these simple observations, Bjerknes experimented with little drums attached to an automatic bellows. He found that two bodies in a fluid field, synchronously pulsating or synchronously oscillating, repel one another when their oscillations are in the same phase, or their pulsations are in opposite phase, and vice versa, while other particles floating passively in the same fluid tend, as Shellbach had observed before, to be attracted or repulsed according as they are heavier or lighter than the fluid medium. The two bodies behave towards one another like two electrified bodies, or like two poles of a magnet. We are entitled to speak of them as hydrodynamic poles. We might even call them hydrodynamic magnets. And pursuing the analogy, we may call the heavy bodies paramagnetic, and the light ones diamagnetic with regard to them. Lamb's hypothesis, then, and canons, is that the centrosomes act as hydrodynamic magnets. The explanation depends on oscillations which have never been seen, in centrosomes which are not always to be discovered. But it brings together certain curious analogies, and these, where we know so little, may be worth reflecting on. If we assume that each centrosome is endowed with a vibratory motion as it floats in the semi-fluid colloids, or hydrosol. To use Graham's word of the cell,
we may take it that the visible intracellular phenomena will be much the same as those we have page 340 on the internal form. Described under an electrical hypothesis, the lines of force will have the same distribution, and such movements as the chromosomes undergo, and such symmetrical configurations as they assume, may be accounted for under the one hypothesis pretty much as under the other. There are, however, other phenomena accompanying mitosis, such as Chambers' astral currents and certain local changes in the viscosity of the egg, which are more easily explained by the hydrodynamic theory. We may assume that the cytoplasm, however complex it may be, is but a sort of microscopically homogeneous emulsion of high dispersion. That is to say, one in which the minute particles of one phase are widely scattered throughout and freely mobile. And this indeed is what is meant by calling it a hydrosol. Let us assume also that the particles are a little less dense than the continuous phase in which they are dispersed. And assume lastly, it is not the easiest of our assumptions, that these ultraminute particles will be affected, just as are the grosser ones, by the forces of the hydrodynamic field. All this being so, the dispersed particles will be repelled from the oscillating centrosome with a force which falls off very rapidly, for Bjerknes tells us that it varies inversely as the seventh power of the distance, a round clear field like a drop or a bubble, will be formed round the centrosome, and the dispersed particles expelled from this region will tend to accumulate in a crowded spherical zone immediately beyond it. Outside of this, again, they will continue to be repulsed, but slowly, and we may expect a second and lesser concentration at the periphery of the cell. A clear central mass, or centrosphere, will thus come into being, and the surrounding cytoplasm will be rendered denser and more viscous, especially close around the centrosphere, and again peripherally, by condensation of the dispersed particles. Moreover, all outward movements of these lighter particles entail inward movements of the heavier, which, by hypothesis, are also the more fluid. Streamlines or visible currents will flow towards the center, giving rise to the star-shaped aster. And the best accounts of the sea urchin's egg tally well with what is thus deduced from the hydrodynamic on page 341 and structure of the cell. The round drop of clear fluid, which forms the center of the aster, grows as the aster grows, fluid streaming towards it from all parts of the cell along the channels of the astral rays. The cytoplasm between the rays is in the gel state, but gradually passes into a sol beyond the confines of the aster. Seifritz asserts that the substance of the centrosphere is not much more viscous than water, but that the wedges of cytoplasm between the inwardly directed streams are stiff and viscous. After the centrosome divides, we have two oscillating bodies instead of one. They tend to repel one another and pass easily through the fluid centrosphere to the denser layer. But now the new centrosomes, on opposite sides of the centrosphere, repel each on its own side, the dispersed particles of the denser zone, and two new asters are formed, their rays marked by the streams coursing inwards to the centrosome foci. Thus the amphiaster comes into being. It is not that the old aster divides as a definite entity, but the old aster ceases to exist when its focus is disturbed, and about the new foci, new asters are necessarily and automatically developed. Again, this hypothetic account tallies well with Chambers' description. The same attractions and repulsions should be manifested, perhaps better still, in whatsoever bodies lie or float within the cell, whether liquid or solid, oil globules, yolk particles, mitochondria, chromosomes, or whatnot. A zoned, concentric arrangement of yolk globules is often seen in the egg, with the centrosome as focus. And in certain sea urchin eggs, the mitochondria gather around the centrosome, while the amphiaster is forming, collecting together in that very zone to which Chambers ascribes a semi-rigid or viscous consistency. The Golgi bodies found in various germ cells are at first black, rod-like bodies embedded in the centrosphere. They undergo changes in complex movements, now scattering through the cytoplasm and anon crowding again around the centrosome. Some periodic change in the density of these bodies compared with page 342 on the internal form. That of the medium in which they lie seems all that is required to account for their excursions. And such changes of density are not only of likely occurrence during the active chemical operations associated with fertilization and division,
but are in all probability inseparable from the changes in viscosity, which are known to occur. The movements and arrangements of the chromosomes already described may be easily accounted for if we postulate, in addition to their repulsion from the oscillating centrosomes, induced oscillations in themselves such as to cause them to attract one another. The well-defined length of the spindle and the position of equilibrium in which it comes to rest may be conceived as resultants of the several mutual repulsions of the centrosomes by one another, by the chromosomes or other lighter material of the equatorial plate, and again by such lighter material as may have accumulated at the periphery of the egg. The first two of these will tend to lengthen the spindle, the last to shorten it. And the last will especially affect its position and direction. When Chambers amputated part of an amphiastral egg, the remains of the amphiaster disappeared, and then came into being again in a new and more symmetrical position. It, or its centrosomal focus, had been symmetrically repelled, we may suppose, by the fresh surface. Hertwig's law that the spindle axis tends to lie in the direction of the largest mass of protoplasm, in other words, to point where the cell surface lies farthest off, and its repulsion is least felt, may likewise find its easy explanation. Between these hypotheses, we may choose one or other, if we choose at all, according to our judgment. As Henri Poincaré tells us, we never know that any one physical hypothesis is true. We take the simplest we can find, and this we call the guiding principle of simplicity. In this case, the hydrodynamic hypothesis is a simple one, but it all rests on a hypothetic oscillation of the centrosome, which has never been witnessed. Bayliss has shown that precisely such reversible states of gelation as we have been speaking of as 2-piece 343 or VD, and structure of the cell 329, periodic changes in viscosity, may be induced in living protoplasm by electrical stimulation. On the other hand, the fact that the hydrodynamic forces fall off as fast as they do with increasing distance admits their efficacy, and the minute dispersed particles must, under Stokes's law, be slow to move. Lastly, it may well be, as Lilly has urged, that such work as his own, or Ida Hyde's, or Gray's, on change of potential in developing eggs, taken together with that of many others on the behavior of colloid particles in an electrical field, has not yet been followed out in all its consequences, either on the physical or the physiological side of the problem. But to return to our general discussion, as regards the actual mechanical division of the cell into two halves, we shall see presently that in certain cases, such as that of a long cylindrical filament, surface tension, and what is known as the principle of minimal areas, go a long way to explain the mechanical process of division. And in all cells whatsoever, the process of division must somehow be explained as the result of a conflict between surface tension and its opposing forces. But in such a case as our spherical cell, it is none too easy to see what physical cause is at work to disturb its equilibrium and its integrity. The fact that when actual division of the cell takes place, it does so at right angles to the polar axis and precisely in the direction of the equatorial plane, would lead us to suspect that the new surface formed in the equatorial plane sets up an annular tension directed inwards, where it meets the outer surface layer of the cell itself. But at this point, the problem becomes more complicated. Before we can hope to comprehend it, we shall have not only to inquire into the potential distribution at the surface of the cell in relation to that which we have seen to exist in its interior, but also to take account of the differences of potential which the material arrangements along the lines of force must themselves tend to produce. Only thus can we approach a comprehension of the balance of forces which cohesion, friction, capillarity, and electrical distribution combine to set up. The manner in which we regard the phenomenon would seem to WMN. Bayliss, reversible gelation in living protoplasm, Prox DRS BXDL 196, 296, 29720. Page 344 turn, in great measure, upon whether or no we are justified in assuming that in the liquid surface film of a minute spherical cell, local and symmetrically localized differences of surface tension are likely to occur. If not, then changes in the conformation of the cell, such as lead immediately to its division, must be ascribed not to local changes in its surface tension, but rather to direct changes in internal pressure, or to mechanical forces
due to an induced surface distribution of electrical potential. We have little reason to be skeptical. In fact, we now know that the cell is so far from being chemically and physically homogeneous that local variations in its surface tension are more than likely. They are certain to occur. Bütschli suggested more than 60 years ago that cell division was brought about by an increase of surface tension in the equatorial region of the cell, and the suggestion was the more remarkable that it was, I believe. The very first attempt to invoke surface tension as a factor in the physical causation of a biological phenomenon. An increase of equatorial tension would cause the surface area there to diminish, and the equator to be pinched in, but the total surface area of the cell would be increased thereby, and the two effects would strike a balance. But as Bütschli knew very well, the surface tension change would not stand alone. It would bring other phenomena in its train. Currents would tend to be set up, and tangential strains would be imposed on the cell membrane or cell surface as a whole. The secondary, if not the direct effects of increased equatorial tension, might after all suffice for the division of the cell. It was Loeb in 1895 who first showed that streaming went on from the equator towards the divided nucleus. To the violence of these streaming movements he attributed the phenomenon of division, and many other physiologists have adopted this hypothesis. The currents of which Loeb spoke call for countercurrents towards the equator, in or near the surface of the cell, and theory and observation both indicate that precisely such currents are bound to be set up by the surface energy involved in the increase of equatorial tension. An opposite view has been held by some, and especially by T.B. Robertson. Quincke had shown that the formation of soap at the surface of an oil droplet lowers the surface tension of the latter, and that if the saponification be local, that part of the surface tends to enlarge and spread out accordingly. Robertson, in a very curious experiment, found that by laying a thread moistened with dilute caustic alkali or merely smeared with soap across a drop of olive oil afloat in water, the drop at once divided into two parts. A vast amount of controversy has arisen over this experiment, but Speke seems to have shown conclusively that it is an exceptional case. In a drop of olive oil balanced in water and touched anywhere with an alkali, there is so copious a formation of lighter soaps that differences of density tend to drag the drop in two. But in the case of other oils, and especially the thinner oils, such as oil of bergamot, the saponified portion bulges, as theory directs. And when the alkali is applied to two opposite poles, the equatorial region is pinched in, as McClendon, in opposition to Robertson, had found it to do. Conversely, if an alkaline thread be looped around the drop, the zone of contact bulges, and instead of dividing at the equator, the drop assumes a lens-like form. We may take it then as proven that a relative increase of equatorial surface tension, whether in oil drops, mercury globules, or living cells, does lead or tend to lead to an equatorial constriction. In all cases, a system of surface currents is set up among the fluid drops towards the zone of increased tension, and an axial countercurrent flows towards the pole or poles of lowered tension. Precisely such currents have been observed to run in various eggs, especially of page 346 on the internal form. Certain nematodes during division of the cell. But if the process be slow, more than 7 or 8 minutes long, the slow currents become hard to see. Various contents of the cell are transported by these currents, and clear, yolk-free polar caps and equatorial accumulations of yolk and pigment are among the various manifestations of the phenomenon. The extrusion of a polar body at a small and sharply defined region of lowered tension is a particular case of the same principle. But purely chemical changes are not of necessity the fundamental cause of alteration in the surface tension of the egg, for the action of electrolytes on surface tension is now well known and easily demonstrated. So, according to other views than those with which we have been dealing, electrical charges are sufficient in themselves to account for alterations of surface tension, and in turn for that protoplasmic streaming, which, as so many investigators agree, initiates the segmentation of the egg. A great part of our difficulty arises from the fact that in such a case as this, the various phenomena are so entangled and apparently concurrent that it is hard to say which initiates another, and to which this or that secondary phenomenon may be considered due. Of recent years, the phenomenon of adsorption has been adduced, as we have already briefly said, in order to account for many of the events and appearances which are associated with the asymmetry and lead towards the division of the cell.
But our short discussion of this phenomenon may be reserved for another chapter.
However, we are not directly concerned here with the phenomena of segmentation or cell division in themselves, except only insofar as visible changes of form are capable of easy and obvious correlation with the play of force.
The very fact of development indicates that, while it lasts, the equilibrium of the egg is never complete.
And the gist of the matter is that if you have karyokinetic figures developing inside the cell, that of itself indicates that the dynamic system and the localized forces arising from it are in NPH 347 and structure of the cell. Gradual alteration and changes in the outward configuration of the system are bound, consequently, to take place. Perhaps we may simplify the case still more. We have learned many things about cell division, but we do not know much in the end. We have dealt perhaps with too many related phenomena and failed because we tried to combine and account for them all. A physical problem, still more a mathematical one, wants reducing to its simplest terms.
And Dr. Rashevsky has simplified and generalized the problem of cell division, or division of a drop, in a series of papers, which still outrun by far the elementary mathematics of this book. If we cannot follow him in all he does, we may find useful lessons in his way of doing it. Cells are of many kinds. They differ in size and shape, in visible structure, and chemical composition. Most have a nucleus, some few have none. Most need oxygen, some few do not. Some metabolize in one way, some in another. What small residuum of properties remains common to them all? A living cell is a little fluid or semi-fluid system in which work is being done, physical forces are in operation, and chemical changes are going on. It is in such intimate relation with the world outside, its own milieu intern with the great milieu externe, that substances are continually entering the cell, some to remain there and contribute to its growth, some to pass out again with loss of energy and metabolic change. The picture seems simplicity itself, but it is less simple than it looks. For on either side of the boundary wall, both in the adjacent medium and in the living protoplasm within, there will be no uniformity, but only degrees of activity and gradients of concentration. Substances which are being absorbed and consumed will diminish from periphery to center. Those which are diffusing outwards have their greatest concentration near the center, decrease towards the periphery, and diminish further with increasing distance in the near neighborhood of the system. Size, shape, diffusibility, permeability, chemical properties of this and that may affect the gradients, but in the living cell, the interchanges are always going on, and the gradients are always there. Page 348 on the internal form. If the cell be homogeneous, taking in and giving out at a constant rate in a uniform way, its shape will be spherical. The concentration field of force, or concentration field, will likewise have a spherical symmetry, and the resultant force will be zero. But if the symmetry be ever so little disturbed and the shape be ever so little deformed, then there will be forces at work tending to increase the deformation, and others tending to equalize the surface tension and restore the spherical symmetry. And it can be shown that such agencies are within the range of the chemistry of the cell. Since surface tension becomes more and more potent as the size of the drop diminishes, it follows that, under fluid conditions, the smallest solitary cells are least likely to depart from a spherical shape, and that cell division is only likely to occur in cells above a certain critical order of magnitude, and using such physical constants as are available. Rashevsky finds that this critical magnitude tallies fairly well with the average size of a living cell. The more important lesson to learn, however, is this, that merely by virtue of its metabolism, every cell contains within itself factors which may lead to its division after it reaches a certain critical size. There are simple corollaries to this simple setting of the case, since unequal concentration gradients are the chief cause which renders non-spherical shapes of cell possible, and these last only so long as the cell lives and metallizes. It follows that, as soon as the gradients disappear, whether in death or in a resting stage, the cell reverts to a spherical shape and symmetry. Again, not only is there a critical size above which cell division becomes possible and more probable,
but there must also be a size beyond which the cell is not likely to grow. For the specific surface decreases, the metabolic exchanges diminish, the gradients become less steep, and the rate of growth decreases too. There must come a stage where anabolism just balances catabolism, and growth ceases though life goes on. When streaming currents are visible within the cell, they seem to complicate the problem. But after all, they are part of the result and proof of the existence of the gradients we have described. In any further account of Rashevsky's theories, the mathematical difficulties very soon begin. But it is well to realize that pure theory often carries the mathematical physicist a long way, and that higher and higher powers of the microscope, and EP 349 and structure of the cell, greater and greater histological skill are not the one and only way to study the physical forces acting within the cell. As regards the phenomena of fertilization, of the union of the spermatozoon with the pronucleus of the egg, we might study these also in illustration, up to a certain point of the forces which are more or less manifestly at work. But we shall merely take as a single illustration the paths of the male and female pronuclei as they travel to their ultimate meeting place. The spermatozoon, when within a very short distance of the egg cell, is attracted by it, the same attraction being further manifested in a small conical uprising of the surface of the egg. The nature of the attractive force has been much disputed. Loeb found the spermatozoon to be equally attracted by other substances, even by a bead of glass. It has been held also that the attraction is chemotropic, some substance being secreted by the egg which drew the sperm towards it. Just as Pfeffer, having shown that malic acid has an attraction for antheridia, suppose this substance to play its attractive part within the mucus of the archegonia. Again, the chemical secretion may be neither attractive nor directive, but yet play a useful part in activating the spermatozoa. However that may be, Gray has shown reason to believe that an electromotive force is developed in the contact between active spermatozoon and inactive ovum, and that it is the electrical change so set up and almost instantaneously propagated, which precludes the entry of another spermatozoon. Whatever the force may be, it is one which acts normally to the surface of the ovum, and after entry the P page 350I on the internal form, the spermatozoon points straight towards the center of the egg, from the fact that other spermatozoa, subsequent to the first, fail to effect an entry. We may safely conclude that an immediate consequence of the entry of the spermatozoon is an increase in the surface tension of the egg, this being but one of the complex reactions exhibited by the surface or cortex of the cell. Somewhere or other, within the egg, near or far away, lies its own nuclear body, the so-called female pronucleus, and we find that after a while this has fused with the male pronucleus or head of the spermatozoon, and that the body resulting from their fusion has come to occupy the center of the egg. This must be due, as Whitman pointed out many years ago, to a force of attraction acting between the two bodies, and another force acting upon one or other or both in the direction of the center of the cell. Did we know the magnitude of these several forces, it would be an easy task to calculate the precise path which the two pronuclei would follow, leading to conjugation and to the central position. As we do not know the magnitude, but only the direction of these forces, we can only make a general statement. 1. The paths of both moving bodies will lie wholly within a plane triangle drawn between the two bodies and the center of the cell. 2. Unless the two bodies happen to lie, to begin with, precisely on a diameter of the cell, their paths, until they meet one another, will be curved paths, the convexity of the curve being towards the straight line joining the two bodies. 3. The two bodies will meet a little before they reach the center, and having met and fused, will travel on to reach the center in a straight line. The actual study and observation of the path followed is not very easy, owing to the fact that what we usually see is not the path itself, but only a projection of the path upon the plane of the microscope. But the curved path is particularly well seen in the frog's egg, where the path of the spermatozoon is marked by a little streak of brown pigment, and the fact of the meeting of the pronuclei before reaching the center has been repeatedly seen by many observers. The problem recalls the famous problem of three bodies, which has so occupied the astronomers, and it is obvious that the foregoing brief description is very far from including all possible cases. Many of these are particularly described in the works of Foale, Roux, Whitman, and others, The intracellular phenomena of which we have now spoken have assumed great importance in biological literature and discussion during the last 50 years. But it is open to us to doubt whether they will be found in the end to possess more than a secondary, even a remote biological significance. Most, if not all of them, would seem to follow immediately and inevitably from certain simple assumptions as to the physical constitution of the cell, and from an extremely simple distribution of polarized forces within it.
We have already seen that how a thing grows, and what it grows into is a dynamic and not a merely material problem. So far as the material substance is concerned, it is so only by reason of the chemical, electrical, or other forces which are associated with it. But there is another consideration which would lead us to suspect that many features in the structure and configuration of the cell are of secondary biological importance. And that is the great variation to which these phenomena are subject in similar or closely related organisms, and the apparent impossibility of correlating them with the peculiarities of the organism as a whole. In a broad and general way, the phenomena are always the same. Certain structures swell and contract, twine and untwine, split and unite, advance and retire. Certain chemical changes also repeat themselves. But nature rings the changes on all the details. Comparative study has shown that almost every detail of the processes of mitosis described above is subject to variation in different forms of cells. A multitude of cells divide to the accompaniment of karyokinetic phenomena, but others do so without any visible karyokinesis at all. Sometimes the polarized field of force is within, page 352, 338, form and structure of the cell. Sometimes it is adjacent to, and at other times it lies remote from, the nucleus. The distribution of potential is very often symmetrical and bipolar, as in the case described. But a less symmetrical distribution often occurs with the result that we have, for a time at least, numerous centers of force. Instead of the two main correlated poles, this is the simple explanation of the numerous stellate figures, haploid number of Krayar, Rausum's Fig, 103. Summation diagram showing the percent number of instances among 2,415 phanerogams and 1070 metazoa, in which the chromosomes do not exceed a given number. Data from MJD White, or Stralingen, which have been described in certain eggs, such as those of Chaetopterus. The number of chromosomes may be constant within a group, as in the tailed amphibia, with 12, or very variable, as in sedges and in grasshoppers. In one and the same species of worm, Ascaris megalocephala, and remarkably constant in general as the number in any one species undoubtedly is. Yet we must not forget that in plants and animals alike, the whole range of observed numbers is but a small one, Fig denied. 103. For as regards there are varieties of Artemia salina which hardly differ in outward characters, but differ widely in the number of their chromosomes. The germ nuclei few have less than 6 chromosomes, and few have more than 20. In closely related animals, such as various species of copepods, and even in the same species of worm or insect. The form of the chromosomes and their arrangement in relation to the nuclear spindle have been found to differ in ways alluded to above, while only here and there, as among the chrysanthemums. Two related species or varieties show their own characteristic chromosome numbers, in contrast to the narrow range of the chromosome numbers. We may reflect on the all but infinite possibilities of chemical variability. Miescher showed that a molecule containing 40 C atoms would admit, arithmetically, though not necessarily chemically, of 1,000,000 possible isomers, and changes in position of the N atoms of a protein, for instance, might vastly increase that prodigious number. In short, we cannot help perceiving that many nuclear phenomena are not specifically related to the particular organism in which they have been observed, and that some are not even specially and indisputably connected with the organism as such. They include such manifestations of the physical forces, in their various permutations and combinations, as may also be witnessed, under appropriate conditions, in non-living things. When we attempt to separate our purely morphological, or purely, page 354, 340 form and structure of the cell structure, embryological studies from physiological and physical investigations, we tend ipso facto to regard each particular structure and configuration as an attribute, or a particular character of this or that particular organism. From this assumption, we are easily led to the framing of theories as to the ancestral history,
the classificatory position, the natural affinities of the several organisms. In fact, to apply our embryological knowledge to the study of phylogeny. When we find, as we are not long of finding, that our phylogenetic hypotheses become complex and unwieldy, we are nevertheless reluctant to admit that the whole method, with its fundamental postulates, is at fault.
And yet nothing short of this would seem to be the case in regard to the or her phases, at least of embryonic development. All the evidence at hand goes, as it seems to me, to show that embryological data, prior to and even long after the epoch of segmentation, are essentially a subject for physiological and physical investigation, and have but the esgitis fink, if any, with the problems of zoological classification. Comparative embryology has its own facts to classify, and its own methods and principles of classification. We may classify eggs according to the presence or absence, the paucity or abundance of their associated food yolk, the chromosomes according to their form and their number, the segmentation according to its various types, radial, bilateral, spiral, and so forth. But we have little right to expect. And in point of fact, we shall very seldom, and as it were, only accidentally find that these embryological categories coincide with the lines of natural or phylogenetic classification, which have been arrived at by the systematic zoologist. The efforts to explain heredity by help of genes and D chromosomes, which have grown up in the hands of Morgan and others since this book was first written, stand by themselves in a category which is all their own and constitutes a science which is justified of itself. To weigh or criticize these explanations would lie outside my purpose, even were I fitted to attempt the task. When these great discoveries began to be made, Bateson crossed the ocean to see and hear for himself what Morgan and his pupils had to show and to tell. He came home convinced and humbly marveling. And I leave this great subject on one side, not because I doubt for a moment the facts, nor dispute the hypotheses, nor decry the IM page 355 importance of one another, but because we are so much in the dark as to the mysterious field of force in which the chromosomes lie, far from the visible horizon of physical science, that the matter lies, for the present, beyond the range of problems which this book professes to discuss, and the trend of reasoning which it endeavors to maintain. The cell, which Goodseer spoke of as a center of force, is in reality a sphere of action of certain more or less localized forces. And of these, surface tension is the particular force which is especially responsible for giving to the cell its outline and its morphological individuality. The partially segmented differs from the totally segmented egg, the unicellular infusorian from the minute multi-page 356 cellular turbularian, in the intensity and the range of those surface tensions, which in the one case succeed and in the other fail to form a visible separation between the cells. Adam Sedgwick used to call attention to the fact that very often, even in eggs that appear to be totally segmented, it is yet impossible to discover an actual separation or cleavage through and through between the cells which on the surface of the egg are so clearly delimited. So far, no farther have the physical forces effectuated a visible cleavage. The vacuolation of the protoplasm in actinopheres or actinosphaerium is due to localized surface tensions, quite irrespective of the multinuclear nature of the latter organism. In short, the boundary walls due to surface tension may be present or may be absent, with or without the delimitation of the other specific fields of force, which are usually correlated with these boundaries and with the independent individuality of the cells. What we may safely admit, however, is that one effect of these circumscribed fields of force is usually such a separation or segregation of the protoplasmic constituents, the more fluid from the less fluid, and so forth, as to give a field where surface tension may do its work and bring a visible boundary into being. When the formation of a surface is once effected, its physical condition, or phase, will be bound to differ notably from that of the interior of the cell, and under appropriate chemical conditions, the formation of an actual cell wall, cellulose or other, is easily eye-intelligible. To this subject we shall return again in another chapter. From the moment that we enter on a dynamical conception of the cell, we perceive that the old debates were vain as to what visible portions of the cell were active or passive, living or non-living. For the manifestations of force can only be due to the interaction of the various parts, to the transference of energy from one to another. Certain properties may be manifested, certain functions may be carried on,
by the protoplasm apart from the nucleus. But the interaction of the two is necessary, that other and more important properties or functions may be manifested. We know, for instance, that portions of an infusorian are incapable of regenerating lost parts in the absence of a nucleus, while nucleated pieces soon regain the specific form of the organism. And we are told that reproduction by fission cannot be initiated. So, Boyce 357. Apparently, all its later steps can be carried on, independently of nuclear action. Nor, as Verworn pointed out, can the nucleus possibly be regarded as the sole vehicle of inheritance, since only in the conjunction of cell and nucleus do we find the essentials of cell life. Kern und Protoplasma sind nur vereint lebensfähig, as Nussbaum said. Indeed, we may, with E.B. Wilson, go further and say that the terms nucleus and cell body should probably be regarded as only topographical expressions denoting two differentiated areas in a common structural basis. Endless discussion has taken place regarding the centrosome, some holding that it is a specific and essential structure, a permanent corpuscle derived from a similar pre-existing corpuscle, a fertilizing element in the spermatozoon, a special organ of cell division, a material dynamic center of the cell, as Van Beneden and Boveri call it. While on the other hand, it is pointed out that many cells live and multiply without any visible centrosomes, that a centrosome may disappear and be created anew. And even that, under artificial conditions, abnormal chemical stimuli may lead to the formation of new centrosomes. We may safely take it that the centrosome, or the attraction sphere, is essentially a force, and that this dynamic center may or may not be constituted by, but will be very apt to produce, a concrete and visible concentration of matter. It is far from correct to say, as is often done, that the cell wall or cell membrane belongs to the passive products of protoplasm rather than to the living cell itself, or to say that in the animal cell, the cell wall, because it is slightly developed, is relatively unimportant compared with the important role which it assumes in plants. On the contrary, it is quite certain that, whether visibly differentiated into a semi-permeable membrane or merely constituted by a liquid film, the surface of the cell is the seat of important forces, capillary and electrical, which play an essential part in the dynamics of the cell. Even in the thickened, largely solidified cellulose wall of the plant cell, apart from the mechanical resistances which it affords, the osmotic forces developed in connection with it are of essential importance. But if the cell acts after this fashion as a whole, each part interacting of necessity with the rest, the same is certainly true of UPICH 358, the entire multicellular organism, as Schwann said of old in very precise and adequate words. The whole organism subsists only by means of the reciprocal action of the single elementary parts. As Wilson says again, the physiological autonomy of the individual cell falls into the background, and the apparently composite character which the multicellular organism may exhibit is owing to a secondary distribution of its energies among local centers of action. It is here that the homology breaks down, which is so often drawn and overdrawn between the unicellular organism and the individual cell of the metazoon. Whitman, Adam Sedgwick, and others have lost no opportunity of warning us against the too literal acceptance of the cell theory. Against the view that the multicellular organism is a colony, or as Haeckel called it, in the case of the plant, a republic, of independent units of life. As Goethe said long ago, das Lebendige ist zwar ein Element des Erlegt, aber man kann es aus diesen nicht wieder zusammenstellen und beleben. The dictum of the cellular pathology being just the opposite, jedes Tier erscheint als eine Summe vitaler Einheiten, von denen jeder den vollen Charakter des Lebens an sich trägt. Hofmeister and Sachs have taught us that in the plant, the growth, page 359 of the mass, the growth of the organ, is the primary fact that cell formation is a phenomenon very general in organic life, but still only of secondary significance. Comparative embryology, says Whitman, reminds us at every turn that the organism dominates cell formation, using for the same purpose, one, several, or many cells, massing its material and directing its movements and shaping its organs, as if cells did not exist.
So Robert declared that in the whole world of organisms, das ganz liefert die Teil, nicht die Teile das Ganze. Letzteres setzt die Teile zusammen, nicht diese jenes. And on the botanical side, D'Arcy has summed up the matter in an aphorism. Die Pflanze bildet Zellen, nicht die Zelle bildet Pflanzen. Discussed almost wholly from the concrete or morphological point of view. The question has for the most part been made to turn on whether actual protoplasmic continuity can be demonstrated between one cell and another, whether the organism be an actual reticulum or syncytium. But from the dynamical point of view, the question is much simpler. We then deal not with material continuity, not with little bridges of connecting protoplasm, but with a continuity of forces, a comprehensive field of force, which runs through and through the entire organism, and is by no means restricted in its passage to a protoplasmic continuum. And such a continuous field of force, somehow shaping the whole organism, independently of the number, magnitude, and form of the individual cells, which enter like a froth into its fabric, seems to me certainly and obviously to exist. As Whitman says, the fact that physiological unity is not broken by cell boundaries is confirmed in so many ways that it must be accepted as one of the fundamental truths of biology. Chapter 5. The forms of cells. Protoplasm, as we have already said, is a fluid or a semi-fluid substance, and we need not try to describe the particular properties of the colloid or jelly-like substances to which it is allied, or rather the characteristics of the colloidal state in which it and they exist. We should find it no easy matter, nor need we appeal to precise theoretical definitions of fluidity, lest we come into a debatable land. It is in the most general sense that protoplasm is fluid. As Graham said of colloid matter in general, its softness partakes of fluidity and enables the colloid to become a vehicle for liquid diffusion. Like water itself, when we can deal with protoplasm in sufficient quantity, we see it flows. Particles move freely through it. Air bubbles and liquid droplets show round or spherical within it. And we shall have much to say about other phenomena manifested by its own surface, which are those especially characteristic of liquids. It may encompass and contain solid bodies, and it may secrete solid substances within or around itself. And it often happens in the complex living organism that these solid substances, such as shell or nail or horn or feather, remain when the protoplasm which formed them is dead and gone. But the protoplasm itself is fluid or semi-fluid, and permits a free, though not necessarily rapid, diffusion and easy convection of particles within itself, which simple fact is of elementary importance. Page 361-1. In connection with form, throwing light on what seem to be common characteristics and peculiarities of the forms of living things, much has been done and more said about the nature of protoplasm since this book was written. Calling cytoplasm the cell protoplasm, after deduction of chloroplasts and other gross inclusions, we find it to contain fats, proteins, lecithin, and some other substances combined with much water, up to 97%. To form a sort of watery gel, the microscopic structures attributed to it, alveolar, granular, or fibrillar, are inconstant or invalid. But it does appear to possess an invisible or submicroscopic structure, distinguishing it from an ordinary colloid gel and forming a quasi-solid framework or reticulum. This framework is based on proteid macromolecules in the form of polypeptide chains of great length and carrying in side chains other organic constituents of the cytoplasm. The polymerized units represent the macilla, which the genius of Nageli predicted or postulated more than 60 years ago, and we may speak of a micellar framework as representing in our cytoplasm the dispersed phase of an ordinary colloid. In short, as the cytoplasm is neither true fluid, not true solid, neither is it true colloid in the ordinary sense. Its micellar structure gives it a certain rigidity or tendency to retain its shape, a certain plasticity and tensile strength, a certain ductility or capacity to be drawn out in threads, but yet leaves it with a permeability or semi-permeability, a capacity to swell by imbibition, above all, an ability to stream and flow, which justify our calling it fluid or semi-fluid, and account for its exhibition of surface tension and other capillary phenomena. The older naturalists, in discussing the differences between organic and inorganic bodies, laid stress upon the circumstance that the latter grow by agglutination and the former by what they termed intussusception. The contrast is true, but it applies rather to solid or crystalline bodies as compared with colloids of all kinds, whether living or dead. But it so happens that the great majority of colloids are of organic origin, and out of them our bodies and our food and the very clothes we wear are almost wholly made. A crystal grows by deposition of new molecules one by one and layer by layer, each one superimposed on the solid substratum, G page 362, already formed. Each particle would seem to be influenced only by the particles in its immediate neighborhood, and to be in a state of freedom and independence from the influence, either direct or indirect, of its remoter neighbors. So Lavoisier was the first to say, and as Kelvin and others later on explained the formation and the resulting forms of crystals, so we believe that each added particle takes up its position in relation to its immediate neighbors already arranged, in the holes and corners that their arrangement leaves, and in closest contact with the greatest number. Hence we may repeat or imitate this process of arrangement, with great or apparently even with precise accuracy, in the case of the simpler crystalline systems, by piling up spherical pills or grains of shot. In so doing, we must have regard to the fact that each particle must drop into the place where it can go most easily, or where no easier place offers. In more technical language, each particle is free to take up, and does take up, its position of least potential energy relative to those already there. In other words, already there. For each particle motion is induced until the energy of the system is so distributed that no tendency or resultant force remains to move it more. This has been shown to lead to the production of plane surfaces in all cases where, by the limitation of material, surfaces must occur. Where we have planes, their straight edges and solid angles must obviously occur also, and if equilibrium is to follow, must occur symmetrically. Our piling up of shot to make MIC crystals gives us visible demonstration that the result is actually to obtain, as in the natural crystal, plane surfaces and sharp angles symmetrically disposed. But the living cell grows in a totally different way, very much as a piece of glue swells up in water by imbibition, or by interpenetration into and throughout its entire substance. The semifluid colloid mass takes up water, partly to combine chemically with its individual molecules, partly by physical diffusion into the interstices between molecules or micellae, and partly, as it would seem, in other ways. So that the entire phenomenon is a complex and even an obscure one. But so far as we are concerned, the net result is very simple, for the equilibrium or tendency to equilibrium of fluid pressure in all parts of its interior while the process of imbibition is going on, the constant rearrangement of its fluid mass, the contrast, in short, with the crystalline method of growth, where each particle comes to rest to move,
Relatively to the whole, no more. Lead the mass of jelly to swell up very much as a bladder into which we blow air, and so, by a graded and harmonious distribution of forces, to assume everywhere a routed and more or less bubble-like external form. So when the same school of older naturalists called attention to a new distinction or contrast of form between organic and inorganic objects, in that the contours of the former tended to roundness and curvature, and those of the latter to be bounded by straight lines, planes, and sharp angles, we see that this contrast was not a new and different one, but only another aspect of their former statement, and an immediate consequence of the difference between the processes of agglutination and intussusception. So far, then, as growth goes on, undisturbed by pressure or other external force, the fluidity of the protoplasm, its mobility internal E-page 364, the forms itself, and external, and the way in which particles move freely, hither and thither within, all manifestly tend to the production of swelling rounded surfaces, and to their great predominance over plane surfaces in the contours of the earth. These rounded contours will tend to be preserved for a while, in the case of naked protoplasm by its viscosity, and in presence of a cell wall by its very lack of fluidity. In a general way, the presence of curved boundary surfaces will be especially obvious in the unicellular organisms,
and generally in the external form of all organisms, and wherever mutual pressure between adjacent cells or other adjacent parts has not come into play to flatten the rounded surfaces into planes, the swelling of any object, organic or inorganic, living or dead, is bound to be influenced by any lack of structural symmetry or homogeneity. We may take it that all elongated structures, such as hairs, fibers of silk or cotton, fibrillae of tendon and connective tissue, have, by virtue of their elongation, an invisible as well as a visible polarity. Moreover, the ultimate fibrils are apt to be invested by a protein different from the collagen within, and liable to swell more or to swell less. In ordinary tendons, there is a reticular sheath which swells less and is apt to burst under pressure from within. It breaks into short lengths, and when the strain is relieved, these roll back and form the familiar annuli. Another instance is the tendency to swell of the macromolecules of many polymerized organic bodies, proteins among them. But the rounded contours, which are assumed and exhibited by a piece of hard glue when we throw it into water and see it expand as it sucks the water up, are not near so regular nor so beautiful as are those which appear when we blow a bubble or form a drop or even pour water into an elastic bag. For these curving contours depend upon the properties of the bag itself, of the film or membrane which contains the mobile gas, or which contains or bounds the mobile liquid mass. And hereby, in the case of the fluid or semi-fluid mass, we are introduced to the subject of surface tension, of which indeed we have spoken in the preceding chapter, but which we must now examine with greater care. Page 365 of Surface Tension. Among the forces which determine the forms of cells, whether they be solitary or arranged in contact with one another, this force of surface tension is certainly of great, and is probably of paramount importance. But while we shall try to separate out the phenomena which are directly due to it, we must not forget that in each particular case, the actual conformation which we study may be, and usually is, the more or less complex resultant of surface tension acting together with gravity, mechanical pressure, osmosis, or other physical forces. The peculiar beauty of a soap bubble, solitary or in collocation, depends on the absence, to all intents and purposes, of these alien forces from the field. Hence Plateau spoke of the films which were the subject of his experiments as Lame's fluid sans pesanteur. The resulting form is in such a case so pure and simple that we come to look on it as well nigh a mathematical abstraction. Surface tension, then, is that force by which we explain the form of a drop or of a bubble, of the surfaces external and internal of a froth, or through a collocation of bubbles, and in many other things like. It is a property of liquids, in the sense at least with which our subject is concerned, and it is manifested at or very near the surface, where the liquid comes into contact with another liquid, a solid or a gas. We note here that the term surface is to be interpreted in a wide sense, for wherever we have solid particles embedded in a fluid, wherever we have a non-homogeneous fluid or semi-fluid, or a two-phase colloid such as a particle of protoplasm, wherever we have the presence of impurities, as in a mass of molten metal, there we have always to bear in mind the existence of surfaces and of surface phenomena, not only on the exterior of the mass, but also throughout its interstices. Wherever like and unlike meet, you page 366, the forms of cells, a liquid in the mass is devoid of structure. It is homogeneous and without direction or polarity. But the very concept of surface tension forbids this to be true of the surface layer of a body of liquid, or of the interphase between two liquids, or of any film, bubble, drop, or capillary jet or stream. In all these cases, and more emphatically in the case of a monolayer, even the liquid has a structure of its own. And we are reminded once again of how largely the living organism, whether high or low, is composed of colloid matter in precisely such forms and structural conditions. Surface tension is due to molecular force, to force, that is to say, arising from the action of one molecule upon another. And since we can only ascribe a small sphere of action to each several molecule, this force is manifested only within a narrow range. Within the interior of the liquid mass, we imagine that such molecular interactions negative one another. But near the free surface, within a layer or film approximately equal to the range of the molecular force, or to the radius of the aforesaid sphere of action. There is a lack of equilibrium and a consequent manifestation of force. The action of the molecular forces has been variously explained, but one simple explanation, or mode of statement, is that the molecules of the surface layer are being constantly attracted into the interior by such as are just a little more deeply situated. The surface shrinks as molecules keep quitting it for the interior, and this surface shrinkage exhibits itself as a surface tension. The process continues till it can go no farther. That is to say, until the surface itself becomes a minimal area. This is a sufficient description of the phenomenon in cases where a portion of liquid is subject to no other than its own molecular forces. And, since the sphere has pH 367 of all solids, the least surface for a given volume, it accounts for the spherical form of the raindrop, of the grain of shot, or of the living cell in innumerable simple organisms. It accounts also, as we shall presently see, for many much more complicated forms, manifested under less simple conditions. Let us note in passing that surface tension is a comparatively small force, and is easily measurable. For instance, that between water and air is equivalent to but a few grains per linear inch, or a few grams per meter. But this small tension, when it exists in a curved surface of great curvature, such as that of a minute drop, gives rise to a very great pressure, directed inwards towards the center of curvature. We may easily calculate this pressure, and so satisfy ourselves that when the radius of curvature approaches molecular dimensions, the pressure is of the order of thousands of atmospheres, a conclusion which is supported by other physical considerations. The other phenomena of surface and the other phenomena of surface tension involve the doing of work, and the power to do work is what we call energy. The whole energy of the system is diffused throughout its molecules. As is obvious in such a simple case as we have just considered, but of the whole stock of energy only the part residing at, or very near, the surface normally manifests itself in work. And hence we speak, though the term be open to LPH 368, some objection, of a specific surface energy. Surface energy, and the way it is increased and multiplied by the multiplication of surfaces due to the subdivision of the tissues into cells, is of the highest interest to the physiologist, and even the morphologist cannot pass it by. For the one finds surface energy present, often perhaps paramount, in every cell of the body, and the other may find, if he will only look for it, the form of every solitary cell, like that of any other drop or bubble, related to, if not controlled by, capillarity. The theory of capillarity or surface energy has been set forth with the utmost possible lucidity by Tate and by Clerk Maxwell, on whom the following paragraphs are based. They having based their teaching on that of Gauss, who rested on Laplace, let E be the whole potential energy of a mass M of liquid. Let E subscript 0 be the energy per unit mass of the interior liquid, we may call it the internal energy, of thickness T and density rho E being what we call the surface energy. It is obvious that the total energy consists of the internal plus the surface energy, and that the former is distributed through the whole mass minus its surface layers. That is to say, in mathematical language, E equals open parenthesis M minus S dot sigma T rho, close parenthesis E subscript 0, plus S dot sigma T rho. But this is equivalent to writing equals M E subscript 0, plus dot sigma T rho, open parenthesis E minus E subscript 0, close parenthesis. And this is as much as to say that the total energy of the system may be taken to consist of two portions, one uniform throughout the whole mass, and another which is proportional on the one hand to the amount of surface, and on the other hand to the difference between E and E subscript 0, that is to say to the difference between the unit values of the internal and the surface energy. It was Gauss who first showed how from the mutual attractions between all the particles, we are led to an expression for what we on page 369 of surface energy. Now call the potential energy of the system, and we know as a fundamental theorem of dynamics, as well as of molecular physics, that the potential energy of the system tends to a minimum, and finds in that minimum its stable equilibrium. We see in our last equation that the term ME naught is irreducible, save by a reduction of the mass itself. But the other term may be diminished, 1, by a reduction in the area of surface, S, or 2, by a tendency towards equality of E and E naught. That is to say, by a diminution of the specific surface energy, E. These then are the two methods by which the energy of the system will manifest itself in work. The one, which is much the more important for our purposes, leads always to a diminution of surface, to the so-called principle of minimal areas. The other, which leads to the lowering, under certain circumstances, of surface tension, is the basis of the theory of adsorption, to which we shall have some occasion to refer as a modus operandi in the development of a cell wall, and in a variety of other histological phenomena. In the technical phraseology of the day, the capacity factor is involved in the one case, and the intensity factor in the other, inasmuch as we are concerned with the form of the cell. It is the former which becomes our main postulate, telling us that the energy equations of the surface of a cell, or of the free surfaces of cells in partial contact, or of the partition surfaces of cells in contact with one another, all indicate a minimum of potential energy in the system, by which minimal condition the system is brought, ipso facto, into equilibrium. And we shall not fail to observe with something more than mere historical interest and curiosity how on page 370 the forms of cells. Deeply and intrinsically there enter into this whole class of problems the method of maxima and minima, discovered by Fermat, the loi universelle de repos of Maupertuis. Dans tous les cas d'équilibre dans la statique ordinaire ne sont que des cas particuliers. And the lineae curvae maximi minimiv proprietatibus gaudentes of Euler. By which principles these old natural philosophers explained correctly a multitude of phenomena, and drew the lines whereon the foundations of great part of modern physics are well and truly laid. For that physical laws deal with minima is very generally true, and is highly characteristic of them. The hanging chain so hangs that the height of its center of gravity is a minimum. A ray of light takes the path, however devious, by which the time of its journey is a minimum. Two chemical substances in reaction so behave that their thermodynamic potential tends to a minimum, and so on. The natural philosophers of the 18th century were engrossed in minimal problems, and the differential equations which solve them nowadays are among the most useful and most characteristic equations in mathematical physics. Voici, said Maupertuis, dans un assez petit volume, à quoi je réduis mes ouvrages mathématiques. And when Lagrange, following Euler's lead, conceived the principle of least action, he regarded it not as a metaphysical principle, but as un résultat simple et général de loi de la mécanique. Like Maxwell's equations and other such flashes of genius, it clarifies our knowledge, adds weight to our observations, brings order into our stock and trade of facts. It embodies and extends that law of simplicity which Baroli was the first to lay down. Lex perpetua natura est ut agat minimo laborum deis et modi simplicissimis facilis, page 301. The principle of least action grew up, and grew quickly out of cruder, narrower notions of least time or least space or distance. Nowadays, it is developing into a principle of least action in space-time, which shall still govern and predict the motions of the universe. The infinite perfection of nature is expressed and reflected in these concepts, and Aristotle's great aphorism that nature does nothing in vain lies at the bottom of them all. In all cases where the principle of maxima and minima comes into play, as it conspicuously does in films at rest under surface tension, the configurations so produced are characterized by obvious and remarkable symmetry. Such symmetry is highly characteristic of organic forms, and is rarely absent in living things, save in such few cases as amoeba, where the rest and equilibrium on which symmetry depends are likewise lacking. And if we ask what physical equilibrium has to do with formal symmetry and structural regularity, the reason is not far to seek, nor can it be better put than in these words of Marx. In every symmetrical system, every deformation that tends to destroy the symmetry is complemented by an equal and opposite deformation that tends to restore it. In each deformation, positive and negative work is done. One condition, therefore, though not an absolutely sufficient one, that a maximum or minimum of work corresponds to the form of equilibrium, is thus supplied by symmetry. Regularity is successive symmetry. There is no reason, therefore, to be astonished that the forms of equilibrium are often symmetrical and regular. A crystal is the perfection of symmetry and of regularity. Symmetry is displayed in its external form, and regularity revealed in its internal lattices. Complex and obscure as the attractions, rotations, vibrations, and whatnot within the crystal may be, we rest assured that the configuration, repeated again and again, of page 372, the component atoms is precisely that for which the energy is a minimum. And we recognize that this minimal distribution is of itself tantamount to symmetry and to stability. Moreover, the principle of least action is but a setting of a still more universal law, that the world and all the parts thereof tend ever to pass from less to more probable configurations, in which the physicist recognizes the principle of Clausius, or second law of thermodynamics, and with which the biologist must somehow reconcile the whole theory of evolution. As we proceed in our inquiry, and especially when we approach the subject of tissues or agglomerations of cells, we shall have from time to call in the help of elementary mathematics. But already, with very little mathematical help, we find ourselves in a position to deal with some simple examples of organic forms. When we melt a stick of sealing wax in the flame, surface tension, which was ineffectively present in the solid but finds play in the now fluid mass, rounds off its sharp edges into curves, so striving towards a surface of minimal air. And in like manner, by merely melting the tip of a thin rod of glass, Hooke made the little spherical beads which served him for a microscope. When any drop of protoplasm, either over all its surface or at some free end, as at the extremity of the pseudopodium of an amoeba, is seen likewise to round itself off, that is not an effect of vital contractility, but as Hofmeister showed so long ago as 1867, a simple consequence of surface tension. And almost immediately afterwards, Engelmann argued on the same lines that the forces which cause the contraction of protoplasm in general may be just the same as those which tend to make every non-spherical drop of fluid become spherical. We are not concerned here with the many theories and speculations which would connect the phenomena of surface tension with contractility. Muscular movement or other special physiological function, page 373 of surface action. But we find ample room to trace the operation the same cause in producing, under conditions of rest and equilibrium, certain definite and inevitable forms. It is of great importance to observe that the living cell is one of those cases where the phenomena of surface tension are by no means limited to the outer surface. For within the heterogeneous emulsion of the cell, between the protoplasm and its nuclear and other contents, and in the alveolar network of the cytoplasm itself. So far as that alveolar structure is actually present in life, we have a multitude of interior surfaces, and especially among plants. We may have large internal interfacial contacts between the protoplasm and its included granules, or its vacuoles filled with the cell sap. Here we have a great field for surface action, and so long ago as 1865. Nageli and Schwendener showed that the streaming currents of plant cells might be plausibly explained by this phenomenon. Even 10 years earlier, Weber had remarked upon the resemblance between the protoplasmic streamings and the currents to be observed in certain inanimate drops for which no cause but capillarity could be assigned. What sort of chemical changes lead up to or go hand in hand with the variations of surface tension in a living cell is a vastly important question. It is hardly one for us to deal with, but this at least is clear that the phenomenon is more complicated than its first investigators, such as Butchley and Quincke, ever took it to be, for the lowered surface tension which leads, say, to the throwing out of a pseudopodium is accompanied first by local acidity, then by local adsorption of proteins, lastly and consequently by gelation. And this last is tantamount to the formation of ectoplasm, a step in the direction of encystment. The elementary case of amoeba is nonetheless a complicated one. The amoeboid form is the very negation of rest or of equilibrium. Though page 374, the creature is always moving from one protein configuration to another. Its surface tension is never constant but continually varies from here to there.
Where the surface tension is greater, that portion of the surface will contract into spherical or spheroidal forms. Where it is less, the surface will correspondingly extend. While generally speaking, the surface energy has a minimal value, it is not necessarily constant. It may be diminished by a rise of temperature. It may be altered by contact with adjacent substances, by the transport of constituent materials from the interior to the surface, or again by actual chemical and fermentative change. For within the cell, the surface energies developed about its heterogeneous contents will continually vary as these contents are affected by chemical metabolism. As the colloid materials are broken down and as the particles in suspension are diminished in size, the free surface energy will be increased, but the osmotic energy will be diminished. Thus arise the various fluctuations of surface tension and the various phenomena of amoeboid form and motion, which Bütschli and others have reproduced or imitated by means of the fine emulsions which constitute their artificial amoebae. A multitude of experiments show how extraordinarily delicate is the adjustment of the surface tension forces, and how sensitive they are to the least change of temperature or chemical state. Thus, page 375, the form of amoeba. On a plate which we have warmed at one side, a drop of alcohol runs towards the warm area, a drop of oil away from it, and a drop of water on the glass plate exhibits lively movements when we bring into its neighborhood a heated wire or a glass rod dipped in ether. The watercolor painter makes good use of the surface tension effect of the minutest trace of oxgall. When a plasmodium of aethalium creeps towards a damp spot or a warm spot, or towards substances which happen to be nutritious, and creeps away from solutions of sugar or of salt, we are dealing with phenomena too often ascribed to purposeful action or adaptation, but every one of which can be paralleled by ordinary phenomena of surface tension. The soap bubble itself is never in equilibrium, for the simple reason that its film, like the protoplasm of amoeba or aethalium, is exceedingly heterogeneous. Its surface energies vary from point to point, and chemical changes and changes of temperature increase and magnify the variation. The surface of the bubble is in continual movement. As more concentrated portions of the soapy fluid make their way outwards from the deeper layers, it thins and it thickens. Its colors change, currents are set up in it, and little bubbles glide over it.
It continues in this state of restless movement as its parts strive one with another in their interactions towards unattainable equilibrium.
On reaching a certain tenuity, the bubble bursts, as is bound to happen when the attenuated film has no longer the properties of matter and mass. Page 376, the forms of cells, the film becomes a mere bimolecular, or even a monomolecular layer. And at last we may treat it as a simple surface of discontinuity, so long as the changes due to imperfect equilibrium are taking place very slowly. We speak of the bubble as at rest. It is then, as Willard Gibbs remarks, that the characters of a film are most striking and most sharply defined. So also, and surely not less than the soap bubble, is every cell surface a complex affair. Face and interface have a molecular orientation of their own, depending both on the partition membrane and on the phases on either side. It is a variable orientation, changing at short intervals of space and time. It coincides with inconstant fields of force, electrical and other. It initiates and controls or catalyses chemical reactions of great variety and importance. In short, we acknowledge and confess that in simplifying the surface phenomena of the cell for the time being, and for our purely morphological ends, we may be losing sight or making abstractions of some of its most specific physical and physiological characteristics. In the case of the naked protoplasmic cell, as the amoeboid phase is emphatically a phase of freedom and activity, of unstable equilibrium, of chemical and physiological change. So on the other hand, does the spherical form indicate a phase of stability, of inactivity, of rest? In the one phase, we see unequal surface tensions manifested in the creeping movements of the amoeboid body, in the rounding off of the ends of its pseudopodia, in the flowing out of its substance over a particle of food, and in the current motions in the interior of its mass, till in the alternate phase, when internal homogeneity and equilibrium have been as far as possible attained, and the potential energy of the system is at a minimum, the cell assumes a rounded or spherical form, passes into a state of rest, and, for a reason which we shall presently consider, becomes at the same time insisted, page 377, the form of amoeba. In their amoeboid phase, the various amoebae are just so many varying distributions of surface energy and varying amounts of this potential. An ordinary floating drop is a figure of equilibrium, under conditions of which we shall soon have something to say. And if both it and the fluid in which it floats be homogeneous, it will be a round drop. A figure of revolution, but the least chemical heterogeneity will cause the surface tension to vary here and there, and the drop to change its form accordingly. The little swarm spores of many algae lose their flagella as they settle down, and become mere drops of protoplasm for the time being. They put out pseudopodia, in other words, their outline changes, and presently this amoeboid outline grows out into characteristic lobes or lappets, a sign of more or less symmetrical heterogeneity in the cell substance. In a budding yeast cell, figure 103a, we see a definite and restricted change of surface tension. When a bud appears, whether with or without actual growth by osmosis or otherwise at the mass, it does so because at a certain part of the cell surface the tension has diminished, and the area of that portion expands accordingly. But in turn, the surface tension of the expanded or extruded portion makes itself felt, and the bud rounds itself off into a more or less spherical form. The yeast cell with its bud is a simple example of an important principle. Our whole treatment of cell form in relation to surface tension depends on the fact, which Herrera was the first to give clear expression to, that the incipient cell wall retains with but little impairment the properties of a liquid film, and that the growing cell, in spite of the wall by which it has begun to be surrounded, to page 378, the forms of cells, behaves very much like a fluid drop. So, to a first approximation, even the yeast cell shews by its ovoid and non-spherical form that it has acquired its shape under some influence other than the uniform and symmetrical surface tension, which makes it. This oval or any other asymmetrical form once acquired may be retained by virtue of the solidification and consequent rigidity of the membrane-like wall of the cell. And, unless rigidity ensue, it is plain that such a conformation as that of the yeast cell with its attached bud could not be long retained as a figure of even partial equilibrium. But as a matter of fact, the cell in this case is not in equilibrium at all. It is in process of budding and is slowly altering its shape by rounding off its bud. In like manner, the developing egg, through all its successive phases of form, is never in complete equilibrium, but is constantly responding to slowly changing conditions by phases of partial, transitory, unstable, and conditional equilibrium. There are innumerable solitary plant cells and unicellular organisms in general, which, like the yeast cell, do not correspond to any of the simple forms which may be generated under the influence of simple and homogeneous surface tension. And in many cases, these forms, which we should expect to be unstable and transitory, have become fixed and stable by reason of some comparatively sudden solidification of the envelope. This is the case, for instance, in the more complicated forms of diatoms or of desmides, where we are dealing in a less striking but even more curious way than in the budding yeast cell, not with one simple acto-F formation, but with a complicated result of successive stages of localized growth, interrupted by phases of partial consolidation. The original cell has acquired a certain form, and then, under altering conditions and new distributions of energy, has thickened here or weakened there, and has grown out or tended, as it were, to branch at particular points. We can often trace in each particular stage of growth, or at each particular temporary growing point, the laws of surface tension manifesting themselves in what is for the time being a fluid surface. Nay, more. Even in the adult and completed structure, we have little difficulty in tracing and recognizing, for instance, in the outline of such a desmid as euastrum, the rounded lobes which have successively grown or flowed out from the original rounded and page 379 of liquid films. Flattened cell, what we see in a many-chambered foraminifer, such as Globigerina or Rotalia, is the same thing, save that the stages are more separate and distinct, and the whole is carried out to greater completeness and perfection. The little organism as a whole is not a figure of equilibrium nor of minimal area, but each new bud or separate chamber is such a figure, conditioned by the forces of surface tension, and superposed upon the complex aggregate of similar bubbles,
after these latter have become consolidated one by one into a rigid system. Let us now make some inquiry into the forms which a fluid surface can assume under the mere influence of surface tension. In doing so, we are limited to conditions under which other forces are relatively unimportant. That is to say, where the surface energy is a considerable fraction of the whole energy of the system. And in general, this will be the case when we are dealing with portions of liquid so small that their dimensions come within or near to what we have called the molecular range, or more generally, in which the specific surface is large. In other words, it is the small or minute organisms or small cellular elements of larger organisms whose forms will be governed by surface tension, while the forms of the larger are non-molecular forces. A large surface of water sets itself level because here gravity is predominant, but the surface of water in a narrow tube is curved, for the reason that we are here dealing with particles which lie within the range of each other's molecular force. The like is the case with the cell surfaces and cell partitions which we are about to study, and the effect of gravity will be especially counteracted and concealed when the object is immersed in a liquid of nearly its own density. We have already learned as a fundamental law of capillarity that a liquid film in equilibrium assumes a form which gives it a minimal area under the conditions to which it is subject. These conditions include 1. The form of the boundary, if such exists, and 2. The pressure, if any, to which the film is subject, which pressure is closely related to the volume of air or of liquid that the film, if it be a closed one, may have to contain. In the simplest of cases, as when we take up a soap film on a plain wire ring, the film is exposed to equal atmospheric pressure on both sides. And it'll be page 380, the forms of cells obviously has its minimal area in the form of a plane. So long as our wire ring lies in one plane, however irregular in outline, the film stretched across it will still be in a plane. But if we bend the ring so that it lies no longer in a plane, then our film will become curved into a surface which may be extremely complicated, but is still the smallest possible surface which can be drawn continuously across the uneven boundary. The question of pressure involves not only external pressures acting on the film, but also that which the film itself is capable of exerting. For we have seen that the film is always contracting to the utmost, and when the film is curved, this leads to a pressure directed inwards, perpendicular, that is to say, to the surface of the film. In the case of the soap bubble, the uniform contraction of whose surface has led to its spherical form, this pressure is balanced by the pressure of the air within. And if an outlet be given for this air, then the bubble contracts with perceptible force until it stretches across the mouth of the tube, for instance, across the mouth of the pipe through which we have blown the bubble. A precisely similar pressure, directed inwards, is exercised by the surface layer of a drop of water or globule of mercury, or by the surface pellicle on a portion or drop of protoplasm. Only we must always remember that in the soap bubble, or the bubble which a glass blower blows, there is a twofold pressure as compared with that which the surface film exercises on the drop of liquid of which it is a part. For the bubble consists, unless it be so thin as to consist of a mere layer of molecules, of a liquid layer with a free surface within and another without. And each of these two surfaces exercises dependent and co-equal tension and its corresponding pressure. If we stretch a tape upon a flat table, whatever be the tension of the tape, it obviously exercises no pressure upon the table below. But if we stretch it over a curved surface, a cylinder for instance, it does exercise a downward pressure. And the more curved the surface, the greater is this pressure. That is to say, the greater is this share of the entire force of tension, which is resolved in the down page 381 of liquid films. In mathematical language, the pressure P varies directly as the tension T and inversely as the radius of curvature. R, that is to say, P equals T divided by R per unit of surface. If instead of a cylinder, whose curvature lies only in one direction, we take a case of curvature in two dimensions, as for instance a sphere, then the effects of these two curvatures must be added together to give the resulting pressure P, which becomes equal to T over R plus T over R prime, or P equals T times 1 over R plus 1 over R prime. And if in addition to the pressure P, which is due to surface tension, we have to take into account other pressures, P prime, P double prime, etc., due to gravity or other forces,
then we may say that the total pressure P equals P prime plus B double prime plus T times 1 over R plus 1 over prime prime. We may have to take account of the extraneous pressures in some cases, as when we come to speak of the shape of a bird's egg, but in this first part of our subject, we are able for the most part to neglect them. Our equation is an equation of equilibrium. The resistance to compression, the pressure outwards of our fluid mass, is a constant quantity P. The pressure inwards, T times 1 over R plus 1 over R prime, is also constant. And if the surface, unlike that of the mobile amoeba, be homogeneous, so that T is everywhere equal, it follows that 1 over R plus 1 over R prime equals C, a constant throughout the whole surface in question. Now, equilibrium is reached after the surface contraction has done its utmost. That is to say, when it has reduced the surface to the least possible area. So we arrive at the conclusion from the physical side that a surface such that 1 over R plus 1 over R prime equals C, in other words, a surface which has the same mean curvature at all points, is equivalent to a surface of minimal area for the volume enclosed. Page 382. And to the same conclusion, we may also come by ways purely mathematical. The plane and the sphere are two obvious examples of such surfaces, for in both the radius of curvature is everywhere constant. From the fact that we may extend a soap film across any ring of wire, however fantastically the wire be bent, we see that there is no end to the number of surfaces of minimal area, which may be constructed or imagined. While some of these are very complicated indeed, others, such as a spiral or helicoid screw, are relatively simple. But if we limit ourselves to surfaces of revolution, that is to say, to surfaces symmetrical about an axis, we find, as Plateau was the first to show, that those which meet the case are few in number. They are 6 in all, namely the plane, the sphere, the cylinder, the catenoid, the unduloid, and a curious surface which Plateau called the nodoid, figure 104 roulettes of the conic sections. These several surfaces are all closely related, and the passage from one to another is generally easy. Their mathematical interrelation is expressed by the fact, first shown by Delaunay in 1841, that the plane curves by whose revolution they are generated are themselves generated as roulettes of the conic sections. Let us imagine a straight line or axis on which a circle, ellipse, or other conic section rolls. The focus of the conic section will describe a line in some relation to the fixed axis, an Edith line, or roulette when we rotate it around the axis. We'll describe in space one or another of the 6 surfaces of revolution of which we are speaking. If we imagine an ellipse so to roll on a baseline, either of its foci will describe a sinuous or wavy line, figure 104b. At a distance, page 383, of minimal surfaces, alternately maximal and minimal from the axis. This wavy name, by rotation about the axis, becomes the meridional nay of the surface, which we call the unduloid. And the more unequal the two axes are of our ellipse, the more pronounced will be the undulating sinuosity of the roulette. If the two axes be equal, then our ellipse becomes a circle. The path described by its ruling center is a straight line parallel to the axis. A, in the mode of revolution generated therefrom, will be a cylinder. In other words, the cylinder is a miting case of the unduloid. If one axis of our ellipse vanish, while the other remains of finite length, then the ellipse is reduced to a straight line with its foci at the two ends, and its roulette will appear as a succession of semicircles touching one another upon the axis, C. The solid of revolution will be a series of equal spheres. If, as before, one axis of the ellipse vanish, but the other be infinitely long, then the roulette described by the focus of this ellipse will be a circular arc at an infinite distance, i.e., it will be a straight line normal to the axis, and the surface of revolution traced by this straightly turning about the axis will be a plane. If we imagine one focus of our ellipse to remain at a given distance from the axis, but the other to become infinitely remote, that is tantamount to saying that the ellipse becomes transformed into a parabola, and by the rolling of this curve along the axis, there is described a catenary. Lastly, but this is more difficult to imagine, we have the case of the hyperbola. We cannot well imagine the hyperbola rolling upon a fixed straight line, so that its focus shall describe a continuous curve. But let us suppose that the fixed knee is, to begin with,
asymptotic to one branch of the hyperbola, and that the rlung proceeds until the ne is now asymptotic to the other branch. That is to say, touching it at an infinite distance. There will then be mathematical continuity if we recommence rolling with this second branch, and so in turn with the other when each has run its course. We shall see on reflection that the line traced by one and the same focus will be an elastic curve, describing a succession of kinks or knots, and the solid of revolution described by this meridional line about the axis is the so-called nodoid. The physical transition of one of these surfaces into another can, page 384, the forms of cells, be experimentally illustrated by means of soap bubbles, or better still, after another method of plateaus, by means of a large globule of oil-supported W-hen necessary by wire rings and lying in a fluid of specific gravity equal to its own. To prepare a mixture of alcohol and water of a density precisely equal to that of the oil globule is a troublesome matter, and a method devised by Mr. C.R. Darling is a great improvement on plateaus. Mr. Darling used the oily liquid orthotoluidine, which does not mix with water, has a beautiful and conspicuous red color, and has precisely the same density as water, when both are kept at a temperature of 24 degrees Celsius. We have therefore only to run the liquid into water at this temperature in order to produce beautifully spherical drops of any required size. And by adding a little salt to the lower layers of water, the drop may be made to rest or float upon the denser liquid. Figure 105. We have seen that the soap bubble, spherical to begin with, is transformed into a plane when we release its internal pressure and let the film shrink back upon the orifice of the pipe. If we blow a bubble and then catch it up on a second pipe, so that it stretches between, we may draw the two pipes apart with the result that the spheroidal surface will be gradually flattened in a longitudinal direction, and the bubble will be transformed into a cylinder. But if we draw the pipes yet farther apart, the cylinder narrows in the middle into a sort of hourglass form, the increasing curvature of its transverse section being balanced by a gradually increasing negative curvature in the longitudinal section. The cylinder has, in turn, been converted into an unduloid. When we hold a soft glass tube in the flame and draw it out, we are in the same identical fashion converting a cylinder into an unduloid, figure 105. When, on the other hand, we stop the end and blow, we again convert the cylinder into an unduloid, B, but into one which is now positively, while the former was negatively curved. The two figures are page 385. Essentially the same, save that the two halves of the one change places in the other. That's fuse. Cylinders and unduloids are the commonest occurrence among the forms of small unicellular organisms, or of individual cells in the simpler aggregates, and that in the processes of growth, reproduction and development transitions are frequent from one of these forms to another, is obvious to the naturalist, and we shall deal presently with a few of these phenomena. But before we go further in this inquiry, we must consider, to some small extent at least, the curvatures of the 6 different surfaces, so far as to determine what modification is required, in each case, of the general equation which applies to them all. We shall find that, with this question is closely connected the question of the pressures exercised by or impinging on the film, and also the very important question of the limiting conditions, which, from the nature of the case, set bounds to the extension of certain of the figures. The whole subject is mathematical, and we shall only deal with it in the most elementary way. We have seen that, in our general formula, the expression 1 over r plus 1 over r prime equals c, a constant, and that this is, in all cases, the condition of our surface being one of minimal area. That is to say, it is always true for one and all the 6 surfaces which we have to consider. But the constant c may have any value, positive, negative, or nil. In the case of the plane, where r and r prime are both infinite, 1 over r plus 1 over r prime equals 0. The expression therefore vanishes, and our dynamical equation of equals p, in short, we can only have a plane film. Or we shall only find a plane surface in our cell when on either side thereof we have equal pressures or no pressure at all. A simple case is the plane partition between 2 equal and similar cells, as in a filament of spirogyra. In the sphere, the radii are all equal. R equals r prime. They are also positive, and t times the quantity 1 over r plus 1 over r prime.
Or 2T over R is a positive quantity involving a constant positive pressure P. On the other side of the equation, in the cylinder, one radius of curvature has the finite and positive value R, but the other is infinite. Our formula becomes to over R to E page 386, the forms of cells, which corresponds a positive pressure P supplied by the surface tension, as in the case of the sphere, but evidently of just half the magnitude. In plane, sphere, and cylinder, the two principal curvatures are constant separately and together, but in the unduloid, the curvatures change from one point to another. At the middle of one of the swollen beads or bubbles, the curvatures are both positive. The expression, open parenthesis, 1 over R plus 1 over R prime, close parenthesis, is therefore positive, and it is also finite. The film exercises, like the cylinder, a positive pressure inwards to be compensated by an equivalent outward pressure from within. Between two adjacent beads at the middle of one of the narrow necks, there is obviously a much stronger curvature in the transverse direction, but the total pressure is unchanged, and we now see that a negative curvature along the unduloid balances the increased curvature in the transverse direction. The sum of the two must remain positive as well as constant. Therefore, the convex or positive curvature must always be greater than the concave or negative curvature at the same point. And this is plainly the case in our figure of the unduloid. The catenoid, in this respect, a limiting case of the unduloid, has its curvature in one direction equal and opposite to its curvature in the other, this property holding good for all points of the surface. R equals minus a prime, and the expression becomes open parenthesis 1 over R plus 1 over R prime, close parenthesis, equals open parenthesis 1 over R minus 1 over close parenthesis equals 0. That is to say, the mean curvature is 0, and the catenoid, like the plane itself, has no curvature and exerts no pressure. None of the other surfaces save these two share this remarkable property. And it follows that we may have, at times, the plane and the catenoid coexisting as parts of one and the same boundary system, just as the cylinder or the unduloid may be capped by portions of spheres. It follows also that if we stretch a soap film between two rings, and so form an annular surface open at both ends, that surface is a catenoid, the simplest case being when the rings are parallel and normal to the axis of the figure. Page 387 of Figures of Equilibrium. The nodoid is like the unduloid, a continuous curve which keeps altering its curvature as it alters its distance from the axis. But in this case, the resultant pressure inwards is negative instead of positive. But this curve is a complicated one, and its full mathematical treatment is too hard for us. In one of Plateau's experiments, a bubble of oil, protected from gravity by a fluid of equal density to its own, is balanced between annuli, and by adjusting the distance apart of these, it may be brought to assume the form of Fig. 106, that is to say, of a cylinder with spherical ends. There is then everywhere a pressure inwards on the fluid contents of the bubble, a pressure due to the convexity of the surface film. Figure 106, Figure 107, A and B. This cylinder may be converted into an unduloid, either by drawing the rings farther apart or by abstracting some of the oil, until at length rupture ensues, and the cylinder breaks up into two spherical drops. Or again, if the surrounding liquid be made ever so little heavier or lighter than that which constitutes the drop, then gravity comes into play. The conditions of equilibrium are modified accordingly, and the cylinder becomes part of an unduloid, with its dilated portion above or below, as the case may be, Figure 107. In all cases, the unduloid, like the original cylinder, is capped by spherical ends, the sign and the consequence of a positive pressure produced by the curved walls of the unduloid. But if our initial cylinder, instead of being tall, be a flat or dumpy one, page 388, the forms of cells, with certain definite relations of height to breadth, then new phenomena may occur. For now, if oil be cautiously withdrawn from the mass by help of a small syringe, the cylinder may be made to flatten down so that its upper and lower surfaces become plane, which is of itself a sufficient indication that the pressure inwards is now nil. But at the very moment when the upper and lower surfaces become plane, it will be found that the sides curve inwards in the fashion shown in Fig. This figure is a catenoid, which, as we have seen, is, like the plane itself, a surface exercising no pressure,
and which therefore may coexist with the plane as part of one and the same system. We may continue to withdraw more oil from our bubble, drop by drop. And now the upper and lower surfaces dimple down into concave portions of spheres as the result of the negative internal pressure. And thereupon the peripheral catenoid surface alters its form, perhaps on this small scale, imperceptibly, and becomes a portion of a nodoid. It represents, in fact, that portion of the nodoid which in Fig 109 lies between such points as OP. While it is easy to draw the outline or meridional section of the nodoid, it is obvious that the solid of revolution to be derived from it can never be realized in its entirety, for one part of the solid figure would cut or entangle with another. All that we can ever do accordingly is to realize isolated portions of the nodoid. View page 389 VV of Figures of Equilibrium 375. In all these cases, the ring or annulus is not merely a means of mechanical restraint. Controlling the form of the drop or bubble, it also marks the boundary, or locus of discontinuity, between one surface and another. If, in a sequel to the preceding experiment of plateaus, we use solid disk instead of a newly, we may exert pressure on our oil globule as we exerted traction before. We begin again by adjusting the pressure of these disks so that the oil assumes the form of a cylinder. Our disks, that is to say, are adjusted to exercise a mechanical pressure just equal to what in the former case was supplied by the surface tension of the spherical caps or ends of the bubble. If we now increase the pressure slightly, the peripheral walls become convexly curved, exercising a precisely corresponding pressure. The form assumed by the sides of our figure is now that of a portion of an unduloid. If we increase the pressure, the peripheral surface of oil will bulge out more and more, and will presently constitute a portion of a sphere. But we may continue the process yet further, and find within certain limits the system remaining perfectly stable. What is this new curved surface which has arisen out of the sphere as the latter was produced from the unduloid? It is no other than a portion of a nodoid, that part which in Fig 109 lies between M and N, but this surface, which is concave in both directions towards the surface of the oil within, is exerting a pressure upon the latter, just as did the sphere out of which a moment ago it was transformed. And we had just stated in considering the previous experiment that the pressure inwards exerted by the nodoid was a negative one. The explanation of this seeming discrepancy lies in the simple fact that if we follow the outline of our nodoid curve in Fig 109 from OP, the surface concerned in the former case to man, that concerned in the present, we shall see that in the two experiments, the surface of the Euclid is not the same, but lies on the positive side of the curve in the one case, and on the negative side in the O there. These capillary surfaces of plateaus form a beautiful example of the materialization of mathematical law. Theory leads to certain equations which determine the position of points in a system, and these points we may then plot as curves on a coordinate diagram. But a drop or a bubble may realize in an instant the D page 390, the whole result of our calculations, and materialize our whole apparatus of curves. Such a case is what Bacon calls a collective instance, bearing witness to the fact that one common law is obeyed by every point or particle of the system, where the underlying equations are unknown to us, as happens in so many natural configurations. We may still rest assured that kindred mathematical laws are being automatically followed and rigorously obeyed, and sometimes half revealed. Of all the surfaces which we have been describing, the sphere is the only one which can enclose space of itself. The others can only help to do so in combination with one another or with the sphere. Moreover, the sphere is also, of all possible figures, that which encloses the greatest volume with the least area of surface. It is strictly and absolutely the surface of minimal area, and it is ipso facto the form which will be assumed by a unicellular organism, just as by a raindrop, if it be practically homogeneous, and if, like Orbulina floating in the ocean, its surroundings be likewise homogeneous, and its field of force symmetrical. It is only relatively speaking that the rest of these configurations are surfaces minimi irae, for they are so under conditions which involve various pressures or restraints. Such restraints are imposed by the pipe or annulus which supports and confines our oil globule or soap bubble, and in the case of the organic cell,
Similar restraints are supplied by solidifications partial or complete, or other modifications local or general of the cell surface or cell wall. One thing we must not fail to bear in mind, in the case of the soap bubble, we look for stability or instability, equilibrium or non-equilibrium, in its several configurations. But the living cell is seldom in equilibrium. It is continually using or expending energy, and this ceaseless flow of energy gives rise to a steady state taking the place of and simulating equilibrium. In like manner, the U page 39101 of Figures of Equilibrium, the hardly changing outline of a jet or waterfall is but in pseudo-equilibrium. It is in a steady state, dynamically speaking. Many puzzling and apparent paradoxes of physiology, such to take a single instance as the maintenance of a constant osmotic pressure on either side of a cell membrane, are accounted for by the fact that energy is being spent and work done, and a steady state or pseudo-equilibrium maintained thereby. Before we pass to biological illustrations of our surface tension figures, we have still another matter to deal with. We have seen from our description of two of Plateau's classical experiment S that at some particular point one type of surface gives place to another. And again, we know that when we draw out our soap bubble into a cylinder and then beyond, there comes a certain point at which the bubble breaks in two and leaves us with two bubbles of which each is a sphere or a portion of a sphere. In short, there are certain limits to the dimensions of our figures, within which limits equilibrium is stable, but at which it becomes unstable and beyond which it breaks down. Moreover, in our composite surfaces, when the cylinder, for instance, is capped by two spherical cups or lenticular discs, there are well-defined ratios which regulate their respective curvatures and their respective dimensions. These two matters we may deal with together. Let us imagine a liquid drop, which in appropriate conditions has been made to assume the form of a cylinder. We have already seen that its ends will be capped by portions of spheres. Since one and the same liquid film covers the sides and ends of the drop, or since one and the same delicate membrane encloses the sides and ends of the cell, we assume the surface tension, T, to be everywhere identical, and it follows, since the internal fluid pressure is also everywhere identical, that the expression open parenthesis 1 over r plus 1 over r prime close parenthesis for the cylinder is equal to the corresponding expression, which we may call open parenthesis 1 over r plus 1 over r prime close parenthesis in the case of the terminal spheres. But in the figure 110 page 392, the forms of cells, cylinder 1 over r prime equals 0, and in the sphere 1 over r equals 1 over r prime. Therefore, our relation of equality becomes 1 over r equals 2 over r, or r equals 2r, which means that the sphere in question has just twice the radius of the cylinder of which it forms a cap. And if OB, the radius of the sphere, be equal to twice the radius O of the cylinder, it follows that the angle AOB is an angle of 60 degrees, and BOC is also an angle of 60 degrees. That is to say, the arc BC is equal to 1/3 pi. In other words, the spherical disk, which, under the given conditions, caps our cylinder, is not a portion taken at haphazard, but is neither more nor less than that portion of a sphere which is subtended by a cone of 60 degrees. Moreover, it is plain that the height of the spherical cap DE equals OB minus AB equals r times 2 minus square root of 3 equals 0.27 r, where r is the radius of our cylinder, or 1/2 the radius of our spherical cap. In other words, the normal height of the spherical cap over the end of the cylindrical cell is just a very little more than 1/8 of the diameter of the cylinder, or of the radius of the sphere. And these are the proportions which we recognize more or less under normal circumstances. In such a case as the cylindrical cell of Spiragira, when one end is free and capped by a portion of a sphere. Among the many theoretical discoveries which we owe to Plateau, one to which we have just referred is of peculiar importance, namely that, with the exception of the sphere and the plane, the surfaces with which we have been dealing are only in complete equilibrium within certain dimensional limits, or in other words, have a certain definite limit of stability. Only the plane and the sphere, or any portion of a sphere, are perfectly stable because they are perfectly symmetrical figures. Perhaps it were better to say that their symmetry is such that any small disturbance will probably readjust itself,
and leave the plane or spherical surface as it was before.
While in the other configurations, the chances are that a disturbance once set up will travel in one direction or another, increasing as it goes. For equilibrium and probability, as Boltzmann told us, are nearly allied.
Page 393. For experimental demonstration, the case of the cylinder is the simplest. If we construct a liquid cylinder, either by drawing out a bubble or by supporting a globule of oil between two rings, the experiment proceeds easily until the length of the cylinder becomes just about 3 times as great as its diameter.
But soon afterwards, instability begins, and the cylinder alters its form. It narrows at Fig. 111. The waste, so passing into an unduloid, and the deformation progresses quickly until our cylinder breaks in two, and its two halves become portions of spheres. This physical change of one surface into another corresponds to what the mathematicians call a discontinuous solution of a problem of minima. The theoretical limit of stability, according to Plateau, is when the length of the cylinder is equal to its circumference. That is to say, when LG or when the ratio of length to diameter is represented by an n. The fact is that any small disturbance takes the form of a wave and travels along the cylinder. Short waves do not affect the stability of the system, but waves whose length exceeds that of the circumference tend to grow in amplitude, until, contracting here, expanding there, the cylinder turns into a pronounced unduloid and soon breaks into 2 parts or more. Thus, the cylinder is a D page 394, the forms of cells. Stable figure until it becomes longer than its own circumference, and then the risk of rupture may be said to begin. But Rayleigh showed that still longer waves, leading to still greater instability, are needed to break down material resistance. For, as Plateau knew well, his was a theoretical result, to be departed from under material conditions. It is affected largely by viscosity, and, as in the case of a flowing cylinder or jet, by inertia. When inertia plays a leading part, viscosity being small, a node of maximum instability corresponds to nearly half as much again as in the simple or theoretical case. And this result is very near to what Plateau himself had deduced from Sauert's experiments on jets of water. When the fluid is external, as when the cylinder is of air, the wavelength of maximal instability is longer still. Lastly, when viscosity is very large and becomes paramount, then the wavelength between regions of maximal instability may become very long indeed. So that, as Rayleigh put it, long viscid threads do not tend to divide themselves into drops at mutual distances comparable with the diameter of the cylinder, but rather to give way by attenuation at few and distant places. It is this that renders possible the making of long glass tubes, or the spinning of threads of viscose and like materials. But while these latter preserve their continuity, the principle of Plateau tends to give them something of a wavy, unduloid surface, to the great enhancement of their beauty. We are prepared, then, to find that such cylinders and unduloids as occur in organic nature seldom approach in regularity to those which theory prescribes, or a soap film may be made to show, but rather exhibit all manner of gradations, from something exquisitely neat and regular to a coarse and distant approximation to the ideal thing. The unduloid has certain peculiar properties as regards its limitations of stability, but we need mention 2 facts only. 1, that when the unduloid which we produce with our soap bubble or our T page 395 of figures of equilibrium, oil globule, consists of the figure containing a complete constriction, then it has somewhat wide limits of stability. But 2, if it contained the swollen portion, then equilibrium is limited to the case of the figure consisting of one complete unduloid, no less nor more. That is to say, when the ends of the figure are constituted by the narrowest portions, and its middle by the widest portion of the entire curve. The theoretical proof of this is difficult, but if we take the proof for granted, the fact itself will serve to throw light on what we have learned regarding the stability of the cylinder. 4. When we remember that the meridional section of our unduloid is generated by the rolling of an ellipse upon a straight line in its own plane, we easily see that the length of the entire unduloid is equal to the circumference of the generating ellipse. As the unduloid becomes less and less sinuous in outline, it approaches, and in time reaches the form of the cylinder as a limiting case. And pari passu, the ellipse which generated it passes into a circle as its foci come closer and closer together. The cylinder of a length equal to the circumference of its generating circle is homologous to an undulatoid whose length is equal to the circumference of its generating ellipse. And this is just what we recognize as constituting one complete segment of the undulatoid. For the same reason, it is the very standby of the glassblower, whose flasks and bottles are, of necessity, undulatoids. The blown glass bottle is a true undulatoid, and the potter's vase a close approach to an undulatoid. But the alabaster bottle turned on the lathe is another story. It may be an imitation or a reminiscence of the potter's or the glassblower's work, but it is no undulatoid nor any surface of minimal area at all. The catenoid, as we have seen, is a surface of zero pressure, and as such is unlikely to form part, unless momentarily, a cell. It forms a limiting case between undulatoid and nodoid, and were it realized, it would seldom be visibly different from the other two. In Trichodina pediculus, a minute infusorian para, page 396, the forms of cells. In the site of the freshwater polyp, we have a circular disc bounded apparently by two parallel rings of cilia, with a pulley-like groove between. The groove looks very like that catenoid surface which we have produced from two parallel and opposite annuli, and the fact that the lower surface of the little creature is practically plane, where it creeps over the smooth body of the hydra. Looks like confirming the catenoid analogy, but the upper surface of the infusorian, with its ciliated gullet, gives no assurance of a zero pressure, and we must take it that the equatorial groove of Trichodina resembles or approaches, but is not mathematically identical with, a catenoid surface. Figure 112, Trichodina pediculus. While those figures of equilibrium which are also surfaces of revolution are only 6 in number, there is an infinite number of other figures of equilibrium, that is to say, of surfaces of constant mean curvature, which are not surfaces of revolution. And it can be shown mathematically that any given contour can be occupied by a finite portion of some such surface in stable equilibrium. The experimental verification of this theorem lies in the simple fact, already noted, that however we bend a wire into a closed curve, plane or not plane, we may always fill the entire area with a continuous film. No more interesting problem has ever been propounded to mathematicians as the outcome of experiment than the general problem so to describe a minimal surface passing through a closed contour, and no complete solution, no general method of approach has yet been discovered of the regular figures of equilibrium, or surfaces of constant mean curvature, apart from the surfaces of revolution which we have discussed. The helicoid spiral is the most interesting to the biologist. PR 97 V of figures of equilibrium 383. This is a helicoid generated by a straight line perpendicular to an axis, about which it turns at a uniform rate, while at the same time it slides also uniformly along this same axis. At any point in this surface, the curvatures are equal and of opposite sign, and the sum of the curvatures is accordingly nil. Among what are called ruled surfaces, or surfaces capable of being defined by a system of stretch strings, the plane and the are the only two whose mean curvature is null, while the cinder is the only one whose curvature is finite and constant, as the simplest of helicoids corresponds in 3 dimensions to what in 2 dimensions is merely a plane, the latter being generated by the rotation of a straight line about an axis without the superadded gliding motion which generates the helicoid. So there are other and much more complicated helicoids which correspond to the sphere, the undulatoid, and the rest of our figures of revolution, the generating planes of these latter being supposed to wind spirally about an axis. In the case of the cinder, it is obvious that the resulting figure is indistinguishable from the cinder itself. In the case of the undulatoid, we obtain a grooved spiral, and we meet with something very like it in nature, for instance, in spirochaetes, Photogracilis, etc. But in point of fact, the screw motion given to an undulatoid or catenary curve fails to give a minimal screw surface, as we might have expected it to do. The foregoing considerations deal with a small part only of the theory of surface tension, or capillarity, with that part, namely, which relates to the surfaces capable of subsisting in equilibrium under the action of that force, either of itself or subject to certain simple constraints. And as yet we have limited ourselves to the case of a single surface, or of a single drop or bubble,
leaving to another occasion a discussion of the forms assumed when such drops or vesicles meet and combine together.
What we have said may help us to understand the form of a cell. Considered, as with certain imitations, we may legitimately consider it as a quid drop or liquid vesicle. Conformation of a tissue or cell aggregate must be dealt with in the light of another series of theoretical considerations. In both cases, we can do no more than touch on the fringe of a large and difficult subject. There are many forms, or rather surfaces such, that through every point there runs a straight line which lies wholly in the surface. Page 398, capable of realization under surface tension, and many of them doubtless to be recognized among organisms, which we cannot deal with in this elementary account. The subject is a very general one. It is, in its essence, more mathematical than physical. It is part of the mathematics of surfaces, and only comes into relation with surface tension, because this physical phenomenon illustrates and exemplifies in a concrete way the simple and symmetrical conditions with which the mathematical theory is capable of dealing. And before we pass to illustrate the physical phenomena by biological examples, we must repeat that the simple physical conditions which we presuppose will never be wholly realized in the organic cell. Its substance will never be a perfect fluid, and hence equilibrium will be slowly reached. Its surface will seldom be perfectly homogeneous, and therefore equilibrium will seldom be perfectly attained. It will very often or generally be the seat of other forces, symmetrical or unsymmetrical, and all these causes will more or less perturb the surface tension effects. But we shall find that, on the whole, these effects of surface tension, though modified, are not obliterated, nor even masked. And accordingly, the phenomena to which I have devoted the foregoing pages will be found manifestly recurring and repeating themselves among the phenomena of the organic cell. In a spider's web, we find exemplified several of the principles of surface tension, which we have now explained. The thread is spun out of a glandular secretion, which issues from the spider's body as a semi-fluid cylinder, the force of expulsion giving it its length, and that of surface tension giving it its circular section. It is too viscid and too soon hardened on exposure to the air to break up into drops or spherules, but it is otherwise with another sticky secretion, which, coming from another gland, is simultaneously poured over the U-page 399 slacker cross threads as they issue to form the spiral portion of the web. This latter secretion is more fluid than the first, and only dries up after several hours. By capillarity, it wets the thread, spreading over it in an even film or liquid cylinder. As such, it has its limits of stability and tends to disrupt at points more distant than the theoretical wavelength, owing to the imperfect fluidity of the viscous film, and still more to the frictional drag of the inner thread with which it is in contact. Save for this qualification, the cylinder disrupts in the usual manner, passing first into the wavy outline of an unduloid, whose swollen internodes swell more and more till the necks between them break asunder, and leave a row of spherical drops or beads, strung like dewdrops at regular intervals along the thread. If we try to varnish a thin, taut wire, we produce automatically the same identical result. Unless our varnish be such as to dry almost instantaneously, it gathers into beads, and do what we will, we fail to spread it smooth. It follows that, according to the drying qualities of our varnish, the process may stop at any point short of the formation of perfect spherules. And as our final stage, we may only obtain half-formed beads or the wavy outlines of an unduloid. The beads may be helped to form by jerking the stretched thread, and so disturbing the unstable equilibrium of the viscid cylinder. This the spider has been said to do, but Dr. G.T. Bennett assures me that she does nothing of the kind. She only draws her thread out a little, and leaves it a trifle slack. If the gum should break into droplets, well and good be it, it matters little. The web with its sticky threads is not improved thereby. Another curious phenomenon here presents itself. In Plateau's experimental separation of a cylinder of oil into two spherical halves, it was noticed that when contact was nearly broken, that is to say, when the narrow neck of the unduloid had become very thin, the two spherical bulli, instead of absorbing the fluid out of the narrow neck into themselves, as they had done with the preceding portion, drew out this small remaining part of the U page 400 to 386, the forms of cells etched the liquid into a thin thread as they completed their spherical F-worm and receded from one another. The reason being that, after the thread or neck has reached a certain tenuity, internal friction prevents or retards a rapid exit of the fluid from the thread to the adjacent sphere wall. It is for the same reason that we are able to draw a glass rod or tube, which we have heated in the middle, into a long and uniform cinder or thread by quickly separating the two ends. But in the case of the glass rod, the long, thin thread quickly cools and solidifies, while in the ordinary separation of a liquid cylinder, the corresponding intermediate cylinder remains liquid, and therefore, H key any other liquid cylinder. It is liable to Fig. 113. Dewdrops on a spider's web. Break up provided that its dimensions exceed the limit of stability, and its length is generally such that it breaks at 2 points, thus leaving 2 terminal portions continuous and confluent with the spheres, and 1 median portion, WA, resolves itself into a tiny spherical drop, midway between the original and larger 2. Occasionally, the same process of formation of a connecting thread repeats itself a second time between the small intermediate spheral and the large spheres, and in this case we obtain 2 additional spherals, still smaller in size, and lying one on either side of our first little one. This whole phenomenon of equal and regularly interspaced beads, often with little beads regularly interspaced between the larger ones, and now and then with a third order of still smaller beads regularly intercalated, may be easily observed in a spider's web, such as that of Epeira, very often with beautiful regularity, sometimes interrupted and disturbed by a one of homogeneity in the secreted fluid. And the same phenomenon is EPH 401, repeated on a grosser scale when the web is bespangled with dew, and its threads bestrung with pearls innumerable. To the older naturalists, these regularly arranged and beautifully formed globules on the spider's web were a frequent source of wonderment. Blackwall, counting some 20 globules in 1/10 of an inch, calculated that a large garden spider's web should comprise about 120,000 globules. The net was spun and finished in about 40 minutes, and Blackwall was filled with admiration of the skill and quickness with which the spider manufactured these little beads. And no wonder, for according to the above estimate, they had to be made at the rate of about 50 per second. Here we see exemplified what Plateau told us of the law of minimal areas transforming the cylinder into the unduloid and disrupting it into spheres. Figure 114, root hair of Trionea in glycerine. After Berthold, into spheres. The little delicate beads, which stud the long, thin pseudopodia of a foraminifer, such as Gromia, or which appear in like manner on the film of protoplasm coating the long radiating spicules of Globigerina, represent an identical phenomenon. Indeed, we may study in a protoplasmic filament the whole process of formation of such beads. If we squeeze out on a slide the viscid contents of a mistletoe berry, the long sticky threads into which the substance runs show the whole phenomenon particularly well. True, many long cylindrical cells, such as are common in plants, show no sign of beating or disruption. But here the cell walls are never fluid but harden as they grow, and the protoplasm within is kept in place and shape by its contact with the cell wall. It was noticed many years ago by Hofmeister, and afterwards explained by Berthold, that if we dip the long root hairs of certain water plants, such as Hydrocharis or Trionea, in a denser fluid, a little sugar solution or page 402, the forms of cells. Dilute glycerine. The cell sap tends to diffuse outwards, the protoplasm parts company with its surrounding and supporting wall, and then lies free as a protoplasmic cylinder in the interior of the cell. Thereupon it soon shews signs of instability, and commences to disrupt. It tends to gather into spheres, which, however, as in our illustration, may be prevented by their narrow quarters from assuming the complete spherical form, and in between these spheres, we have more or less regularly alternate ones of smaller size. We cannot wish for a better or a simpler proof of the essential fluidity of the protoplasm. Similar but less regular beads or droplets may be caused to appear under stimulation by an alternating current in the protoplasmic threads within the living cells of the hairs of Tridoscantia. The explanation usually given is that the viscosity of the protoplasm is reduced or its fluidity increased. But an increase of the surface tension would seem a more likely reason. In one of Robert Chambers' delicate experiments, a filament of protoplasm is drawn off by a microneedle from the fluid surface of a starfish egg. If drawn too far, it breaks, and part returns within the protoplasm, while the other rounds itself off on the needle's point. If drawn out less far, it looks like a row of beads or chain of droplets. If yet more relaxed, the droplets begin to fuse until the whole filament is withdrawn. If drawn out anew, the process repeats itself. The whole story is a perfect description of the behavior of a fluid jet or cylinder, of varying length and thickness. We may take note here of a remarkable series of phenomena, which, though they seem at first sight to be of a very different order, p. page 403, the shape of a splash, are closely related to those which attend and which bring about the breaking up of a liquid cylinder or thread. In Mr. Worthington's beautiful experiments on splashes, it was found that the fall of a round pebble into water from a height first formed a dip or hollow in the surface, and then caused a filmy cup of water to rise up all round, opening out trumpet fashion or closing in like a bubble, according to the height from which the pebble fell. The cup or crater tends to be fluted in alternate ridges and grooves. Its edges get scalloped into corresponding lobes and notches, and the projecting lobes or prominences tend to break off or break up into drops or beads. Figure 115. A similar appearance is seen on a great scale in the edge of a breaking wave, for the smooth figure 115. Phases of a splash, from Worthington, figure 116, a wave breaking into spray, page 400 for the foreign. The forms of cells' edge becomes notched or sinuous, and the surface nearby becomes ribbed or fluted, owing to the internal flow being helped here and hindered there by a viscous shear. And then all of a sudden, the uneven edge shoots out an array of tiny jets, which break up into the countless droplets which constitute spray, fig 116. The naturalist may be reminded also of the beautifully symmetrical notching of the calicles of many hydroid zoophytes, which little cups had begun their existence as liquid or semi-liquid films before they became stiff and rigid. The next phase of the splash, with which we are less directly concerned, is that the crater subsides, and where it stood a tall column rises up, which also tends, if it be tall enough, to break up into drops. Lastly, the column sinks down in its turn, and a ripple runs out from where it stood. The edge of our little cup forms a liquid ring or annulus, comparable on the one hand to the edge of an advancing wave, and on the other to a liquid thread or cylinder, if only we conceive the thread to be bent round into a ring. And accordingly, just as the thread segments first into an unduloid, and then into separate spherical drops, so likewise will the edge of cup or annulus tend to do. This phase of notching or beading of the edge of the splash is beautifully seen in many of Worthington's experiments, and still more beautifully in recent work, frontispiece. In the second place, the fact that the crater rises up means that liquid is flowing in from below. The segmentation of the rim means that channels of easier flow are being created, along which the liquid is led or driven into the protuberances. And these last are thereby exaggerated into the jets or streams which become conspicuous at the edge of the crater. In short, any film or film-like fluid or semi-fluid cup will be unstable. Its instability will tend to show itself in a fluting of the surface and a notching of the edge. And just such a fluting and notching are conspicuous features of many-minute organic cup-like structures. In the hydroids, fig 117, we see that these common features of the U page 405, the latter phase of a splash. The crater has subsided, a columnar jet has risen up, and the jet is dividing into droplets. From Harold E. Edgerton, Massachusetts, Institute of Technology. A cord-like thickening of the edge of the cup is a variant of the same order of phenomena. It is due to the checking at the rim of the flow of liquid from below, and a similar thickening is to be seen, not only in some hydroid calicles, but also in many vorticellae and other cup-shaped organisms. And these are by no means the only manifestations of surface tension in the splash which show resemblances and analogies to organic form. The phenomena of an ordinary liquid splash are so swiftly transitory that their study is only rendered possible by photography. Figure 117. Calicles of Campanularia species, A, B, C, D. But this excessive rapidity is not an essential part of the phenomenon. For instance, we can repeat and demonstrate many of the simpler phenomena in a permanent or quasi-permanent form by splashing water onto a surface of dry sand, or by firing a bullet into a soft metal target. There is nothing, then, to prevent a slow and lasting manifestation in a viscous medium, such as a protoplasmic organism, of phenomena.
which appear and disappear with EPH 408 evanescent rapidity in a more mobile liquid. Nor is there anything peculiar in the splash itself. It is simply a convenient method of setting up certain motions or currents and producing certain surface forms in a liquid medium, or even in such an imperfect fluid as a bed of sand. Accordingly, we have a large range of possible conditions under which the organism might conceivably display configurations analogous to or identical with those which Mr. Worthington has shown us how to exhibit by one particular experimental method. To one who has watched the potter at his wheel, it is plain that the potter's thumb, like the glass blower's blast of air, depends for its efficacy upon the physical properties of the clay or slip, which for the time being is essentially a fluid. The cup and the saucer, like the tube and the bulb, display, in their simple and primitive forms, beautiful surfaces of equilibrium as manifested under certain limiting conditions. They are neither more nor less than glorified splashes, formed slowly, under conditions of restraint which enhance or reveal their mathematical symmetry. We have seen, and we shall see again before we are done, that the art of the glass blower is full of lessons for the naturalist as also for the physicist, illustrating as it does the development of a host of mathematical configurations and organic conformations, which depend essentially on the establishment of a constant and uniform pressure within a closed elastic shell or fluid envelope or bubble. In like manner, the potter's art illustrates the somewhat obscurer and more complex problems, scarcely less frequent in biology, of a figure equilibrium, which is an open surface of revolution. The two series of problems are closely akin, for the glass blower can make most things which the potter makes by cutting off portions of his hollow ware. Besides, when this fails in the glass blower ceasing to blow, begins to use his rod to trim the sides or turn the edges of a wine glass or a beaker, he is merely borrowing a trick from the still older craft of the potter. It would seem venturesome to extend our comparison with these liquid surface tension phenomena from the cup or calicle of the hydrozoon to the little hydroid polyp within. And yet, there is something to be learned by such a comparison. The cylindrical body of the tiny polyp, the jet-like row of tentacles, the beaded EPH 409, the annulations which these tentacles exhibit, the web-like film, which sometimes, when they stand a little way apart, conjoins their bases, the thin annular film of tissue which surrounds the little organism's mouth, and the manner in which this annular peristom contracts, like a shrinking soap bubble, to close the aperture, are every one of them features to which we may find a singular and striking parallel in the surface tension phenomena of the splash. Some 70 years ago, much interest was aroused by Helmholtz's work, and also Kirchhoff's work, on discontinuous motions of a fluid. That is to say, on the movements of one body of fluid within another, and the resulting phenomena due to friction at the surfaces. What Kelvin called Helmholtz's admirable discovery of the law of vortex motion in a perfect fluid was the chief result of this investigation, and was followed by much experimental work. In order to illustrate and to extend the mathematical conclusions, the drop, the bubble, and the splash are parts of a long story, and a falling drop, or a drop moving through surrounding fluid, is a case deserving to be considered. A drop of water, tinged with fuchsin, is gently released under a pressure of a couple of millimeters at the bottom of a glass of water. Its momentum enables it to rise through a few centimeters of the surrounding water, and in doing so, it communicates motion to the water around. In front, the rising drop thrusts its way through, almost like a solid body. Behind it tends to drag the surrounding water after it by fluid friction. And these two motions together give rise to beautiful vorticoid configurations, the Strömungsspirals or tintpiles of their first discoverers, figure 119. Under a higher and more continuous pressure, on page 410, the forms of cells, figure 118a, be more phases of a splash after Worthington. See a hydroid polyp after Ullmann, figure 119, liquid jets from a Overbeck, page 411 of falling drops. The drop becomes a jet. The form of the vortex is modified thereby, and may be further modified by slight differences of temperature, that is, of density, or by interrupting the rate of flow. To let a drop of ink fall into water is a simple and most beautiful experiment. The effect is more violent than in the former case. The descending drop turns into a complete vortex ring. It expands and attenuates. It waves about, and the descending loops again turn into incipient vortices. Figure 120. Figure 120. Figure 120. Falling drops. A. Ink in water after J.J. Thompson and Newell. B. Fusel oil and paraffin after Tomlinson. Lastly, instead of letting our drop rise or fall freely, we may use a hanging drop, which, while it sinks, remains suspended to the surface.
Thus, it cannot form a complete annulus, but only a D page 412-396, the forms of cells etch, partial vortex suspended by a thread or column, just as in Overbeck's jet experiments, and the figure so produced in either case is closely analogous to that of a medusa or a jellyfish, with its bell or umbrella, and its clapper or manubrium as well. Some years ago, Emil Hatchek made such vortex drops as these of white gelatine dropped into a hardening fluid. These artificial medusae sometimes show a symmetrical pattern of radial ribs due to shrinkage, and this to dehydration by the coagulating fluid. And Fig. 121. Various metazoids. 1. Synchorate. 2. Cordylophora. 3. Cladonema after Almay. Extremely curious result of Hatchek's experiments is to show how sensitive these vorticoid drops are to physical conditions. For using the same gelatine all the while, and merely varying the density of the fluid in the third decimal place, we obtain a whole range of configurations from the ordinary hanging drop to the same with a rib pattern, and then to medusoid vortices of various graded forms. The living medusa has a geometrical symmetry so marked and regular as to suggest a physical or mechanical element in the little creature's growth and construction. It has, to begin with, its vortex H-key bell or umbrella with its cylindrical handle or manubrium. The bell is GP page 413 of vorticoid or medusoid drops, traversed by radial canals, 4 or in multiples of 4. Its edge is beset with tentacles, smooth or often beaded at regular intervals and of graded sizes, and certain sensory structures, including solid concretions or otoliths, are also symmetrically interspaced. No sooner made than it begins to pulsate. The little bell begins to ring figure 1211b, medusoid drops of gelatin after hatching. Buds, miniature replicas of the parent organism, are very apt to appear on the tentacles or on the manubrium or sometimes on the edge of the bell. We seem to see one vortex producing others before our eyes. The development of a medusoid deserves to be studied without prejudice from this point of view. Certain it is that the tiny medusoids of Obelia, for instance, are budded off with a rapidity and a complete perfection, which suggests an automatic and all but instantaneous act of conformation, rather than a gradual process of growth. Moreover, not only do we recognize in a vorticoid drop a schema or analog of medusoid form, but we seem able to discover various actual phases of the splash or drop in the all but innumerable living types of jellyfish. In Cladonema, we seem to see an early stage of a breaking drop, and in Cordylophora, a beautiful picture of incipient vortices. Figure 122, Medusa chloris, a cilia infusoria. It is hard indeed to say how much or little all of these analogies imply, but they indicate, at the very least, how certain simple organic forms might be naturally assumed by one fluid mass within another, when gravity, surface tension, and fluid friction play, page 414, the forms of cells. Their part under balanced conditions of temperature, density, and chemical composition. A little green infusorian from the Baltic Sea is, as near as may be, a medusa in miniature. It is curious indeed to find the same medusoid, or as we may now call it, vorticoid configuration, occurring in a form so much lower in the scale, and so much less in order of magnitude than the ordinary medusae. The viscosity of the liquid, while it retards the breaking up of the cylinder, and increases the length of the segments beyond that which theory demands, has nevertheless less influence in this direction than we might have expected. On the other hand, any external support or adhesion or mere contact with a solid body will be equivalent to a reduction of surface tension, and so will very greatly increase the stability of our cylinder. It is for this reason that the mercury in our thermometers seldom separates into drops, though it sometimes does so, much to our inconvenience. And again, it is for this reason that the protoplasm in a long tubular or cylindrical cell need not divide into separate cells and internodes
until the length of these far exceeds the theoretical limits.
An interesting case is that of a viscous drop immersed in another viscous fluid and drawn out into a thread by a shearing motion of the latter. The thread seems stable at first, but when left to rest, it breaks up into drops of a very definite and uniform size. The size of the drops or wavelength of the undulloid of which they are made, depending on the relative viscosities of the two threads. Plateau's results, though discovered by way of experiment, and though, as we have said, they illustrate the materialization of mathematical law, are nevertheless essentially theoretical results, approached rather than realized in material systems. That a liquid cylinder begins to be unstable when its length exceeds 2 pi is all but mathematically true of an all but immaterial soap bubble, but very far from true, as Plateau himself was well aware, in a fluid jet. Retarded by viscosity and by inertia, the principle is true and universal, but our living cylinders do not follow the abstract laws, page 415 of mathematics, any more than do the drops and jets of ordinary fluids or the quickly drawn and quickly cooling tubes in the glassworker's hands. Plateau says that in most liquids, the influence of viscosity is such as to cause the cylinder to segment when its length is about 4 times, or even 6 times its diameter instead of a fraction over 3 times. As theory would demand of a perfect fluid, if we take it at 4 times, the resulting spherules would have a diameter of about 1.8 times, and their distance apart would be about 2.2 times the original diameter of the cylinder. And the calculation is not difficult, which would show how these dimensions are altered. In the case of a cylinder formed around a solid core, as in the case of a spider's web, Plateau also observed that the time taken in the division of the cylinder is directly proportional to its diameter, while varying with the nature of the liquid. This question of the time taken in the division of a cell or filament in relation to its dimensions has not, so far as I know, been inquired into by biologists. From the simple fact that the spheres of all configurations at whose surface area for a given volume is an absolute minimum, we have seen it to be the one figure of equilibrium assumed by a drop or vesicle when no disturbing factor is at hand. But such freedom from counter-influences is likely to be rare, and neither does the raindrop nor the round world itself retain its primal sphericity. For one thing, gravity will always be at hand to drag and distort our drop or bubble, unless its dimensions be so minute that gravity becomes insignificant compared with capillarity. Even the soap bubble will be flattened or elongated by gravity, according as we support it from below or from above, and the bubble which is thinned out almost to blackness will, from its small mass, be the one which remains most nearly spherical. Innumerable new conditions will be introduced, in the shape of complicated tensions and pressures, when one drop or bubble becomes associated with another, and when a system of intermediate films or partition walls is developed between them. This subject we shall discuss later in connection with cell aggregates or tissues, and we shall find that further theoretical considerations are, page 416, the forms of cells needed as a preliminary to any such inquiry. Meanwhile, let us consider a few cases of the forms of cells, either solitary or in such simple aggregates that their individual form is little disturbed thereby. Let us clearly understand that the cases we are about to consider are those where the perfect symmetry of the sphere is replaced by another symmetry, less complete, such as that of an ellipsoidal or cylindrical cell. The cases of asymmetrical deformation or displacement, such as are illustrated in the production of a bud or the development of a lateral branch, are much simpler, for here we only assume a slight and localized variation of surface tension, such as may be brought about in various ways through the heterogeneous chemistry of the cell, but such diffused and graded asymmetry as brings about, for instance, the ellipsoidal shape of a yeast cell is another matter. If the sphere be the one surface of complete symmetry and therefore of independent equilibrium, it follows that in every cell which is otherwise conformed there must be some definite cause of its departure from sphericity. And if this cause be the obvious one of resistance offered by a solidified envelope, such as an eggshell or firm cell wall, we must still seek for the deforming force which was in action to bring about the given shape prior to the assumption of rigidity. Such a cause may be either external to or may lie within the cell itself. On the one hand, it may be due to external pressure
or some form of mechanical restraint, as when we submit our bubble to the partial restraint of discs or rings, or more complicated cages of wire. On the other hand, it may be due to intrinsic causes, which must come under the head either of differences of internal pressure or of lack of homogeneity or isotropy in the surface or its envelope. GP 417 of asymmetry and anisotropy. Our formula of equilibrium or equation to an elastic surface is P equals P sub E plus, in parentheses, T over R plus T prime over R prime, end parentheses, where P is the internal pressure, P sub any extraneous pressure normal to the surface are R prime, the radii of curvature at point, and T prime, the corresponding tensions normal to one another of the envelope. Now, in any given form which we seek to account for, R prime are known quantities, but all the other factors of the equation are subject to inquiry, and somehow or other, by this formula, we must account for the form of any solitary cell whatsoever, provided always that it be not formed by successive stages of solidification. The cylindrical cell of Spirogyra, the ellipsoidal yeast cell, or, as we shall see in another chapter, even the egg of any bird. In using this formula hitherto, we have taken it in a simplified form. That is to say, we have made several limiting assumptions. We have assumed that P was the uniform hydrostatic pressure, equal in all directions, of a body of liquid. We have assumed likewise that the tension T was due to surface tension in a homogeneous liquid film, and was therefore equal in all directions, so that T equals to prime, and we have only dealt with surfaces or parts of a surface where extraneous pressure, P sub n, was non-existent. Now, in the case of a bird's egg, the external pressure, P sub n, that is to say the pressure exercised by the walls of the oviduct, will be found to be a very important factor. But in the case of the yeast cell or the Spirogyra, wholly immersed in water, no such external pressure comes into play. We are accordingly left in such cases as these last with two hypotheses, namely that the departure from a spherical form is due to inequalities in the internal pressure P, or else to inequalities in the tension T, as to say, to a difference between T and T prime. In other words, it is theoretically possible that the oval form of a yeast cell is due to a greater internal pressure, a greater tendency to grow in the direction of the longer axis of the ellipse, or alternatively, that with equal and symmetrical tendencies to growth, there is associated a difference of external resistance in respect of the tension, and implicitly the molecular structure of the cell wall. Now the former hypothesis is not impossible. Protoplasm is far from being a perfect fluid. It is the seat of various internal forces, sometimes manifestly polar. And it is quite possible that the forces osmotic and other, which lead to an increase of the content of the Ju page 418, the forms of cells, cell and are manifested in pressure outwardly directed upon its wall, may be unsymmetrical, and such as to deform what would otherwise be a simple sphere. But while this hypothesis is not impossible, it is not very easy of acceptance. The protoplasm, though not a perfect fluid, has yet on the whole the properties of a fluid. Within the small compass of the cell, there is little room for the development of unsymmetrical pressures. And in such a case as Spirogyra, where most part of the cavity is filled by watery sap, the conditions are still more obviously, or more nearly those under which a uniform hydrostatic pressure should be displayed. But in variations of T, that is to say of the specific surface tension per unit area, we have an ample field for all the various deformations with which we shall have to deal. Our condition now is that open parenthesis T over R plus T prime over R prime close parenthesis equals a constant. But it no longer follows, though it may still often be the case, that this will represent a surface of absolute minimal area. As soon as T and T prime become unequal, we are no longer dealing with a perfectly liquid surface film, but its departure from perfect fluidity may be of all degrees. From that of a slight non-isotropic viscosity to the state of a firm elastic membrane. And it matters little whether this viscosity or semi-rigidity be manifested in the self-same layer, which is still a part of the protoplasm of the cell, or in a layer which is completely differentiated into a distinct and separate membrane. As soon as by secretion or adsorption, the molecular constitution of the surface layer is alteration, or the secondary chemical changes which follow it,
maybe such as to produce an anisotropy, and to render the molecular forces less capable in one direction than another of exerting that contractile force, by which they are striving to reduce to a minimum the surface area of the cell. A slight inequality in two opposite directions will produce the ellipsoid cell, and a great inequality will give rise to the cylindrical cell, or any other cylindrical cell which grows in freedom from any manifest external restraint, has assumed that particular form simply by reason of the molecular constitution of its developing wall, or page 419 of its symmetry and anisotropy membrane, and that this molecular constitution was anisotropous, in such a way as to render extension easier in one direction than another. Such a lack of homogeneity or of isotropy in the cell wall is often rendered visible, especially in plant cells, in the form of concentric lamellae, annulae, and spiral striations. But there exists yet another heterogeneity to help us account for the long threads, hairs, fibers, cylinders, which are so often formed. Carl Nageli said many years ago that organized bodies, starch grains, cellulose, and protoplasm itself consisted of invisible particles, each an aggregate of many molecules. He called them micellae, and these were isolated or dispersed, as we should say, in a watery medium. This theory was, to begin with, an attempt to account for the colloid state. But at the same time, the particles were supposed to be so ordered and arranged as to render the substance anisotropic, to confer on it vectorial properties, as we say nowadays. And so, to account for the polarization of light by a starch grain or a hair, it was so criticized by Bütschli and von Ebner that it fell into disrepute, if not oblivion. But a great part of it was true. And the micellar structure of wool, cotton, silk, and similar substances is now rendered clearly visible by the same X-ray methods as revealed the molecular orientation, or lattice structure, of a crystal to von Lau. It is now well known that the cell wall has in many cases a definite structure which depends on molecular assemblages in the material of which it is composed, and is made visible by X-rays in the form of diffraction patterns. The green alga valonia has very large bubbly cells, 2 to 3 centimeters long, with cell walls formed, as usual, of subglyceride with long chain molecules some 500 angstrom units, or say 0.05 mu long, bound together sideways to form a multiple sheet or three-dimensional lattice. In the cell wall of valonia, one set of chains runs around in a left-handed spiral. Another forms meridians from pole to pole, and these two layers are superposed alternately to build the wall. Hemp has 2 layers, both running in right-handed spirals. Flax 2 layers, crossing and recrossing in spirals of opposite side. Even the cytoplasm and its contents seem to be influenced by molecular lines directrices, corresponding to the striae of the cell wall. Analogous, but still more complicated results of molecular structure are to be found in wool, cotton, and other fibers. Page 420, the forms of cells. But this phenomenon, while it brings about a certain departure from complete symmetry, is still compatible with, and coexistent with, many of the phenomena which we have seen to be associated with surface tension. The symmetry of tensions still leaves the cell a solid of revolution, and its surface is still a surface of equilibrium. The fluid pressure within the cylinder still causes the filmical form, or membrane, which caps its ends, to be of a spherical form. And in the young cell, where the surface pellicle is absent, or but little differentiated, as for instance in the ogonium of Achlea or in the young zygospore, we see the tendency of the entire structure towards a spherical form reasserting itself, unless, as in the latter case, it be overcome by direct compression within the cylindrical mother cell. Moreover, in those cases where the adult filament consists of cylindrical cells, we see that the young germinating spore, at first spherical, very soon assumes with growth an elliptical or ovoid form, the direct result of an incipient anisotropy of its envelope, which, when more developed, will convert the ovoid into a cylinder. We may also notice that a truly cylindrical cell is comparatively rare, for in many cases what we call a cylindrical cell shews a distinct bulging of its sides. It is not truly a cylinder, but a portion of a spheroid or ellipsoid. Unicellular organisms in general, protozoa, unicellular cryptogams, various bacteria, and the free isolated cells, spores, ova, etc., of higher organisms, are referable for the most part to a small number of typical forms, but there are many others in which either no symmetry is to be recognized, or in which the form is clearly not one of equilibrium. Among these latter we have amoeba itself, and all manner of amoeboid organisms, and also many curiously shaped cells such as the trypanosums and various aberrant infusoria. We shall return to the consideration of these, but in the meanwhile it will suffice to say and to repeat that inasmuch as their surfaces are not equilibrium surfaces, so neither are the living cells themselves in any stable equilibrium. On the contrary, they are in continual flux and movement, each portion of the U page 421 of stable and unstable equilibrium surface constantly changing its form, passing from one phase to another of an equilibrium, which is never stable for more than a moment, and which death restores to the stable equilibrium of a sphere. The former class, which rest in stable equilibrium, must fall, as we have seen, into two classes, those whose equilibrium arises from liquid surface tension alone, and those in whose conformation some other pressure or restraint has been superimposed upon ordinary surface tension. To he fact that all these organisms belong to an order of magnitude in which form is mainly, if not wholly, conditioned and controlled by molecular forces, is due the limited range of forms which they actually accept. They vary according to varying physical conditions. Sometimes they do so in so regular and orderly a way that we intuitively explain them as phases of a life history and leave physical properties and physical causation alone. But many of their variations of form we treat as exceptional, abnormal, decadent, or morbid, and are apt to pass these over in neglect, while we give our attention to what we call a typical or characteristic form or attitude. In the case of the smallest organisms, bacteria, micrococci, and so forth, the range of form is especially limited, owing to their minuteness, the powerful pressure which their highly curved surfaces exert, and the comparatively homogeneous nature of their substance. But within their narrow range of possible diversity, these minute organisms are protean in their changes of form. A certain species will not only change its shape from stage to stage of its little cycle of life, but it will be remarkably different in outward form according to the circumstances under which we find it, or the histological treatment to which we subject it. Hence the pathological student, commencing the study of bacteriology, is early warned to pay little heed to differences of form, for purposes of recognition or specific identification. Whatever grounds we may have for attributing to these organisms a permanent or stable specific identity, after the fashion of the higher plants and animals, we can seldom safely do so on the ground of definite and always recognizable form. We may often be inclined, in short, to ascribe to them a physiological, sometimes a pathogenic, rather than a morphological specificity. Many unicellular forms and a few other simple organisms are spherical, and serve to illustrate in the simplest way the point at issue. Unicellular algae, such as Protococcus or Halosphaera, the innumerable floating eggs of fishes, the floating unilocular foraminifer or Bellina, the lovely green multicellular volvox of our ponds. All of these in their several grades of simplicity or complication are so many round drops, spherical because no alien forces have deformed or misshapen them. But observe that, with the exception of volvox, whose spherical body is covered wholly and uniformly with minute cilia, all the above are passive or inactive forms. And in a resting or insisted phase, the spherical form is common and general in a great range of unicellular organisms. Conversely, we see that those unicellular forms which depart markedly from sphericity, excluding for the moment the amoeboid forms and those provided with skeletons, are all ciliate or flagellate. Cilia and flagella are sui generis. We know nothing of them from the physical side. We cannot reproduce or imitate them in any non-living drop or fluid surface. But we can easily see that they have an influence on form, besides serving for locomotion. When our little monad or euglena develops a flagellum, that is in itself an indication of asymmetry or polarity, of non-homogeneity of the little cell. And in the various flagellate types, the flagellum, or its analogues, always stand on prominent points, or ends, or edges of the cell. Where curvature is high and surface tension may be expected to be low, for the product of surface tension by mean curvature tends to be constant. Figure 123. A flagellate monad distigma proteus Ehrenberg. After Seville, Kent. The minute dimensions of a cilium or a flagellum are such that the molecular forces leading to surface tension must here be under peculiar conditions and restraints. We cannot hope to understand them by comparison with a whiplash, or through any other analogy drawn from a different order of magnitude. I suspect that a ciliary surface is always electrically charged, and that a point charge is formed or induced in each cilium or flagellum. Just as we learn the properties of a drop or a jet as phenomena proper to their scale of magnitude, so someday we shall learn the very different physical but UP 423 study of cilia and flagella. Microcosmic properties of these minute, mobile, pointed, fluid, or semi-fluid threads. Cilia, like flagella, tend to occupy positions or cover surfaces which would otherwise be unstable, and often indeed, as in a trochosphere larva, or even in a rotifer, a ring of cilia seems to play the very part of one of Plato's wire rings, supporting and steadying the semi-fluid mass in its otherwise unstable configuration. Let us note here in passing what seems to be an analogous phenomenon. Chitinous hairs, spines, or bristles are common and characteristic structures among the smaller crustacea, and more or less generally among the arthropods. We find them at every exposed point or corner. They fringe the sharp edge or border of a limb. As we draw the creature, we seem to know where to put them in. In short, they tend to occur, as the flagella do, just where the surface tension would be lowest, if or when the surface was in a fluid condition. Of the other surfaces plateau, we find cylinders enough and despair and spirigira, and a host of other filamentous algae and fungi. But it is to the vegetable kingdom that we go to find them, where a cellulose envelope enables the cylinder to develop beyond its ordinary limitations. The unduloid makes its appearance whenever sphere or cylinder begin to give way. We see the transitory figure of an unduloid in the normal fission of a simple cell, or of the nucleus itself, and we have already seen it to perfection in the incipient beatings of a spider's web, or of a pseudopodial thread of protoplasm. A large number of infusoria have unduloid contours, in part at least, and this figure appears in reap pairs in a great variety of forms. The cups of various vorticellae, figure 124 below the ciliated ring, look like a beautiful series of unduloids in every gradation of form, from what is all but cylindrical to all but a perfect sphere. Moreover, successive phases in their life history appear as mere graded changes on page 424 of unduloid form. It has been shown lately, in one or two instances at least, that species of vorticella may metamorphose into one another. In other words, that contours supposed to characterize species are not specific. Figure 124. Various species of vorticella. Figure 125. Various species of salpingoica. Figure 126. Various species of Tintinus, Dinobrion, and Cotinella. After Seville, Kent, and others, these vorticellid unduloids are not fully symmetrical. Rather, are they such unduloids as develop when we suspend an oil globule between two unequal rings, or blow a bubble between two unequal pipes. For our vorticellid bell hangs by two terminal supports, the narrow stalk to which it is attached below, and the thickened ring from which spring its circumoral cilia. And it is most interesting to see how, when the bell leaves page 425 of various unduloids, 409, its stalk, as sometimes happens, and swims away, a new ring of cilia comes into being to encircle and support its narrow end. Similar unduloids may be traced in even greater variety among other families or genera of the infusoria. Sometimes, as in vorticella itself, the unduloid is seen in the contour of the soft semifluid body of the hiving animal. At other times, as in Salpingoica, Tintinus, and many other genera, we have a membranous cup containing the animal, but originally secreted by and molded upon its semifluid hiving surface. Here we have an excellent illustration of the contrast between the different ways in which such a structure may be regarded and interpreted. The teleological explanation is that it is developed for the sake of protection, 127, Phaginicola fig 128. Folliculina, as a domicile and shelter for the H-tidal organism within. The mechanical explanation of the physicist seeking after the efficient, not the final cause, is that it owes its presence and its actual confirmation to certain chemico-physical conditions, that it was inevitable under the given conditions that certain constituent substances present in the protoplasm
should be drawn by molecular forces to its surface layer, that under this adsorptive process, the conditions continuing favorable, the particles accumulated and concentrated till they formed, with the help of the surrounding medium, a pellicle or membrane, thicker or thinner as the case might be. That this surface, polypi or membrane, was inevitably bound by molecular forces to contract into a surface of the least possible area, which the circumstances permitted, and freedom of the system permitted, and ipso facto caused this surface to be a surface of revolution, and that of the few surfaces of revolution, which, as T-pitch 426, being also surfaces minimi array, were available, the unduloid was manifestly the one permitted, and ipso facto caused by the dimensions of the organism and other circumstances of the case. And just as the thickness or thinness of the pellicle was obviously a subordinate matter, so we see that the actual outline of this, or that particular unduloid, is also a very subordinate matter, such as physicochemical variants of a minor order would suffice to bring about. For between the various unduloids which the various species of Vorticella represent, there is no more real difference than that difference of ratio or degree which exists between two circles of different diameter, or two lines of unequal length. Figure 129. Trachelophyllum. After Rezhnowski, in many cases, of which figure 129 is an example, we have a more or less unduloid form exhibited not by a surrounding pellicle or shell, but by the soft protoplasmic body of a ciliated organism. In such cases, the form is mobile and changes continually from one to another unduloid contour according to the movements of the animal. We are dealing here with no stable equilibrium, but possibly with a subtle problem of streamlines, as in the difficult but beautiful problem suggested by the form of a fish. But this whole class of cases and of problems we merely take note of here. We shall speak of them again, but their treatment is hard. In considering such series of forms as these various unduloids, we are brought sharply up, as in the case of our bacteria or micrococci, against the biological concept of organic species. In the intense classificatory activity of the last 100 years, it has come about that every form which is apparently characteristic, that is to say, which is capable of being described or portrayed, and of being cage 427 recognized when met with again, has been recorded as a species, for we need not concern ourselves with the occasional discussions or individual opinions as to whether such and such a form deserves specific rank or be only a variety. And this secular labor is pursued in direct obedience to the precept of the Systema Naturae, ut sic in summa confusione rerum apparenti. Summus conspicitur naturae ordo. In like manner, the physicist records, and is entitled to record, his many hundred species of snow crystals, or of crystals of calcium carbonate. Indeed, the snow crystal illustrates to perfection how nature rings the changes on every possible variation and permutation and combination of form, subject only to the condition in this instance that a snow crystal shall be a plane, symmetrical, rectilinear figure with all its external angles those of a regular hexagon. We may draw what we please on a sheet of hexagonal paper keeping to its lines, and when we repeat our drawing kaleidoscope fashion about a center, the stellate figure so obtained is sure to resemble one or another of the many recorded species of snow crystals. And this endless beauty of crystalline form is further enhanced when the flakes begin to thaw, and all their feathery outlines soften. But regarding these species of his, the physicist makes no assumption. He records them simpliciter. He notes, as best he can, the circumstances such as temperature or humidity under which each occurs, in the hope of elucidating the conditions which determine their formation, but above all, he on page 428, the forms of cells, does not introduce the element of time and of succession or discuss their origin and affiliation as an historical sequence of events. But in biology, the term species carries with it many large, though often vague assumptions. Though the doctrine or concept of the permanence of species is dead and gone, yet a certain quasi-permanency is still connoted by the term. If a tiny foraminiferal shell, a lagina for instance, be found living today, and a shell indistinguishable from it to the eye be found fossil in the chalk, or some still more remote geological formation,
the assumption is deemed legitimate that that species has survived and has handed down its minute-specific character or characters from generation to generation, unchanged for untold millions of years. If the ancient forms be like to rather than identical with the recent, we still assume an unbroken descent, accompanied by the hereditary transmission of common characters and progressive variations. And if two identical forms be discovered at the ends of the earth, still, with occasional slight reservations on the score of possible homoplasy, we build hypotheses on this fact of identity, taking it for granted that the two appertain to a common stock, whose dispersal in space must somehow be accounted for, its root traced, its epoch determined, and its causes discussed or discovered. In short, the naturalist admits no exception to the rule that a natural classification can only be a genealogical one, nor ever doubts that the fact that we are able to classify organisms at all in accordance with the structural characteristics which they present is due to the fact that they're being related by descent. But this great and valuable and even fundamental generalization sometimes carries us too far. It may be safe and sure and helpful and illuminating when we apply it to such complex entities, such thousand-fold resultants of the combination and permutation of many variable characters, as a horse, a lion, or an eagle. But to my mind, it has a very different look and a far less firm foundation when we attempt to extend it to minute organisms whose specific characters are few and simple, whose simplicity, page 429, becomes more manifest from the point of view of physical and mathematical analysis, and whose form is referable, or largely referable, to the direct action of a physical force. When we come to the minute skeletons of the radiolaria, we shall again find ourselves dealing with endless modifications of form, in which it becomes more and more difficult to discern, and at last vain and hopeless to apply, the guiding principle of affiliation or phylogeny. Among the foraminifera, we have an immense variety of forms, which, in the light of surface tension and of the principle of minimal area, are capable of explanation and of reduction to a small number of characteristic types. Many of them are composite structures, formed by the successive imposition of cell upon cell, and these we shall deal with later on. Let us glance here at the simpler conformations exhibited by the single-chambered or monothalamic genera, and perhaps one or two of the simplest composites. We begin with forms like Asterhyza, figure 320, page 703, which are large, coarse, and highly irregular, and end with others which are minute and delicate, and which manifest a perfect and mathematical regularity. The broad difference between these two types is that the former are characterized, like amoeba, by a variable surface tension, and consequently by unstable equilibrium. But the strong contrast between these and the regular forms is bridged over by various transition stages, or differences of degree. Indeed, as in all other rhizopods, the very fact of the emission of pseudopodia, which are especially characteristic of this group of animals, is a sign of unstable surface equilibrium, and we must therefore consider, or may at least suspect, that those forms whose shells indicate the most perfect symmetry and equilibrium have secreted these during periods when rest and uniformity of surface conditions contrasted with the phases of pseudopodial activity. The irregular forms are in almost all cases arenaceous. That is to say, they have no solid shells formed by steady adsorptive secretion, but only a looser covering of sand grains with which the protoplasmic body has come in contact and cohered. Sometimes, as in Ramalina, we have a calcareous shell combined with irregularity of form, but here we can easily see a partial and, as it were, a broken regularity. The regular forms of sphere and cylinder being repeated in various end page 430-414. The forms of cells etch parts of the ramified mass. When we look more closely at the arenaceous forms, we find the same thing true of them. They represent, in whole or part, approximations to the surfaces of equilibrium, spheres, cylinders, and so forth. In Aschimonnella, we have a precise replica of the calcareous Ramilia, and in Asterhyza itself, in the forms distinguished by Giaturlis as A. crescentina, what is described as the subsegment interiors. Various species of Zagruella. After Brady, the natural physical tendency of the long semifluid cylinder of protoplasm to contract at its limit of stability into unduloid constriction, as a step towards the breaking up into separate spheres. completion of which process is restrained or prevented by contact with the unyielding arenaceous covering. Passing to the typical calcareous foraminifera, we have the most symmetrical of all possible types in the perfect sphere of Orbulina. This is a pelagic organism whose floating habitat gives it a field of Brady Challenger monograph. Challenger monograph. Page 431 of hanging drops. Force of perfect symmetry. Save for one or two other forms which are also spherical or approximately so, like Thermina, the rest of the monothalamic calcareous foraminifera are all comprised by naturalists within the genus Lagina. This large and varied genus consists of flask-shaped shells whose surface is that of an unduloid, or like that of a flask itself, an unduloid combined with a portion of a sphere. We do not know the circumstances under which the shell of Lagina is formed, nor the nature of the force by which, during its formation, the surface is stretched out into the unduloid form. But we may be pretty sure that it is suspended vertically in the sea, that is to say, in a position of symmetry, as regards its vertical axis, about which the unduloid surface of revolution is symmetrically formed. Figure 131. Roman pottery for comparison with species of Lagina. For example, 1 and 2 with L. sulcata, 3, L. urbaniana, 4, L. striata, 5, L. striata, 6, L. styligera. At the same time, we have other types of the same shell in which the form is more or less flattened. And these are doubtless the cases in which such symmetry of position was not present, or was replaced by a broader lateral contact with the surface pellicle. While Orbulina is a simple spherical drop, Lagina suggests to our minds a hanging drop, drawn out to a longer or shorter neck by EP 432, that forms itself. Its own weight, aided by the viscosity of the material. Indeed, the various hanging drops, such as Mr. C.R. Darling shews us, are the most beautiful and perfect unduloids with spherical ends that it is possible to conceive. A suitable liquid, a little denser than water and incapable of mixing with it, such as ethyl benzoate, is poured on a surface of water. It spreads over the surface and gradually forms a hanging drop, approximately hemispherical. But as more liquid is added, the drop sinks or rather stretches downwards, still adhering to the surface film, and the balance of forces between gravity and surface tension results in the unduloid contour. As the increasing weight of the drop tends to stretch it out and finally break it in two. At the moment of rupture, by the way, a tiny droplet is formed in the attenuated neck, such as we described in the normal division of a cylindrical thread. Figure 132, large hanging drops of oil. After Darling, the thin fusiform pointed non-globular Laginas are less easily explained. Surface tension, which tends to keep the drop spherical, is overmastered here, and the elongate shape suggests the viscous drag of a shearing fluid. To pass to a more highly organized class of animals, we find the unduloid beautifully exemplified in the little flask-shaped shells of certain pteropod mollusca, for example, Cuvierina. Here again, the symmetry of the figure would at once lead us to suspect that the creature lived in a position of symmetry to the surrounding forces, as for instance, if it floated in the ocean in an erect position. That is to say, with its long axis coincident with the direction of gravity. And this we know to be actually the mode of life of the little pteropod. Many species of Lagina are complicated and beautified by a pattern, and some by the superaddition to the shell of plane extensions or wings. These latter give a secondary bilateral symmetry to the little shell, and are strongly suggestive of a phase or a period of growth in which it lay horizontally on the surface, instead of hanging vertically from the surface film, in which, that is to say, it was a floating and not a hanging drop. The pattern is of two kinds. Sometimes it consists of a sort of fine reticulation with rounded or more or less hexagonal interspaces. In other cases, it is produced by a symmetrical series of ridges or folds, usually longitudinal, on the body of the flask-shaped cell, but occasionally transversely arranged upon the narrow neck. The reticulated and folded patterns we may consider separately. The netted pattern is very similar to the wrinkled surface of a dried pea or to the more regular wrinkled patterns on poppy and other seeds and even pollen grains. If a spherical body, after developing a skin, begin to shrink a little, and if the skin have so far lost its elasticity as to be unable to keep pace with the shrinkage of the inner mass, it will tend to fold or wrinkle, and if the shrinkage be uniform, and the elasticity and flexibility of the skin be also uniform, then the amount of foldings will be uniformly distributed over the surface. Little elevations and depressions will appear, regularly interspaced and separated by concave or convex folds. These being of equal size, unless the system be otherwise perturbed, each one will tend to be surrounded by 6 others, and when the process has reached its limit, the intermediate boundary walls or folds will be found converted into a more or less regular pattern of hexagons. To these symmetrical wrinkles or shrinkage patterns, we shall return again. But the analogy of the mechanical wrinkling of the coat of a seed is but a rough and distant one, for we are dealing with molecular rather than with mechanical forces. In one of Darling's experiments, a little heavy tar oil is dropped onto a saucer of water, over which it spreads in a thin film, showing beautiful interference colors after the fashion of those of a soap bubble. Presently, tionals appear in the film, which gradually increase in size till they form a cellular pattern, or honeycomb, the oil gathering together in the meshes or walls of the cellular net. Some action of this sort is in all probability at work in a surface film, page 434, protoplasm covering the shell. As a physical phenomenon, the actions involved are by no means fully understood, but surface tension, diffusion, and cohesion play their respective parts therein. The very perfect cellular patterns obtained by Leduc, to which we shall have occasion to refer in a subsequent chapter, are diffusion patterns on a larger scale, but not essentially different. The folded or pleated pattern is doubtless to be explained in a general way by the shrinkage of a surface film under certain conditions of viscous or frictional restraint. Figure 133, a case which, as it seems to me, is closely allied to that of our foraminiferal shells, is described by Quincke, who let a film of chromatized gelatin or of resin set and harden upon a surface of quicksilver, and found that the little solid pellicle had been thrown into a pattern of symmetrical folds, as fine as a diffraction grating. If the surface thus folded or wrinkled be a cylinder or any other figure with one principal axis, page 435, of fluted or pleated cells, of symmetry, such as an ellipsoid or unduloid, the folds will tend to be related to the axis of symmetry, and we may expect accordingly to find regular longitudinal or regular transverse wrinkling. Now, as a matter of fact, we almost invariably find in Ligiana the former condition. That is to say, in our ellipsoid or unduloid shell, the puckering takes the form of the vertical fluting on a column, rather than that of the transverse pleating of an accordion. And further, there is often a tendency for such longitudinal flutings to be more or less localized at the end of the ellipsoid, or in the region where the unduloid merges into its spherical base. In the latter region, we often meet with a regular series of short longitudinal folds, as in the forms denominated L symmetria. All these various forms of surface can be imitated, or precisely reproduced, by the art of the glass blower, and they can be seen in a contracting bubble of saponin, though not in the more fluid soap bubble. They remind one of the ribs or flutings in the film or sheath which splashes up to envelop a smooth pebble dropped into a liquid, as Mr. Worthington has so beautifully shown. In Mr. Worthington's experiment, there appears to be something of the nature of a viscous drag in the surface pellicle, but whatever be the actual cause of variation of tension, it is not difficult to see that there must be in general a tendency towards longitudinal puckering or fluting in the case of a thin-walled cylindrical or other elongated body, rather than a tendency towards transverse puckering or pleating. For let us suppose that some change takes place involving an increase of surface tension in some small area of the curved wall, and leading therefore to an increase of pressure. That is to say, let T become T plus T, and P become P plus P. Our new equation of equilibrium, then in place of P equals T over R plus T over R prime, becomes P plus P over R plus T over R plus T over R prime on page 436, the forms of cells. And by subtraction, P equals T over R plus T over R prime. Now, if R is less than R prime, T over R is greater than T over R prime. Therefore, in order to produce a small increment of pressure P, it is easier to do so by increasing T over R than T over R prime. That is to say, the easier way is to alter or diminish R, and the same will hold good if the tension and pressure be diminished instead of increased. This is as much as to say that when corrugation or rippling of the walls takes place owing to small changes of surface tension and consequently of pressure, such corrugation is more likely to take place in the plane of Oar, that is to say, in the plane of greatest curvature. And it follows that in such a figure as an ellipsoid, wrinkling will be most likely to take place not only in a longitudinal direction, but near the extremities of the figure. That is to say, again, in the region of greatest curvature. The longitudinal wrinkling of the flask-shaped bodies of our lagenae and of the more or less cylindrical cells of many other foraminifera, figure 134, is in complete accord with the above considerations, but nevertheless, we soon find that our result is not a general one, but is defined by certain limiting conditions, and is accordingly subject to what are, at first sight, important exceptions. For instance, when we turn to the narrow neck of the lagina, we see at once that our theory no longer holds. For the wrinkling which was invariably longitudinal in the body of the cell is as invariably transverse in the narrow neck. The reason for the difference is not far to seek. The conditions in the neck are very different from those in the expanded portion of the cell, the main difference being that the thickness of the wall is no longer insignificant, but is of considerable magnitude as compared with the diameter or circumference of the neck. We must accordingly take it into account in considering the bending moments at any point in this region of the shell wall. And it is at once obvious that in any portion of the narrow neck, flexure of a wall in a transverse direction will be very difficult, while flexure in a longitudinal direction will be comparatively easy, just as in the case of a long, narrow strip of iron. We may easily bend it into folds running transversely to its long axis, but not the other way. The manner in which our little lagina shell, page 437 of fluted or pleated cells, tends to fold or wrinkle longitudinally in its wider part and transversely or annularly in its narrow neck is thus completely explained. An identical phenomenon is apt to occur in the little flask-shaped gonangia, or reproductive capsules of some of the hydroid zoophytes, in the annex drawings of these gonangia in two species of Campanularia. We see that in one case, the little vesicle has the flask-shaped or unduloid configuration of a lagina, and here the walls of the flask are longitudinally fluted, just after the manner we have witnessed in the latter genus. In the other Campanularian, the vesicles are long, narrow, and tubular, and here a transverse folding or pleating takes the place of the longitudinally fluted pattern. And the very form of the folds or pleats is enough to suggest that we are not dealing here with a simple phenomenon of surface tension, but with a condition in which surface tension and stiffness are both present and play their parts in the resultant form. Figure 134, Nodos Aries Scalaris, batch, figure 135, Gonangia of Campanularians. An everted rim or short neck may arise in various ways apart from the phenomenon of the hanging drop. To make a thistle head, the glass blower blows a bubble, and from that another one. After blowing the latter up large and thin, he crushes it to pieces, and melting down what is left of it, he forms the rim. I take it that the neck or rim of the shell in diffugia is formed in an analogous way. In connection with the growth of a new individual at the mouth, page 438, there is a very neat expanded orifice in the cyst of Cromulina, figure 136. It is doubtless fashioned in just a simple way, but how I know not. Figure 136, flask-shaped shells or cysts. A and B Cromulina and Duropyxis flagellata C. difflugia, passing from the solitary flask-shaped cell of Lagina, but without leaving the foraminifera, we find in Nodoceria, Rheophax or Segrina, constricted cylinders or successive unduloids, such as are represented in figure 137. In some of these, as in the Arenaceous genus Rheophax, we have to do with the ordinary phenomenon of a partially segmenting cylinder. But in others, the structure is not developed out of a continuous protoplasmic cylinder, but as we can see by examining the interior of the shell, it has been formed in successive stages, beginning with a simple unduloid lagina, about which, after it solidified, another drop of protoplasm accumulated, and in turn assumed the unduloid or laginoid form. The chains of interconnected bubbles which Maury and Draper made many years ago of melted resin are a similar, if not identical, phenomenon.
Figure 137. Various species of Nodoceria, Rheophax sagrina. After Brady, D page 439, VD, of the quiet of the deep sea, 423 fishes, show a vast though helmeted variety of form, and some of the strangest shapes are found in the great depths of the ocean. Here, in unchanging temperature and darkness, save for a few phosphorescent rays, above all, in unruffled stillness and eternal fig, 138. Deep sea fishes, Stomiatidae, Lamprotoxus flagellibarbis, B. Eustomius dactylibus, C. Epari, D. Schmiditi, E. Sylvestans, after Tate Riggin and Truovas. Calm, the conditions of HFE are strange indeed. In deep sea fishes, length and attenuation are common characters of the body and of its parts. A barbel below the HPA may grow to 10 times the whole length of the fish. It ends commonly in an polymer blob. It may give off thread-like branches, and these last slender filaments in Overbeck's jet experiments en Superapia. 394. The water into which the jet is led must first stand for many hours till all internal movements and temperature differences are eliminated. On page 448, the forms of cells are sometimes finely beaded, and slight differences in the beading and branching are said to characterize allied species of fish. Such a barbel looks like a jet or branching stream of one fluid falling through another. It may indeed be that in these quiet depths growth easily follows its lines of least resistance, and that in the shaping of these peculiar outgrowths, hydrodynamical and capillary forces are taking the upper hand. We have found it easy to illustrate the sphere, the cylinder, and the unduloid, 3 of the 6 surfaces of plateau, all with an endless wealth of illustration among the simplest of organisms. The plane we need hardly look for among the finite outlines of a fluid body, and the catenoid, also a surface of zero mean curvature, can likewise only be a rare and transitory configuration. One last surface still remains, namely the node. And there also remains one very common, but most remarkable protozoan configuration, that of the ciliate infusoria, to the most characteristic feature of which we have not so far found a physical analog. Stentor, a ciliate infusorian, from Saville, Kent. Here the curved contour seems to enter, re-enter, and disappear within the substance of the body, so bounding a deep and twisted space or passage, which merges with the fluid contents and vanishes within the cell, and is called by naturalists the gullet. This very peculiar and complicated structure is only kept in equilibrium by the constant activity of cilia over the general surface, page 441, of the ciliate infusoria, of the body, and very especially in the said gullet or re-entrant portion of the surface. Now we have seen the nodoid to be a curved surface, re-entering on itself and endless. No method of support, by wire rings or otherwise, enables us to construct or realize more than a small portion of it. But the typical ciliate, such as paramucine, looks just like what we might expect a nodoid surface to be, if we could only realize it, or a single segment of it in a drop of fluid, and imagine it to be kept in quasi-equilibrium by continual ciliary activity. I suspect indeed that here is nothing more and nothing less than a partial realization of the nodoid itself, that the so-called gullet is but the characteristic inversion or kink in that curve, and that the cilia, which normally clothe the surface and always line the gullet, are needed to realize and to maintain the unstable equilibrium of the figure. If this be so, it is a suggestion and no more. We shall have found among our simple organisms the complete realization, in varying abundance, of each and all of the 6 surfaces of plateau. On each and all of them, we have a host of beautiful patterns of various sorts. All of them so beautiful and so symmetrical that they ought to be capable of geometric representation, and all waiting for their interpreter. From all these configurations, which the law of minimal area controls and dominates, amoeba stands aloof and alone. The rest are all figures of equilibrium, unstable though it may sometimes be. But amoeba is the characteristic case of a fluid surface without an equilibrium. It is the very negation of stability. In composition, it is neither constant nor homogeneous. Its chemistry is in constant flux. Its surface energies vary from here to there. Its fluid substance is drawn hither and thither. Within and without, it is never still, be its motions swift or be they slow. The heterogeneity of its system points towards a maximal surface area, rather than a minimal one,
Only here and there, in small portions of its heterogeneous substance, do we see the rounded contours of a fluid drop in token of temporary equilibrium. Only when its heterogeneous reactions quieten down and the little living speck enters on its resting stage does the protoplasmic body withdraw itself into a sphere and the law of area minima come into its own. Physically analogous is the case of such complicated pseudopodia or axopodia as we find among the foraminifera and heliella, where the whole page 442, the forms of cells. Fabric is in a flux, and currents flow and granules are carried hither and thither. Here again there is no statical equilibrium, but surface tension varies, as does the chemistry of the protoplasm, from one spot to another. The great oceanic group of the radiolaria and the highly complicated skeletons which they construct give us many beautiful illustrations of physical phenomena, among which the effects of surface tension are as usual prominent. But we shall deal later on with these little skeletons under the head of spicular concretions. In a simple and typical heliozoan, such as the sun animalcule, actinophrys sol, we have a drop of protoplasm, contracted by its surface tension into a spherical form. Within this heterogeneous protoplasm are more fluid portions, and a similar surface tension causes these also to assume the form of spherical vacuoles, or of little clear drops within the big one, unless indeed they become numerous and closely packed, in which case they run together and constitute a froth, such as we shall study in the next chapter. One or more of such clear spaces may be what is called a contractile vacuole, that is to say, a droplet whose surface tension is in unstable equilibrium and is apt to vanish altogether, so that the definite outline of the vacuole suddenly disappears. Again, within the protoplasm are one or more nuclei whose own surface tension draws them in turn into the shape of spheres, outwards through the protoplasm, and stretching far beyond the spherical surface of the cell, run stiff linear threads of modified protoplasm, reinforced in some cases by delicate silicious needles. In either case, we know little or nothing about the forces which lead to their production, and we do not hide our ignorance when we ascribe their development to a radiopolarization. In the case of the protoplasmic filament, we may, if we seek for a hypothesis, suppose that it is somehow comparable to a viscid stream, or liquid vein, thrust or spurted out from the body of the cell. But when it is once formed, this long and comparatively rigid filament is separated by a distinct surface from the neighboring end page 443 protoplasm. That is to say, from the more fluid surface protoplasm of the cell, and the latter begins to creep up the filament, just as water would creep up the interior of a glass tube or the sides of a glass rod immersed in the liquid. It is the simple case of a balance between three separate tensions. One, that between the filament and the adjacent protoplasm. Two, that between the filament and the adjacent water. And three, that between the water and the protoplasm. Calling these tensions respectively TFP, TFW, and TWP equilibrium will be attained when the angle of contact between the fluid protoplasm and the filament is such that cos alpha equals TFDW minus PFP. It is evident in this case that the angle is a very small one. The precise form of the curve is somewhat different from that which, under ordinary circumstances, is assumed by a liquid which creeps up a solid surface, as water in contact with air creeps up a surface of glass. The difference being due to the fact that here, owing to the density of the protoplasm being all but identical with that of the surrounding medium, the whole system is practically immune from gravity. Under normal circumstances, the curve is part of the elastic curve by which that surface of revolution is generated, which we have called, after Plateau, the nodoid. But in the present case, it is apparently a catenary. Whatever curve it be, it obviously forms a surface of revolution around the filament. Since this surface tension is symmetrical around the filament, the latter will be pulled equally in all directions. In other words, the filament will tend to be set normally to the surface of the sphere, that is to say, radiating directly outwards from the center. If the distance between two adjacent filaments be considerable, the curve will simply meet the filament at the angle alpha already referred to. But if they be sufficiently near together, we shall have a continuous catenary curve forming a hanging loop between one filament and the other. And the radial filaments are more or less symmetrically interspaced,
we may have a beautiful system of honeycomb-like depressions over the surface of the organism, each cell of the honeycomb having a strictly defined geometric configuration. In the simpler radial area, the spherical form of the entire organism is equally well marked. And here, as also in the more complicated EPPH 444, the forms of cells. In Heliozoa, such as Actinosphaerium, the organism is apt to be differentiated into layers, so constituting sphere within sphere, whose inner surfaces become the seat of adsorption and the locus of skeletal secretion. One layer at least is close packed with vacuoles, forming an alveolar meshwork, with the configurations of which we shall attempt in another chapter to correlate certain characteristic types of skeleton. In Actinosphaerium, the radial filaments pass through the outer layer and seem to rest on, but do not penetrate the layer below. This must happen if the surface energy between the one plasma layer and the other be less than that between the filament and the water end. A very curious conformation is that of the vibratile collar found in Catosiga and the other conoflagellates, and which we also meet with in the collar cells which line the interior cavities of a sponge. Such collar cells are always very minute, and the collar is constituted of a very delicate film which shews an undulatory or rippling motion. It is a surface of revolution, and as it maintains itself in equilibrium, though a somewhat unstable and fluctuating one, it must be, under the restraining circumstances of its case, a surface of minimal head. But it is not so easy to see what these special circumstances are, and it is obvious that the collar, if left to itself, must shrink or shrivel towards its base, and become confluent with the general surface of the cell. For it has no longitudinal supports, and no strengthening ring at its periphery. But in all these collar cells there stands within the annulus of the collar a large and powerful cilium or flagellum in constant movement. And by the action of this flagellum, and doubtless in part also by the intrinsic vibrations of the collar itself, there is set up a constant steady current in the surrounding water, whose direction would seem to be such that it passes up the outside of the collar, down its inner side, and out in the middle in the direction of the flagellum, and there is a distinct eddy, in which foreign particles tend to be caught. Around the peripheral margin of the collar, page 445E of collared cells. When the cell dies, that is to say, when motion ceases, the collar immediately shrivels away and disappears. It is notable, by the way, that the edge of this little mobile cup is always smooth, never notched or low bed, as in the cases we have discussed on page 390, this latter condition being the outcome of a definite instability, marking the close of a period of equilibrium. But the vibratile collar of Catosiga is in a steady state, its equilibrium, such as it is, being constantly renewed and perpetuated, like that of a juggler's pole, by the motions of the system. Somehow its existence is due to the current motions and to the traction exerted upon it through the friction of the stream which is constantly passing by. In short, I think that it is formed very much in the same way as the cup-like ring of streaming ribbons, which we see fluttering and vibrating in the air current of a ventilating fan. If we turn once more to Mr. Worthington's study of splashes, we may find a curious suggestion of analogy in the beautiful craters encircling a central jet, as the collar of Catosiga encircles the flagellum, which we see produced in the later stages of the splash of a pebble. Figure 140. Another exceptional form of cell and beautiful manifestation of capillarity occurs in trypanosomes, those tiny parasites of the blood which are associated with sleeping sickness and certain other dire maladies of beast and man. These minute organisms consist of elongated solitary cells down one side of which runs a very delicate frill, or undulating membrane, the free edge of which is seen to be slightly thickened, and the whole of which undergoes rhythmical and beautiful wavy movements, when certain trypanosomes are artificially cultivated, for instance, teak. Rotatorium, from the blood of the frog, phases of growth are witnessed in which the organism has no undulating membrane, but possesses a long cilium or flagellum, springing from near the front end and exceeding the whole body in length. Again, in T. lewisi, when it reproduces by multiple fission, the products of this division are likewise, page 446, 430, the forms of cells etch, devoid of an undulating membrane, but are provided with a long, free flagellum. It is a plausible assumption to suppose that, as the flagellum waves about, it comes to lie near and parallel to the body of the cell, and that the frill or undulating membrane is formed by the clear, fluid protoplasm of the surface layer springing up in Fig 1a41. A. Trichomonas muris Hartmann. B. Trichomastic serpentis Dobu. C. Trichomonas angusta Alexeyev. A film to run up and along the flagellum, just as a soap film would form under similar circumstances. This mode of formation of the undulating membrane or frill appears to be confirmed by the appearances shown in Fig 14 here. We have three little organisms closely allied to the ordinary trypanosomes, of which one, Trichomastix B, possesses 4 flagella, and the other two, Trichomonas, apparently 3 only. CFF Minchin, Introduction to the Study of the Protozoa, 1914, p. 293, Fig 127. As in A and C, its outer edge is constituted by the apparently missing flagellum A, which has become attached to the body of the creature at the point C, near its posterior end. And all along its course, the superficial protoplasm has been drawn out into a film between the flagellum A and the adjacent surface or edge of the body B. Moreover, this mode of formation has been actually witnessed and described, though in a somewhat exceptional case. The little flagellate monad Herpetomonas is normally destitute of an undulating membrane, but possesses a single long terminal flagellum, according to Professor D.L.L. McKinnon. The cytoplasm in a certain stage of growth becomes somewhat sticky, a phrase which we may, in all probability, interpret to mean that its surface tension is being reduced. For this stickiness is shown in 2 ways. In the first place, the long body, in the course of its various bending movements, is apt to adhere head to tail, so to speak, giving a rounded or sometimes annular form to the organism, such as has also been described in certain species or stages of trypanosomes. But again, the long flagellum, if it get bent backwards upon the body, tends to adhere to its surface, where the flagellum was pretty long and active. Its efforts to continue movement under these abnormal conditions resulted in the gradual lifting up from the cytoplasm of the body of a sort of pseudo-undulating membrane, figure 143. The movements of this structure were so exactly those of a true undulating membrane that it was difficult to believe one was not dealing with a small, blunt trypanosome. This, in short, is a precise figure 143. Herpetomonas assuming the undulatory membrane of a trypanosome. After D.L. McKinnon, page 448, The Forms of Cells. Description of the mode of development which, from theoretical considerations alone, we should conceive to be the natural, if not the only possible way in which the undulating membrane could come into existence. There is a genus closely allied to Trypanosoma, viz. Trypanoplasma, which possesses 1 free flagellum, together with an undulating membrane, and it resembles the neighboring genus Bodo, save that the latter has 2 flagella and no undulating membrane. In like manner, Trypanosoma so closely resembles Herpetomonas that, when individuals ascribed to the former genus exhibit a free flagellum only, they are said to be in the Herpetomonas stage. In short, all through the order, we have pairs of genera which are presumed to be separate and distinct, viz. Trypanosoma herpetomonas, Trypanoplasma bodo, Trichomastix trichomonas, in which one differs from the other, mainly if not solely, in the fact that a free flagellum in the one is replaced by an undulating membrane in the other. We can scarcely doubt that the 2 structures are essentially one and the same. The undulating membrane of a trypanosome, then according to our interpretation of it, is a liquid film and must obey the law of constant mean curvature. It is under curious limitations of freedom, for by one border it is attached to the comparatively motionless body, while its free border is constituted by a flagellum, which retains its activity, and is being constantly thrown, like the lash of a whip, into wavy curves. It follows that the membrane, for every alteration of its longitudinal curvature, must at the same instant become curved in a direction perpendicular thereto. It bends, not as a tape bends, but with the accompaniment of beautiful but tiny waves of double curvature, all tending towards the establishment of an equipotential surface, which indeed, as it is under no pressure on either side, is really a surface of no curvature at all. And its characteristic undulations are not originated by an active mobility of the membrane, but are due to the molecular tensions which produce the very same result in a soap film under similar circumstances.
Some of the larger spirochates possess a structure so like to the undulating membrane of the trypanosomes that it has led some persons to include these peculiar allies of the bacteria among the flagellate protozoa. But it would seem, according to the weight of view page 449 of undulating membranes, evidence that the spirochat membrane does not undulate and possesses no thickened border or marginal filament, Ranfade. It forms a screw surface, or helicoid, and though we might think that nothing could well be more curved, yet its mathematical properties are such that it constitutes a ruled surface, whose mean curvature is everywhere nil. Precisely such a surface, and of exquisite beauty, may be produced by bending a wire upon itself, so that part forms an axial rod and part winds spirally round the axis, and then dipping the whole into a soapy solution, figure 144. Deinonympha gracilis, lady. A peculiar type is the flattened spiral of Deinonympha, which reminds us of the cylindrical spiral of a spirillum among the bacteria. Here we have a symmetrical figure, whose two opposite surfaces each constitute a surface of constant mean curvature. It is evidently EP page 450I, a figure of equilibrium under certain special conditions of restraint. The cylindrical coil of this spirillum, on the other hand, is a surface of constant mean curvature, and therefore of equilibrium as truly, and in the same sense as the cylinder itself, a very beautiful saddle-shaped surface of constant mean curvature is to be found in the little diatom Campylodiscus, and others, a little more complicated, in the allied genus Cerirella. These undulating and helicoid surfaces are exactly reproduced among certain forms of spermatozoa. The tail of a spermatozoon consists normally of an axis surrounded by clearer and more fluid protoplasm, and the axis sometimes splits up into two or more slender filaments. To surface tension operating between these and the surface of the fluid protoplasm, just as in the case of the flagellum of the trypanosome, I ascribe the formation of the undulating membrane, which we find, for instance, in the spermatozoa of the newt or salamander, and of the helicoid membrane wrapped in a far closer and more beautiful spiral than that which we saw in Spirochaeta, which is characteristic of the spermatozoa of many birds. The undulatory membrane which certain ciliate infusoria exhibit is seemingly a different thing. It is not based on a single marginal flagellum, but consists of a row of fine cilia fused together. The membrane can be broken up by certain reagents into fibrillae, and what is more remarkable, a touch of the microdissection needle may split it into a multitude of cilia, all active but beating out of time. A moment more and they unite again. A moment more, all but disappearing from view as they fuse into the optically homogeneous membrane. They unite as quickly and as intimately as though they were so many liquid jets, and they manifestly partake of fluidity. Neither they nor cilia in general have received, nor seem likely to receive, a simple explanation. Nevertheless, we may see a little light in the darkness after all. It would be overbold to seek for every form of living cell a parallel configuration, due to simple capillary forces, as manifested in drop or bubble or jet. And yet, if the simple cases of sphere or cylinder be the beginning of the story, they assuredly are not the end. The U-pitch 451 of flagellate cells. Pointed and flagellate cell of a monad, one of the least and commonest of microorganisms, is far removed from a simple drop, and all its characters to the microscopist's eye are both generally and specifically those of a living thing. But a drop of water falling through an electric field, as in a thunderstorm, is found to lengthen out to 3 or 4 times as long as it is broad. And then, if the strength of the field increase a little, the prolate drop becomes unstable. It grows spindle-shaped, and suddenly, from one of its 2 pointed spindle ends, the positive end especially, a long and slender filament shoots out to the accompaniment of an electrical discharge. We need not assert that the phenomena are identical, nor that the forces in action are absolutely the same. Yet it is no small thing to have learned that the peculiar conformation of the little flagellate monad has its analog in an electrified drop, and is not unique after all. Before we pass from the subject of the conformation of the solitary cell, we must take some account of certain other exceptional forms, less easy of explanation, and still less perfectly understood. Such is the case, for instance, of the red blood corpuscles of man and other vertebrates. And among the sperm cells of the decapod crustacea, we find forms still more aberrant and not less perplexing. These are among the comparatively few cells, or cell-like structures, whose form seems to be incapable of explanation by theories of surface tension. In all the mammalia, save a very few, the red blood corpuscles are flattened circular discs, dimpled in upon their two opposite sides. This configuration closely resembles that of an India rubber ball when we pinch it tightly between finger and thumb. The form of the corpuscle is symmetrical. It is a solid of revolution, but its surface is not a surface of constant mean curvature. From the surface tension point of view, the blood corpuscle is not a surface of equilibrium. In other words, it is not a fluid drop poised UP 452 in another liquid. Some other force or forces must be at work to conform it, and the simple effect of mechanical pressure is excluded, because the corpuscle exhibits its characteristic shape while floating freely in the blood. It has been suggested that the corpuscle is perhaps comparable to a solid of revolution described about one of Cayley's equipotential curves, such as we have spoken of briefly on page 318. Were the corpuscle a sphere or a thin plate, a gas diffusing inwards would reach all parts equally soon, but the surface would be small in the one case and the volume in the other. In so far as the corpuscle resembles or approaches the equipotential form, we might look on it as a compromise, but however advantageous such a shape might be, and however interesting physiologically, we should be as far as ever from understanding how it was produced, figure 145, in all other vertebrates, from fishes to birds, sluggish or active, warm-blooded or cold. The blood corpuscles have the simpler form of a flattened oval disc with somewhat sharp edges and ellipsoidal surfaces, and this, again, is manifestly not a surface of fluid equilibrium. But there is nothing to choose between the one type and the other in the way of physiological efficiency, nor any apparent need for a refinement of adaptive form in either of them. Two facts are noteworthy in connection with the form of the mammalian blood corpuscle. In the first place, its form is only maintained, that is to say, it is only in equilibrium, in specific relation to the medium in which it floats. If we add water to the blood, the corpuscle becomes a spherical drop, a true surface of minimal area and stable equilibrium. If conversely we add a little salt or a drop of glycerine, the corpuscle shrinks, and its surface becomes puckered and uneven. So far, it merely obeys the laws of diffusion, but the phenomenon is more complex than this, for the spherical form is assumed just as well in various isotonic solutions, leaving on page 453 of blood corpuscles the volume unchanged. A little ammonium oxalate impedes or inhibits the change of form. A little serum brings the spherical corpuscles back to biconcave discs again. We are no longer dealing with simple diffusion, but with phenomena of a very subtle kind. Seco-Anley, the form of the corpuscle can be imitated artificially by means of other colloid substances. Many years ago, Norris made the interesting observation that drops of glue in an emulsion assumed a biconcave form closely resembling that of the mammalian corpuscles. The glue was impure and doubtless contained lecithin. Weymouth Reed made similar emulsions of calaster and oleate, in which the same conformation of the drops or particles is beautifully shown.
And Emil Hatschek has made somewhat similar biconcave bodies by dropping gelatine containing potassium ferrocyanide into copper sulfate or a tannin solution. Here Hatschek believes that his biconcave drops are half-formed vortex rings, arrested by the formation of a semi-permeable membrane. But the explanation does not seem to fit the blood corpuscle. The cholesterin bodies in Weymouth Reed's experiment are such as have a place of their own among Lemon's fluid crystals, and it becomes at least conceivable that obscure forces akin to those of crystallization may be playing their part along with surface energy in these strange but familiar conformations. The case is a hard one in every way. From the physiological point of view, it is difficult and complex enough, for the surface of the corpuscle is equivalent to a semi-permeable membrane, through which certain substances pass freely but not others, for the most part anions and not cations. And accordingly, we have here in life a steady state of osmotic inequilibrium, of negative osmotic tension within.
And to this comparatively simple cause, the imperfect dissension of the corpuscle may be due. Page 454, the forms of cells. Whatever the forces are which make and keep the man's corpuscle a dimpled disc and the frog's a flattened ellipsoid, they seem to be of a powerful kind. When we submit either to great hydrostatic pressure, it tends to become spherical at last, the natural result of uniform pressure over its whole surface. But the pressure necessary to bring this result about is very great indeed. Since the form of the blood corpuscle cannot then be rated as a figure of equilibrium, we must be content to regard it as a steady state, and this, moreover, is all we can say of its physico-chemical condition. The red blood corpuscle, especially the non-nucleated one, is in no ordinary sense alive. It has no power of movement, of reproduction, or of repair. It is a mere hemoglobin-freighted drop of protein. Its own metabolism, apart from its alternate give and take of oxygen, is slight indeed or absent altogether. But all the same, chemical change is continually going on. Anions, like HCO3, pass freely through its walls. Simple cations, like sodium and potassium, find it impermeable, and so, between plasma and corpuscles, the conditions are fulfilled for that steady osmotic state known as a Donan equilibrium. Somehow, but we know not how, a steady state is maintained alike in the corpuscle's osmotic equilibrium and in its form. In mammalian blood, the running together of the round biconcave corpuscles into rouleaux gives a well-known and characteristic picture. When cold, rouleaux are formed slowly. In warm plasma, they form quickly, and while in salt solution, they do not form at all. There is a difference of electrical potential between corpuscles and plasma, and the charged corpuscles tend to repel one another. But they also tend to adhere together, all the more when they meet broadside on, whether by actual stickiness or through surface energy. The attractive forces then overcome the repulsive, and the rouleau is formed. But if the potential be reduced and mutual repulsion reduced with it, then the corpuscles stick together just as they happen to meet. Rouleaux are no longer formed, and ordinary agglutination takes place. Whatever be the precise nature of the phenomenon, the number of rouleaux and the mean number of corpuscles in each is found, after a given time, to obey a certain law, Smoluchowski's law, defining the number of contacts of floating bodies under ordinary physical conditions. Figure 146. Sperm cells of decapod crustacea after Koltsov. A. Inochu scorpio. B. Galatea squamifera. C. Do. After maceration to show spiral fibrillae, the sperm cells of the decapod crustacea exhibit various singular shapes. In the crayfish, they are flattened cells with stiff curve processes real. In Inachus, there are two such circles of stiff processes. In Galatea, we have a still more complicated form with long and slightly twisted processes. Page 456, the forms of cells. In all these cases, just as in the case of the blood corpuscle, the structure alters and finally loses its characteristic form when the constitution of the surrounding medium is changed. Here again, as in the blood corpuscle, we have to do with the important force of osmosis, manifested under conditions similar to those of Pfeffer's classical experiments on the plant cell. The surface of the cell acts as a semi-permeable membrane, permitting the passage of certain dissolved substances, or their ions, and including or excluding others, and thus rendering manifest and measurable the existence of a definite osmotic pressure. Again, in the hen's egg, a delicate yolk membrane separates the yolk from the white. The morphologist looks on it, but as the cell wall of a vast, yolk-laden germ cell, the physiologist sees in it a semi-permeable membrane, the seat of many complex activities. The end and upshot of these last is that a steady difference of osmotic pressure, the equivalent of some 2 atmospheres, is maintained between yolk and white, and yet there is no current flowing through. Somewhere or other in the system, there is a constant metabolic flux, a continuous liberation of energy, a continual doing of work, all leading to the maintenance of a steady dynamical state, which is not equilibrium. In the case of the sperm cells of Inachus, certain quantitative experiments have been performed. The sperm cell exhibits its characteristic conformation while lying in the serous fluid of the animal's body, in ordinary seawater, or in a 5% solution of potassium nitrate, these 3 fluids being all isotonic with one another.
As we alter the concentration of potassium nitrate, the cell assumes certain definite forms corresponding to definite concentrations of the salt, and as a further and final proof that the phenomenon is entirely physical. It is found that other salts produce an identical effect when their concentration is proportionate to their molecular weight. And whatever identical effect is produced, UP 457. A similarly identical effect is produced when these concentrations are doubled or otherwise proportionally changed. No Fig 147. Sperm cells oinactes as they appear in saline solutions of varied density. After Koltsov, thus the following table shows the percentage concentrations of certain salts necessary to bring the cell into the forms I and C of Fig J. 147. In each case, the quantities are proportional to the molecular weights, and in each case, twice the quantity is necessary to produce the effect of C, compared with that which gives rise to the all but spherical form of A. Percent concentration of salts in which the sperm cell of Inachus assumes the form of U page 458, the forms of cells.
Complicated arrangement of more or less rigid or elastic structures in the wall of the cell, which, like the wire framework in Plateau's experiments, restrain and modify the forces acting on the drop. In one form of Plateau's experiment, instead of supporting his drop on rings or frames of wire, he laid upon its surface one or more elastic coils, and then, on withdrawing oil from the center of his globule, he saw its uniform shrinkage counteracted by the spiral springs, with the result that the center of each elastic coil seemed to shoot out into a prominence. Just such spiral coils are figured, after Koltsov, in Figure 148, and they may be regarded as closely akin to those local thickenings or striations, spiral and other which are common in vegetable cells. Figure 148, sperm cell of Dromia, after Koltsov. Physically speaking, the protoplasmic colloids are neither simple nor uniform. We begin by thinking of our cell as a drop of homogeneous fluid, and on this bold simplifying assumption, we account for its form to first, and often to a near approximation. For the cell is largely composed of fluid hydrosols, which are still fluid, however viscous they may be, and still tend towards rounded drop-like configurations. But it has also its hydrogels, which show a certain tenacity, a certain elasticity, a certain reluctance to let their particles move on one another, and of these are formed the scarce distinguishable fibrillae within a host of highly specialized cells, the elastic fibers of a tendon, the incipient cell walls of a plant, the rudiments of many axial and skeletal structures. The cases which we have just dealt with lead us to another consideration. In a semi-permeable membrane through which water passes freely in and out, the conditions of a liquid surface are greatly modified. In the ideal or ultimate case, there is neither surface nor surface tension at all. And this would lead us on page 459 VV of the protoplasmic colloids 443. What to reconsider our position and to inquire whether the true surface tension of a liquid film is actually responsible for all that we have ascribed to it, or whether certain of the phenomena which we have assigned to that cause may not in part be due to the contractility of definite and elastic membranes. But to investigate this question, in particular cases, is rather for the physiologist, and the morphologist may go his way, paying little heed to what is no great difficulty. For in surface tension, we have the production of a film with the properties of an elastic membrane, and with the special peculiarity that contraction continues with the same energy, however far the process may already gone. While the ordinary elastic membrane contracts to a certain extent, and contracts no more. But within wide limits, the essential phenomena are the same in both cases. Our fundamental equations apply to both cases alike, and accordingly. So long as our purpose is morphological, so long as what we seek to explain is regularity and definiteness of form, it matters little if we should happen, here or there, to confuse surface tension with elasticity. The contractile forces manifested at a liquid surface with those which come into play at the complex internal surfaces of an elastic solid. GPH 460, Chapter 6. A note on adsorption, an important corollary to, or amplification of, the theory of surface tension is to be found in the chemico-physical doctrine of adsorption, which means, in a word, the concentration of a substance at a surface by reason of that surface energy, of which we have had so much to say.
Charcoal, with its vast internal surface area of carbonized cell walls, is the commonest and most familiar of absorbents, and of it Du Bois-Reymond first used the name. In its full statement, this subject becomes very complicated and involves physical conceptions and mathematical treatment which go far beyond our range. But it is necessary for us to take account of the phenomenon, even though it be in the most elementary way. In the brief account of the theory of surface tension, with which our last chapter began, it was shown that in a drop of liquid, the potential energy of the system could be diminished, and work manifested accordingly in two ways. In the first place, we saw that, at our liquid surface, surface tension tends to set up an equilibrium of form in which the surface is reduced or contracted, either to the absolute minimum of a sphere, or at any rate to the least possible area which is permitted by the various circumstances and conditions. And if the two bodies which comprise our system, namely the drop of liquid and its surrounding medium, be simple substances, and the system be uncomplicated by other distributions of force, then the energy of the system will have done its work, when this equilibrium of form, this minimal area of surface, is once attained. This phenomenon of the production of a minimal surface area we have now seen to be of fundamental importance in the external Z-page. Morphology of the cell, and especially, so far as we have yet gone, of the solitary cell or unicellular organism. But we also saw, according to Gauss' equation, that the potential energy of the system will be diminished, and its diminution will accordingly be manifested in work, if from any cause the specific surface energy be diminished. That is to say, if it be brought more nearly to an equality with the specific energy of the molecules in the interior of the liquid mass. This latter is a phenomenon of great moment in physiology, and while we need not attempt to deal with it in detail, it has a bearing on cell form and cell structure, which we cannot afford to overlook. A diminution of the surface energy may be brought about in various ways. For instance, it is known that every isolated drop of fluid has, under normal circumstances, a surface charge of electricity in such a way that a positive or negative charge, as the case may be, is inherent in the surface of the drop, while a corresponding charge, of contrary sign, is inherent in the immediately adjacent molecular layer of the surrounding medium. Now, the effect of this distribution, by which all the surface molecules of our drop are similarly charged, is that by virtue of the charge they tend to repel one another, and possibly also to draw other molecules of opposite charge from the interior of the mass, the result being in either case to antagonize or cancel, more or less, that normal tendency of the surface molecules to attract one another, which is manifested in surface tension. In other words, an increased electrical charge concentrating at the surface of a drop tends, whether it be positive or negative, to lower the surface tension. Again, a rise of temperature diminishes surface tension and consequently facilitates the formation of a bubble or a froth. It follows, from the principle of Le Chatelier, that foam is warmer than the fluid of which it is made, and the difference is all the greater the lower the concentration of the foaming, or capillary active, substance. But a still more important case has next to be considered. Let us suppose that our drop consists no longer of a single chemical substance, but contains other substances either in suspension or in solution. Suppose, as a very simple case, that it be a watery, page 462, a note on adsorption, fluid exposed to air and containing droplets of oil. We know that the specific surface tension of oil in contact with air is much less than that of water. And it follows that if the watery surface of our drop be replaced by an oily surface, the specific surface energy of the system will be notably diminished. Now, under these circumstances, it is found that, quite apart from gravity, which might cause it to float to the surface, the oil has a tendency to be drawn to the surface. And again, this phenomenon of molecular attraction or adsorption represents work done, equivalent to the diminished potential energy of the system. In more general terms, if a liquid be a chemical mixture, some one constituent in which, if it entered into or increased in amount in the surface layer, would have the effect of diminishing its surface tension, then that constituent will have a tendency to accumulate or concentrate at the surface. The surface tension may be said, as it were, to exercise an attraction on this constituent substance, drawing it into the surface layer. And this tendency will proceed until at a certain surface concentration, equilibrium is reached, its opponent being that osmotic force which tends to keep the substance in uniform solution or diffusion. In other words, in any two-phase system, a change of concentration at the boundary surface and a diminution of surface tension there accompany one another of necessity. Positive adsorption means negative surface tension, and vice versa. Furthermore, the lowering of surface tension, as by saponin, will permit ceteris paribus, an extension of surface, manifesting itself in froth. Thus, the production of a froth and the concentration of appropriate substances therein are two sides of one and the same phenomenon. In the complex mixtures which constitute the protoplasm of the living cell, this phenomenon of adsorption has abundant play. For many of its constituents, such as fats, soaps, proteins, lecithin, etc., possess the required property of diminishing surface tension. Moreover, the more a substance has the power of lowering the surface tension of the liquid in which it happens to be dissolved, the more will it tend to displace another and less effective substance from the surface layer. Thus, we know that protoplasm always contains fats, not only in visible drops, but also in the finest suspension or colloidal solution. And if under any impulse, such for instance as might arise from the Brownian movement, a droplet of oil be brought close to the surface, it is at once drawn into that surface and tends to spread itself in a thin layer over the whole surface of the cell, but a soapy surface, for instance, in contact with the surrounding water would have a surface tension even less than that of the film of oil, and consequently, if soap be present in the water, it will in turn be absorbed and will tend to displace the oil from the surface pellicle. And all this is as much as to say that the molecules of the dissolved or suspended substance distribute themselves throughout the drop as to lead towards an equilibrium for each small unit of volume, between the superficial and internal energy, or in other words, so as to reduce towards a minimum the potential energy of the system. This tendency to concentration at a surface of any substance within the cell by which the surface tension tends to be diminished, or vice versa, constitutes then the phenomenon of adsorption. And the general statement by which it is defined is known as the Willard-Gibbs or Gibbs-Thompson law, and was arrived at not by experimental but by theoretical and hydrodynamical methods. An assemblage of drops or droplets offers a great extension of surface, but so also does an assemblage of equally minute cells, or page 454, a note on adsorption pores. Both alike are two-phase systems, and in both alike, the phenomenon of adsorption has free play. The occlusion of gases, including water vapor, by charcoal is a familiar phenomenon of adsorption, and is due to the minuteness of the pores only insofar as surface area is increased and multiplied thereby. For surface energy is surface strain, or surface tension times surface area, and is vastly increased by minute subdivision. And surface energy is such that whenever a substance is introduced into a two-phase system, which merely means two things in touch or surface contact with one another, it is apt to concentrate itself on the surface where the two phases meet. Absorption implies uniform distribution, as when a gas is absorbed by a liquid. Adsorption implies a heterogeneous field, and a concentration localized on the surfaces therein. Among the many important physical features or concomitants of this phenomenon, let us take note at present that we need not conceive of a strictly superficial distribution of the adsorbed substance. That is to say, of its direct association with the surface layer of molecules, such as we imagined in the case of an electrical charge, but rather of a progressive tendency to concentrate more and more the nearer the surface is approached. Indeed, we may conceive the colloid or gelatinous precipitate in which, in the case of our protoplasmic cell, the dissolved substance tends often to be thrown down to constitute one boundary layer after another. I.e. is a process which takes time. The tendency to surface concentration is a gradual and progressive one, and will fluctuate with every minute change in the composition of our substance, and with every change in the area of its surface. In other words, it involves, in every heterogeneous substance, a continual instability and a constant manifestation of motion, sometimes in the mere invisible transfer of molecules, but often in the production of visible currents, or manifest alterations in the form or outline of the system. Cellular activity is of necessity associated with cellular structure, page 465 of the boundary state.
even in our simplest interpretation thereof, as a mere increase of surface due to the existence and the multiplication of cells. In the chemistry of the tissues, there may be substances, catalysts, and others,
which exhibit their proper reactions, even though the cells containing them be disintegrated or destroyed. But other processes, oxidation itself among them, are essentially surface actions based on adsorption at the vast cell surface of the tissue. The breaking down of the cell walls, the disintegration of cellular structure in a tissue, brings about a biochemical chaos, a medley of reactions. Cells are not merely there because the tissue has grown by their multiplication. There are physico-chemical reasons, even of an elementary kind, which render the morphological phenomenon of the cell indispensable to physiological action. The physiologist deals with the surface phenomena of the cell in ways undreamed of when I began to write this book. To begin with, the concept of a surface in the old mathematical or quasi-mathematical sense no longer suffices to describe the boundary conditions of even a naked protoplasmic cell. As Rayleigh foretold, and as Irving Langmuir has proved, the boundary state consists of a layer of complex molecules, each one a long array of atoms, all set side by side in an orderly and uniform way. There is not merely a boundary surface between two phases, as the older colloid chemistry supposed, but a boundary layer which itself constitutes a third phase, or interphase, and which part of the surface energy has gone to the making of. Surface energy plays a leading part in modern theories of muscular contraction, and has indeed done so ever since Fitzgerald and D'Arsonval indicated a connection between them some 60 years or more ago. It plays its part handsomely, we may be sure, in the electric pile of the torpedo, where 2 million tiny disks present a U-page 466, a note on adsorption. Vast aggregate of interfacial contact. It gives us a new conception, as Wolfgang Ostwald was the first to show, of the relation of oxygen to the red corpuscles of the blood. But many more, and still more complicated, film reactions are started or intensified by the oriented molecules of the monolayer. i.e., the catalytic action of living ferments, a subject vast indeed, is largely a question of modified adsorption or surface action. The range of bodies so adsorbed is extremely limited. The specific reactions which depend on the bacterium engaged are fewer still, and sometimes a whole class of substances may be adsorbed, and only one of them thrown specifically into action. The physiological, and sometimes lethal, actions of various substances are examples of similar effects. The chemistry of the surface layer in this cell or that may be elucidated by its reactions to various penetrants, and depends somehow on the molecular orientation of the surfaces. And on the potentials associated with the characteristic electric fields which we may suppose to correspond to the particular molecular arrangements. It is the dynamic aspect of the case, the ingresses, egresses, and metabolic changes associated with the boundary layer, which interest the physiologist. He finds the monolayer acting in ways not known in a homogeneous liquid, and adsorption is one of these ways. We keep as much as may be to the morphological side of the case rather than to the physiological, to the static side rather than to the dynamic, to the equilibrium attained rather than to the energies to which it is due. We continue to speak of surface, page 467 energy, and of adsorptive phenomena in a somewhat old-fashioned way, but even with this simplifying limitation, we find them helpful, throwing light upon our subject. In the first place, our preliminary account, such as it is already tantamount to a description of the process of development of a cell membrane or cell wall. The so-called secretion of this cell wall is nothing more than a sort of exudation, or striving towards the surface, of certain constituent molecules or particles within the cell, and the Gibbs-Thompson law formulates, in part at least, the conditions under which they do so. The adsorbed material may range from an almost unrecognizable pellicle to the distinctly differentiated ectosarts of a protozoon, and again to the development of a fully formed cell wall, as in the cellulose partitions of a vegetable tissue. In such cases, the dissolved and adsorptive material has not only the property of lowering the surface tension, and hence of itself accumulating at the surface, but has also the property of increasing the viscosity and mechanical rigidity of the material in which it is dissolved or suspended, and so of constituting a visible and tangible membran The zooglobule around a group of bacteria is probably a phenomenon of the same order. In the superficial deposition of inorganic materials, we see the same process abundantly exemplified. Not only do we have the simple case of the building of a shell or test upon the outward surface of a living cell, as for instance in a foraminifer, but in a subsequent chapter, when we come to deal with spicules and spicular skeletons such as those of the sponges and of the radiolaria, we shall see how highly characteristic it is of the whole process of page 468, a note on adsorption. Spicule formation for the deposits to be laid down just in the interfacial boundaries between cells or vacuoles, and how the form of the spicular structures tends in many cases to be regulated and determined by the arrangement of these boundaries. The so-called collenchima, in which an excess of cellulose is laid down around the angles of contact of adjacent cells in a kind of exaggerated brûlée, is another case in point. No pure liquid ever forms a froth or foam. White of egg is no exception to the rule, for the albumin is somehow changed or denatured and becomes a quasi-solid when we beat it up. But in the frothing liquid, there must always be some admixture present to concentrate on, or be absorbed. The surfaces and interfaces of the other, and this dispersion must go on completely and uniformly, so as to leave the whole system homogeneous. The resulting diminution of surface tension facilitates the subdivision of the bubbles and dispersion of the air, and the adsorbed surface layer gives firmness and stability to the system. The sudden increase of surface diminishes, for the moment, the concentration or thickness of the surface layer. The tension rises accordingly, and the cycle of operations begins anew. In physical chemistry, a distinction is usually drawn between adsorption and pseudoadsorption, the former being a reversible, the latter an irreversible or permanent phenomenon. That is to say, adsorption, strictly speaking, implies the surface concentration of a dissolved substance under circumstances which, if they be altered or reversed, will cause the concentration to diminish or disappear. But pseudoadsorption includes cases doubtless originating in adsorption proper, where subsequent changes leave the concentrated substance incapable of re-entering the liquid system. It is obvious that many, though not all of our biological illustrations, for instance the formation of spicules or permanent cell membranes, belong to the class of so-called pseudoadsorption phenomena. But the apparent contrast between the two is in the main a secondary one, and however important to the chemist, is of little consequence to us. While this brief sketch of the theory of membrane formation is cursory and inadequate, it is enough to show that the physical theory of adsorption tends in part to overturn, in part to simplify page 469 of the formation of membranes. Enormously, the older histological descriptions. We can no longer be content with such statements as that of Strasburger, that membrane formation in general is associated with the activity of the kinoplasm, or that of Harper, that a certain spore membrane arises directly from the astral rays. In short, we have easily reached the general conclusion that the formation of a cell wall or cell membrane is a chemico-physical phenomenon, which the purely objective methods of the biological microscope do not suffice to do. Having reached this conclusion, we may wait patiently and confidently for more. But when the physico-chemical nature of these phenomena is admitted, and their dependence on adsorption recognized, or at least assumed, we have still to remember that the chemist himself is none too certain of his ground. He still finds it hard now and then to tell how far adsorption and direct chemical action go their way, what parts they severally play, what shares they take in their intimate cooperation, on which the formation of a membrane depends, be itself dependent on the power of the adsorbed substance to lower the surface tension. It is obvious that adsorption can only take place when the surface tension is always present. It is for this reason that films or threads of creeping protoplasm show little tendency, or none, to cover themselves with an insisting membrane, and that it is only when, in an altered phase, the protoplasm has developed a positive surface tension, and has accordingly gathered itself up into a more or less spherical body, that the tendency to form a membrane is manifested, and the organism develops its cyst or cell wall. The holes in a globularina shell are there to let the pseudopodia through. They may also be described as due to unequal distribution of surface energies, such as to prevent shell substance from being adsorbed here and there. and at the same time inducing a pseudopodium to emerge. Page 470, 454. A note on adsorption sheet. It is found that a rise of temperature greatly reduces the adsorbability of a substance, and this doubtless comes, either in part or whole, from the fact that a rise of temperature is itself a cause of the lowering of surface tension. We may in all probability ascribe to this fact, and to its converse, or at least associate with it, such phenomena as the encystment of unicellular organisms at the approach of winter, or the frequent formation of strong shells or membranous capsules in winter eggs. Again, since a film or a froth, which is a system of films, can only be maintained by virtue of a certain viscosity or rigidity of the liquid, it may be quickly caused to disappear by the presence in its neighborhood of some substance capable of materially reducing the body. Surface tension, for this substance being adsorbed, may displace from the surface layer a material to which was due the rigidity of the film. In this way, a bathytonic substance such as ether causes most foams to subside, and the pouring oil on troubled waters not only calms the waves, but still more quickly dissipates the foam of the breakers. In a very different order of things, the breaking up of an alveolar network, as at a certain stage in the nuclear division of the cell, may be due in part to just such a cause, as well as to the direct lowering of surface tension by electrical agency. Our last illustration has led us back to the subject of a previous chapter, namely to the visible configuration of the interior of the cell, insofar at least as it represents a dispersed system, coarse enough to be visible. And in connection with this wide subject, there are many phenomena on which light is apparently thrown by our knowledge of adsorption, of which we took little or no account in our former discussion. One of these phenomena is nothing less than that visible or concrete polarity, which we have seen to be in some way associated with the dynamical polarity of the cell. This morphological polarity may be of a very simple kind, as when it is manifested in an epithelial cell by the outward shape of the elongated or columnar cell itself, by the essential difference between its free surface and its attached base, or by the presence in the neighborhood of the former of mucus or other products of the cell's activity. But in a great many cases, this polarized symmetry is supplemented by the presence of various fibrillae, or page 471 of linear arrangements of particles, which in the elongated or monopolar cell run parallel with its axis, but tend to a radial arrangement in the more or less rounded or spherical cell. Of late years, great importance has been attached to these various linear or fibrillar arrangements as they are seen, after staining, in the cell substance of intestinal epithelium, of spermatocytes, of ganglion cells, and most abundantly and frequently of all in gland cells. Various functions have been assigned and hard names given to them. For these structures include your mitochondria and your chondriocytes, both of these being varieties of chondrios. Your Altman's granules, your microsomes, pseudochromosomes, epidermal fibrils, and basal filaments, your archaeoplasm and ergastoplasm, and probably your idiosomes, plasmosomes, and many other histological minutiae. Figure 149. A. B. Chondriosomes in kidney cells prior to and during secretory activity after Barrett. C. Do in pancreas of frog after Matthews. The position of these bodies with regard to the other cell structures is carefully described. Sometimes they lie in the neighborhood of the nucleus itself, that is to say in proximity to the fluid boundary surface, which separates the nucleus from the page 472 cytoplasm. And in this position they often form a somewhat cloudy sphere, which constitutes the nibencern. In the majority of cases, as in the epithelial cells, they form filamentous structures and rows of granules, whose main direction is parallel to the axis of the cell, and which may, in some cases and in some forms, be conspicuous at the one end, and in some cases at the other end of the cell. But I seldom find the histologists attempting to explain, or to correlate with other phenomena, the tendency of these bodies to lie parallel with the axis, and perpendicular to the extremities of the cell. It is merely noted as a peculiarity or a specific character of these particular structures. Extraordinarily complicated and diverse functions have been ascribed to them. Engelmann's fibrolenkinus, which was almost certainly another aspect of the same phenomenon, was held by him and by cytologists like Breda and Heidenhain to be an apparatus connected in some unexplained way with the mechanism of ciliary movement. Meves looked upon the chondrosomes as the actual carriers or transmitters of heredity. Altman invented a new aphorism, omne granulum e granulo, as a refinement of Virchow's or Remarque's, omnis cellula e cellula, and many other histologists, more or less in accord, accepted the chondriosomes as important entities, sui generis, intermediate in grade between the cell itself and its ultimate molecular components. The extreme cytologists of the Munich school, Popov, Goldschmidt, and others, following Richard Hertwig, declaring these structures to be identical with chromidia, under which name Hertwig ranked all extranuclear chromatin, would assign them complex functions in maintaining the balance between nuclear and cytoplasmic material. And the yshramidal hypothesis, as every reader of cytological literature knows, has become a very abstruse and complicated thing. With the help of the binuclearity hypothesis of Chardin and his school, it has given us the chromidial net, the U page 473, chromidial apparatus, the trophochromidia, idiochromidia, gametochromidia, the protogonoplasma, and many other novel and original conceptions. There is apt to be confusion between important and unimportant things, and the very names are apt to vary somewhat in significance from one writer to another. The outstanding fact, as it seems to me, is that physiological science has been heavily burdened in this matter, with a jargon of names and a thick cloud of hypotheses. But from the physical point of view, we see but little mystery in the whole phenomenon. For on the one hand, it is likely enough that these various bodies, by vastly extending the intracellular surface area, may serve to increase the physicochemical activities of the cell, and on the other hand, we ascribe their very existence, in all probability and in general terms, to the clumping together under surface tension of various constituents of the heterogeneous cell contents, and to the drawing out of the little clumps along the axis of the cell towards one extremity or the other, in relation to osmotic currents, as these are set up in turn in direct relation to the phenomena of surface energy and of adsorption. And all this implies that the study of these minute structures, even if it taught us nothing else, at least surely and certainly reveals the presence of a definite field of force. Page 474, a note on adsorption, our next and last illustration of the effects of adsorption, which we owe to the work of the late Professor A.B.E. McCallum of Montreal, is of great importance, for it introduces us to phenomena in regard to which we seem to stand on firmer ground than in some of the foregoing cases, albeit the whole story has not been told. In our last chapter, we were restricted mainly, though not entirely, to a consideration of figures of equilibrium, such as the sphere cylinder or the undulloid. And we began at once to find ourselves in difficulties when we were confronted by departures from symmetry, even in such a simple case as the ellipsoidal yeast cell, and the production of its bud. We found the cylindrical cell of Spirogyra, with its plane partitions or its spherical ends, a simple matter to understand. But when this uniform cylinder puts out a lateral outgrowth in the act of conjugation, we have a new and very different system of forces to account for it. The analogy of the soap bubble or of the simple liquid drop was apt to lead us to suppose that surface tension was on the whole uniform over the surface of the cell, and that its departures from symmetry of form were due to variations in external resistance. But if we have been inclined to make such an assumption, we must now reconsider it and be prepared to deal with important localized variations in the surface tension of the cell. For, as a matter of fact, the simple case of a perfectly symmetrical drop with uniform surface, at which adsorption takes place with similar uniformity, is probably rare in physics, and rarer still, if it exists at all, in the fluid or fluid-containing system, which we call in biology a cell. We have more to do with cells whose general heterogeneity of substance leads to qualitative differences of surface, and hence to varying distributions of surface tension. We must accordingly investigate the case of a cell which displays some definite and regular heterogeneity of its liquid surface, just as amoeba displays a heterogeneity which is complex, irregular, and continually fluctuating in amount and distribution. Such heterogeneity as we are speaking of must be essentially chemical, and the preliminary problem is to devise methods of microchemical analysis, which shall reveal localized accumulations of particular substances within page 475 of McCallum's experiments, the narrow limits of a cell, in the hope that their normal effect on surface tension being ascertained. We may then correlate with their presence and distribution the actual indications of varying surface tension, which the form or movement of the cell displays. In theory, the method is all that we could wish. But in practice, we must be content with a very limited application of it. For the substances which have such action as we are looking for, and which are also actual or possible constituents of the cell, are very numerous. While the means are very seldom at hand to demonstrate their precise distribution and localization, but in one or two cases we have such means, and the most notable is in connection with the element potassium. As McCallum has shown, this element can be revealed in very minute quantities by means of a certain salt, a nitrite of cobalt and sodium. This salt penetrates readily into the tissues and into the interior of the cell. It combines with potassium to form a sparingly soluble nitrite of cobalt, sodium, and potassium. And this, on subsequent treatment with ammonium sulfide, is converted into a characteristic black precipitate of cobaltic sulfide. By this means, McCallum demonstrated years ago the unexpected presence of potassium, that is, of chlorides or other potassium salts, accumulated in particular parts of various cells, both solitary cells and tissue cells. And he arrived at the conclusion that the localized accumulations in question were simply evidences of concentration of the dissolved potassium salts, formed and localized in accordance with the Gibbs-Thompson law. For potassium, as we now know, has a much higher ionic velocity than sodium, and accordingly, the page 476, a note on adsorption cations reach and occupy the adsorbing surfaces of the cell membranes out of all proportion to their abundance in the external media. And we may take it also that our potassium salts, like inorganic substances in general, tend to raise the surface tension and will be found concentrated, therefore, at a portion of the surface where the tension is weak. Figure 150. Adsorptive concentration of potassium salts in 1. A cell of pleurocarpus about to conjugate. 2. Conjugating cells of mesocarpus. 3. Sprouting spores of equistum. After McCallum. In Professor McCallum's figure 150, one of the little green alga pleurocarpus, we see that one side of the cell is beginning to bulge out in a wide convexity. This bulge is, in the first place, a sign of weakened surface tension on one side of the cell, which as a whole had hitherto been a symmetrical cylinder. In the second place, we see that the bulging area corresponds to the position of a great concentration of the potassium salt. While in the third place, page 477, from the physiological point of view, we call the phenomenon the first stage in the process of conjugation. In the figure of mesocarpus, a close ally of Spiragira, we see the same phenomenon admirably exemplified in the later stage. From the adjacent cells, distinct outgrowths are being emitted, where the surface tension has been weakened. Just as the glass blower warms and softens a small part of his tube to blow out the softened area into a bubble, or diverticulum. And in our mesocarpus cells, besides a certain amount of potassium, rendered visible over the boundary, which separates the green protoplasm from the cell sap, there is a very large accumulation precisely at the point where the tension of the originally cylindrical cell is weakening to produce the bulge. But in a still later stage, when the boundary between the two conjugating cells is lost, and the cytoplasm of the two cells becomes fused together, then the signs of potassium concentration quickly disappear. The salt becoming generally diffused through the now symmetrical and spherical zygospore in a spore of equistum, while it is still a single cell, no localized concentration of potassium is to be discerned. But as soon as the spore has divided by an internal partition into two cells, the potassium salt is found to be concentrated in the smaller one, and especially towards its outer wall, which is marked by a pronounced convexity. As this convexity, which corresponds to one pole of the now asymmetrical, or quasi-ellipsoidal spore, grows out into the root hair, the potassium salt accompanies its growth and is concentrated under its wall. The concentration is, accordingly, a concomitant of the diminished surface tension, which is manifested in the altered configuration of the system.
Acinate protozoa obtain their food through suctorial tentacles extruded from the surface of the cell, their extrusion being doubtless due to a local diminution of surface tension. A dense concentration of potassium reveals itself accordingly in the surface film of each tiny tentacle. As the tentacles are withdrawn, their potassium diffuses into the cytoplasm.
When retraction is complete, it is again found in surface concentration, but the surface films on which it now concentrates are the surfaces of the protein spherules, or food vacuoles, within the body of the cell. In the case of ciliate or flagellate cells, there is to be found a P page 478, a note on adsorption, characteristic accumulation of potassium 8 and near the base of the cilia. The relation of ciliary movement to surface tension lies beyond our range, but the fact which we have just mentioned throws light upon the frequent or general presence of a little protuberance of the cell surface just where a flagellum is given off, and of a little projecting ridge or fillet at the base of an isolated row of cilia, such as we find in Vorticellida ide. Yet another of Professor McCallum's demonstrations, though its interest is mainly physiological, will help us somewhat further to comprehend what is implied in our phenomena. In a normal cell of Spirogyra, a concentration of potassium is revealed along the whole surface of the spiral coil of chlorophyll-bearing, or chromatophoral, protoplasm, the rest of the cell being wholly destitute of that substance. The inference being that at this particular boundary between chromatophore and cell sap, the surface tension is small in comparison with any other interfacial surface within the system. And again, in certain minute Chytridia-like fungi, parasitic on Spirogyra and the like, the potassium reaction helps to trace the delicate haustoria of the parasite in their course within the host cell, a clear indication of low surface tension at the surface between. Now, as McCallum points out, the presence of potassium is known to be a factor in connection with the chlorophyll-bearing protoplasm in the synthetic production of starch from CO2 under the influence of sunlight. But we are left in some doubt as to the consecutive order of the phenomena, for the lowered surface tension indicated by the presence of the potassium may be itself a cause of the carbohydrate synthesis, while on the other hand, his synthesis may be attended by the production of substances, for example formaldehyde, which lower the surface tension, and so conduce to the concentration of potassium by the end. All we know for certain is that the several phenomena are associated with one another, as apparently inseparable parts or inevitable concomitants of a certain complex action. When we assert that the form of a cell, in the absence of mechanical pressure, is essentially dependent on surface tension, and even when we make the preliminary assumption that protoplasm is essentially a fluid, we are resting our belief on a general consensus of evidence, rather than on compliance with any one crucial definition. The simple fact is that the agreement of cell forms with the forms which physical experiment and mathematical theory assign to liquid surfaces under the influence of surface tension is so frequently and often so typically manifested that we are led, or driven, to accept the surface tension hypothesis as generally applicable and as equivalent to a universal law.e. The occasional difficulties or apparent exceptions are such as to call for further inquiry, but fall short of throwing doubt on the hypothesis. McCallum's researches introduce a new element of certainty, a nail in a sure place, when they demonstrate that in certain movements or changes of form, which we should naturally attribute to weakened surface tension, a chemical concentration which would naturally accompany such weakening actually takes place. They further teach us that in the cell a chemical heterogeneity may exist of a very marked kind, certain substances being accumulated here and absent there, within the narrow bounds of the system. Such localized accumulations can as yet only be demonstrated in the case of a very few substances, and of a single one in particular. And these few are substances whose presence does not produce, but whose concentration tends to follow a weakening of surface tension. The physical cause of the localized inequalities of surface tension remains unknown. We may assume, if we please, that they are due to the prior accumulation or local production of bodies which have this direct effect, though we are by no means limited to this hypothesis. But in spite of some remaining difficulties and uncertainties, we have arrived at the conclusion, as regards unicellular organisms, that not only their general configuration, but also their UPH 480 departures from symmetry may be correlated with the molecular forces manifested in their fluid or semi-fluid surfaces. Looking at the physiological side, rather than at the morphological, which is more properly our own, we see how very important a cellular system is bound to be, even in respect of its surface area alone. The order of magnitude of the cells which constitute our tissues is such as to give a relation of surface to volume far beyond anything in all the structures or mechanisms devised and fabricated by man. At this extensive surface, capillary energy, a form of energy scarcely utilized by man, plays a large predominant part in the energetics of the organism. Even the warm-blooded animal is not in reality a heat engine. Working as it does at almost constant temperatures, its output of energy is bound by the principle of Carnot to be small. Nor is it an electrostatic machine, nor yet an electrodynamic one. It is a mechanism in which chemical energy turns into surface energy, and working hand in hand, the two are transformed into mechanical energy, by steps which are for the most part unknown. We are led on by these considerations to reflect on the molecular rather than the histological structure of the cell. We have already spoken in passing of monomolecular layers, such as Henri Deveau imagined some 30 years ago, and afterwards obtained, and such as Irving Langmuir has lately made his own. The free surface of every liquid, provided the form and symmetry of its molecules permit, presents a single layer of oriented molecules. Such a surface is no mere limit or a simple boundary. It becomes a region of great importance and peculiar activity in certain cases, when, for instance, protein molecules of vast complexity are concerned. It is then a morphological field with a molecular structure of its own and a dynamical field with energetics of its own. It becomes a frontier where this alien molecule may be excluded and that other be passed through, where some must submit to mere adsorption and others suffer chemical change. In a word, we begin to look on a surface layer or membrane, visible or invisible, as a vastly important thing, a place of delicate operations and a field of peculiar and potent activity. Page 480, chapter 7. The forms of tissues or cell aggregates. We pass from the solitary cell to cells in contact with one another, to what we may call in the first instance cell aggregates, through which we shall be led ultimately to the study of complex tissues. In this part of our subject, as in the preceding chapters, we shall have to consider the effect of various forces. But as in the case of the solitary cell, we shall probably find, and we may at least begin by assuming, that the agency of surface tension is especially manifest and important. The effect of this surface tension will manifest itself in surfaces minimi ire, where, as Plateau was always careful to point out, we must understand by this expression not an absolute but a relative minimum, an area. That is to say, which approximates to an absolute minimum as nearly as the circumstances and material exigencies of the case permit. There are certain fundamental principles or fundamental equations besides those we have already considered, which we shall need in our inquiry. For instance, the case which we briefly touched on page 426, of the angle of contact between the protoplasm and the axial filament in a heliozoan, we shall now find to be but a particular case of a general and elementary theorem. Let us restate as follows, in terms of energy, the general principle which underlies the theory of surface tension or capillarity. A portion of the total energy of the system, that, namely, which we call surface energy, is proportional to the area of the surface of contact. It is also proportional to a coefficient which is specific for each particular pair of substances and is constant for these, save only insofar as it may be modified by changes of temperature or of electrical charge. Equilibrium, which is the condition of minimum potential energy in the system, will accordingly, page 482, be obtained, ceteris paribus, by the utmost possible reduction of the surfaces in contact. When we have three bodies in contact with one another, the same is true, but the case becomes a little more complex. Suppose a drop of some fluid A to float on another fluid B, while both are exposed to air. See, here are three surfaces contact. That of the drop with the fluid on which it floats, and those of air with the one and other of these two, and the whole surface energy, E of the system, consists of three parts resident in these three surfaces, as shown in figure 151, or of three specific energies, E sub a B, E sub a C, E sub BC, the condition of equilibrium, or minimal potential energy, will be reached by contracting those surfaces whose specific energy happens to be large and extending those where it is small, contraction leading to the production of a drop, and extension to a spreading film, floating on water. Turpentine gathers into a drop. Olive oil spreads out in a film. And these, according to the several specific energies, are the ways by which the total energy of the system is diminished and equilibrium attained. A drop will continue to exist provided its own two surface energies exceed per unit area the specific energy of the water-air surface around. That is to say, provided, figure 151, E sub a B plus E sub a C is greater than E sub BC. But if the one fluid happened to be oil and the other water, then the combined energy per unit area of the oil-water and the oil-air surfaces together is less than that of the water-air surface. E sub WA is greater than E sub OA plus E sub OWA. Hence, the oil-air and oil-water surfaces increase. The air-water surface contracts and disappears. The oil spreads over the water. And the drop gives place to a film. In both cases, the total surface area is a minimum under the circumstances of the case, and always provided that no external force, such as gravity, complicates the situation. Page 483 of floating drops. The surface energy of which we are speaking here is manifested in that contractile force, or tension, of which we have had so much to say. In any part of the free water surface, for instance, one surface particle attracts another surface particle, and the multitudinous attractions result in equilibrium body-on. But a water particle in the immediate neighborhood of the drop may be pulled outward, so to speak, by another water particle, but find none on the other side to furnish the counterpole. The pull required for equilibrium must therefore be provided by tensions existing in the other two surfaces of contact. In short, if we imagine a single particle placed at the very point of contact, it will be drawn upon by three different forces whose directions lie in the three surface planes and whose figure 152. Page 484 magnitudes are proportional to the specific tensions characteristic of the three interfacial surfaces. Now, for three forces acting at a point to be in equilibrium, they must be capable of representation in magnitude and direction by the three sides of a triangle taken in order, in accordance with the theorem of the triangle of forces. So, if we know the form of our drop as it floats on the surface, figure 152, then by drawing tangents PR from O, the point of mutual contact, we determine the three angles of our triangle, and know therefore the relative magnitudes of the three surface tensions proportional to its sides. Conversely, if we know the three tensions acting in the directions PRS viz. T, AB, TSC, TBC, we know the three sides of the triangle and know from its three angles the form of the section of the drop. All points round the edge of the drop being under similar conditions. The drop must be circular in its figure that of a solid of revolution. The principle of the triangle of forces is expanded as follows. In an old 17th century theorem called Lamy's theorem, if three forces acting at a point be in equilibrium, each force is proportional to the C9 angle contained between the directions of the other two. That is to say, in figure 152, P to R to S equals C9 phi to C9, or P over C9 phi equals R over C9 equals over CNS. And from this, in turn, we derive the equivalent formulae by which each force is expressed in terms of the other two and of the angle between them. Viz P squared equals R squared plus 2RS cosine phi, etc., etc. From this and the foregoing, we learn the following important and useful deductions. 1. The three forces can only be in equilibrium when each is less than N page 485 of floating drops than the sum of the other two, otherwise the triangle is impossible. In the case of a drop of olive oil on a clean water surface, the relative magnitudes of the three tensions at 15 degrees Celsius are nearly as follows. Water-air surface, 59. Oil-air, 25. Oil-water, 16. No triangle having sides of these relative magnitudes is possible, and no such drop can remain in existence. The three surfaces may be all alike, as when two soap bubbles are joined together on either side of a partition film. The three tensions then are all co-equal. and the three angles are co-equal. That is to say, when three similar liquid surfaces or films meet together, they always do so at identical angles of 120 degrees. Whether our two conjoined soap bubbles be equal or unequal, this is still the invariable rule, because the specific tension of a particular surface is independent of form or magnitude. 3. If all three surfaces be different, as when a fluid drop lies between water and air, the three surface tensions will, in all likelihood, be different, and the two surfaces of the drop will differ in their amount of curvature. Figure 153, 4. If two only of the surfaces be alike, then two of the angles will be alike, and the other will be unlike, and this last will be the difference between 360 degrees and the sum of the other two. A particular case is when a film is stretched between solid and parallel walls, like a soap film within a cylindrical tube. Here, so long as no external pressure is applied to either side, so long as both ends of the tube are open or closed, the angles on either side of the film will be equal. That is to say, the film will set itself at right angles to the sides. Many years ago, Sachs laid it down as a principle which, in page 486, the forms of tissues, has become celebrated in botany under the name of Sachs' rule, that one cell wall always tends to set itself at right angles to another cell wall. But this rule only applies to the case we have just illustrated, and such validity as it possesses is due to the fact that among plant tissues it commonly happens that one cell wall has become solid and rigid before another partition wall impinges upon it. Another important principle arises, not out of our equations, but out of the general considerations which led to them. We saw in the soap bubble that at and near the point of contact between our several surfaces, there is a continued balance of forces carried, so to speak, across the interval. In other words, there is physical continuity between one surface and another, and it follows that the surfaces merge one into another by a continuous curve. Figure 154, Plateau's Brouillon and algal filament. After Berthold, figure 155, whatever be the form of our surfaces and whatever the angle between them, a small intervening curved surface is always there to bridge over the line of contact. And this little fillet, or bourrelet as Plateau called it, is big enough to be a common and conspicuous feature in the microscopy of tissues. Figure 154. A similar bourrelet is clearly seen at the boundary between a floating bubble and the liquid on which it floats, in which case it constitutes a mass annulaire, whose mathematical properties in relation to the form of the nearly hemispherical bubble have been investigated by Vandermets-Brugge. The superficial vacuoles in actinophrys or actinospherium present an identical phenomenon. 6. It is a curious effect or consequence of the bourrelet that a horizontal soap film is never either horizontal or plane, for the bourrelet at its edge is deformed by gravity, and the film is correspondingly inclined upwards where it meets it. Figure 155, B, page 487, of Plateau's Brouillon 7. A bourrelet, a fluid mass connected with a fluid film, is no mere passive phenomenon, but has its active influence or dynamical effect. This was pointed out by Willard Gibbs, and Plateau's Brouillon is more often called nowadays. Gibbs's ring. The ring is continuous in phase with the interior of the film, and fluid is sucked into it from the latter, which thins rapidly, and this, becoming a more potent factor of unrest than gravity itself, leads presently to the rupture of the film. Plateau's explanation of his bourrelet as a surface of continuity is thus but a part, and a small part of the story. In the succulent or parenchymatous tissue of a vegetable, the cells have their internal corners rounded off, figure 156, in a way which might suggest the bourrelet, but comes of another cause, figure 156. Parenchyma of maize, shewing intercellular spaces, where the angles are rounded off the cell walls, tend to split apart from one another, and each cell seems tending to withdraw, as far as it can, into a sphere. And this happens not when the tissue is young and the cell walls tender and quasi-fluid, but later on when cellulose is forming freely at the surface of the cell. The cell walls no longer meet as fluid films, but are stiffening into pellicles. The cells, which began as an association of bubbles, are now so many balls in solid contact or partial detachment, and flexibility and elasticity have taken the place of the capillary forces of an earlier and more liquid phase. Statically, though, not dynamically, that is to say, as a line or surface of continuity in Plateau's sense, Our burle is analogous to the accumulation of sand seen, where two nodal lines cross in a Chladni figure. Vers les endroits où des lignes nodales se coupent, elles s'élargissent toujours, de sorte que la forme des parties vibrantes près de ces endroits n'est pas angulaire, mais plus ou moins arrondie. Souvent formed hyperbole, and in somewhat remoter analogy, we may look on the three corpora arenti as so many burlets, helping to fill the angles where three semilunar valves meet at the base of the great arteries. We may now illustrate some of the foregoing principles, constantly bearing in mind the principles set forth in our chapter on the forms of cells, and especially those relating to the pressure exercised by a curved film. Figure 105y7. Let us look for a moment at the case presented by the partition wall in a double soap bubble. As we have just seen the three films in contact, viz. Outer walls of the two bubbles and the partition wall between being all composed of the same substance and being all alike in contact with air. The three tensions must be equal, and the three films must, in all cases, meet at co-equal angles of 120 degrees. But unless the two bubbles be of precisely equal size and therefore of equal curvature, the tangents to the spheres will not meet the plane of their circle of contact at equal angles. And the partition wall will of necessity be a curved, and indeed a spherical surface. It is only plane when it divides two equal and symmetrical cells. It is obvious from the symmetry of the figure that the centers of the two bubbles and of the partition between are all on one and the same straight line. The two bubbles exert a pressure inwards, which is inversely G page 489 proportional to their radii. That is to say, P to P prime as 1 over R to 1 over R prime. And the partition wall must, for equilibrium, exert a pressure P, which is equal to the difference between these two pressures. That is to say, P equals 1 over R equals 1 over R prime minus 1 over R prime over R prime over R prime over. It follows that the curvature of the partition must be just such as is capable of exerting this pressure. That is to say, R equals R prime over R prime. The partition, then, is a portion of a spherical surface, whose radius is equal to the product divided by the difference of the radii of the two bubbles. If the two bubbles be equal, the radius of curvature of the partition is infinitely great. That is to say, the partition is, as we have already seen, a plane surface. Figure 158. In the typical case of an evenly divided cell, such as a double and co-equal soap bubble, figure 158, where partition wall and outer walls are identical with one another and the same air is in contact with them all, we can easily determine the form of the system. For at any point of the boundary of the partition, P, the tensions being equal, the angles QPP prime, RPPPR are all equal, and each is therefore an angle of 120 degrees. But PQPR being tangents, the centers of the two spheres, or circular arcs in the figure, lie on lines perpendicular to them. Therefore, the radii CPC prime is an angle of 60 degrees, and CPC prime is an equilateral triangle. That is to say, the center of each circle lies on the circumference of the other. The due page 490, the partition lies midway between the two centers, and the diameter of the partition wall, PP prime, is OP over CP equals 60 degrees equals root 3 over 2 equals 0.86, 6 times the diameter of each of the two cells. By integrating between the known values of the meridian section and the plane partition, we should find each half of the double cell, or soap bubble, to be equal to 27/32 of a complete sphere. Therefore, the radius of curvature of each half of the divided bubble is greater than that of a sphere of equal volume, in the ratio of cube root of 32 to cube root of 27 equals 2 times cube root of 4 or 3 equals 1.058 to 1 equals 1 to 0.945, is to the radius of each half, or each product of cell division, as cube root of 54 to cube root of 32 equals 3 times cube root of 2 to 2 times cube root of 4 equals 1.91 to 1 to 1 equals 1 to 0. In the case of 3 co-equal and united bubbles, to which case we shall presently return, each is approximately 5/7 of a whole sphere, and their radii therefore r to the radius of the whole sphere as cube root of 7 to cube root of 5 equals 1 to 0.893 equals 1, 2 in parentheses. When two co-equal bubbles coalesce, the internal pressure due to the tension of the wall and varying inversely as its radius of curvature is diminished in the ratio of 1 to 0.945, or say 5.5. And we begin to see, in the case of three bubbles, that the process proceeds in a geometrical progression, each new coalescence increasing the radius of curvature and diminishing the internal pressure by a constant fraction of the whole. This and other simple corollaries may perchance someday be found useful to the biologist. In the case of unequal bubbles, the curvature of their partition wall is easily determined and is shown in Fig 159. The three films meeting and P being as before. Identical films, the three tangents, PQ, PR, PS, meet at co-equal angles of 120 degrees, and PS produced bisects the angle QPR. PQ, PR are tangents perpendicular to the radii CP, C', and C''P. The radius of the spherical partition PP' is found by drawing a perpendicular to PS and PS. The center C'' is by the symmetry of the figure in a straight line with CC' at Oyen. Whether the partition B or be not a plane surface, it is obvious that its line of junction with the rest of the system lies in a plane. P page 491 of Sachs's rule, and is at right angles to the axis of symmetry. The actual curvature of the partition wall is easily seen in optical section, but in surface view the line of junction is projected as a plane, figure 160, perpendicular to the axis. And this appearance has helped to lend support and authority to Sachs' rule, figure 159, figure 160. As soon as the tensions of the cell walls become unequal, whether from changes in their own substance or in the substances with which they are in contact, then the form alters. If the tension along the partition P diminishes, the partition itself enlarges and the angle QPR increases, until when the tension P is very small compared with Q or R, the whole figure becomes a sphere, and the partition wall, dividing it into two hemispheres, stands at right angles to the outer wall. This is the case when the outer wall of the cell is practically solid. On the other hand, if P begins to increase relatively to Q and R, then the partition wall contracts, and the two adjacent cells become larger and larger segments of a sphere, until at length the system becomes divided into two separate cells. Figure 161, to put the matter still more simply. Let the annex diagrams, figure 161, represent a system of three films, one being a partition, page 492. The wall running between the other two and where the partition T meets the outer wall T'. Let the several tensions or the tractions exerted on a point at their meeting place be proportional to T' and T. Let alpha, beta, and gamma be, as in the figure, the opposite angles. Then 1, if T be equal to T', and T be relatively insignificant, the angles alpha, beta will be of 90 degrees. If T equals T', but be a little greater than T, then T will exert an appreciable traction, and alpha, beta will be more than 90 degrees. Say, for instance, 100 degrees. If T equals T' equals T, then alpha, beta, gamma will all equal 120 degrees. Figure 162, part of a dragonfly's wing. The outer walls of the two cells on either side of the partition will be straight, as well as continuous in the first case, and more or less curved in the other two. We have a vivid illustration, if a somewhat crude one, of the first case in a section of honey, where the waxen walls, which meet one another at 120 degrees, meet the wooden sides of the box at 90 degrees. The wing of a dragonfly shews a seemingly complicated system of veins, which the foregoing considerations help much to simplify. The wing is traversed by a few strong veins, or ribs, more or less parallel to one another, between which finer veins make a page 493 meshwork of cells. These lesser veins being all much of a muchness, and exerting tensions insignificant compared with those of the greater veins, where A2 ribs run so near together that only one row of cells lies between. These cells are quadrangular in form, their thin partitions meeting the ribs at right angles on either side. Where B2 rows of cells are intercalated between a pair of ribs, one row fits into the other by angles of 120 degrees, the result of co-equal tens ions, but both meet the ribs at right angles,
as in the former case. Where, c, the cell rows are numerous, all their angles in common tend to be co-equal angles of 120 degrees, and the cells resolve, consequently, into a hexagonal meshwork. Many spherical cells, such as Protococcus, divide into two equal halves, separated by a plane partition. Among other lower algae akin to Protococcus, such as the nostocs and oscillatoria, in which the cells are embedded in a gelatinous matrix, we find a series of forms, such as are represented in Fig G guide 163, which various conditions depend, according to what we have already learned, upon the relative magnitudes of the tensions at the surface of the cells and the boundary between them. In some cases, Figure 163b, the cells remain spherical because they are merely embedded in the matrix with no other physical continuity between them. Even two soap bubbles do not tend to unite, unless their surfaces be moist, or we put a drop of soap solution between them. Fig 163, filaments or chains of cells in various lower algae. A. Nostoc. B. Anabina. C. Rivillaria. D. Dulcillatoria. In certain other cases, the system consists of a relatively thick-walled tube, subdivided by more delicate partitions, which latter then tend, as in D, to become plane septa set at right angles to the walls. Or again, side walls and septa may be all alike, or nearly so. And then the configuration, as in C on Fig 163, is that of a linear cluster of soap bubbles. In the spores of liverworts, such as Pallia, the first partition, see page 494, the forms of tissues, the equatorial partition in Fig guide 165, it divides the spore into two equal halves, and is therefore a plane surface normal to the surface of the cell. But the next partitions arise near to either end of the original spherical or elliptical cell. And each of these latter will likewise tend to set itself normally to the cell wall. At least the angles on either side of the partition will tend to be identical, and their magnitude will depend on the relative tensions of the cell wall and the partition. The angles will be right angles if the cell wall is solid, or nearly so when the partition is formed, but they will be somewhat greater if, in all probability, rigidity of the cell wall has not been quite attained. In either case, the partition itself will be part of a spherical surface whose curvature will now correspond to the difference of pressures in the two chambers, or cells which it serves to separate. Fig 164, Fig guide 165. Early development of a liverwort Pallia. After Waldman, we have innumerable cases near the tip of a growing filament, for instance, where in like manner the partition wall which cuts off the terminal, more or less conical, cell constitutes a spherical lens, page 495, of cell L partitions. Shaped surface, set normally to the adjacent walls, and the center of curvature is the meeting point of two tangents to the cone. We find such a lenticular partition at the tips of the branches of many Floridae, in Dictyota dichotoma as figured by Rienicki. We have a succession of them. And by the way, where in such cases as these, the tissues happen to be very transparent, we often have a puzzling confusion of lines, figure 166, one being the optical section of the curved partition wall, the other being the straight linear projection of its outer edge to which we have already referred. Figure 166, cells of Dictyota. After Reinke, figure 167, terminal and other cells of Cara. In the conical terminal cell of Cara, we have the same lens-shaped curve, but a little lower down. Where the sides of the shoot are approximately parallel, we have flat transverse partitions, and the form of the cells is more or less what we have been led to expect in the simple case of successive transverse partitions. Figure 167. In the young Antheridia of Cara, figure 168, and in the geometrically similar case of the sporangium, or conidiophore, of Mukhar, we easily recognize the hemispherical form of the septum which shuts off the large spherical cell from the cylindrical filament. Here, in the first phase of development, we should have to take into consideration the different pressures exerted by the single curvature of the cylinder and the double curvature of its spherical cap. And we should find that the partition would have a somewhat low curvature, with a radius less than the diameter of the cylinder, which it would have exactly equaled, but for the additional pressure inwards which it receives from the curvature of the large surrounding sphere.
But as the latter continues to figure 168, young antheridium of Cara, page 496, the forms of tissues, grow, its curvature decreases, and so likewise does the inward pressure of its surface. And accordingly, the little convex partition bulges out more and more. In the ordinary meristematic tissue of a plant, the new partition wall within a dividing cell will generally meet the old walls at right angles to begin with, because its tension is usually small compared to what theirs has become. But as the system grows and the old wall strengthens, the tensions of all three walls become approximately the same, and they tend towards a new position of equilibrium in which, as seen in optical section, they meet as before,
at co-equal angles of 120 degrees. Figure 169. Cambium cells after division, altering from A to B.
The biological facts, which the foregoing considerations go far to explain and account for, have been the subject of much argument and discussion on the part of the botanists. Let me recapitulate in a very few words the history of this long discussion. Some 70 years ago, Hofmeister laid it down as a general, but purely empirical law that the partition wall stands always perpendicular to what was previously the principal direction of growth in the cell, or in most cases perpendicular to the long axis of the cell. This contains an important truth, for it is as much as to say that the cell tends to be divided by the smallest page 497 of cell partitions, partition capable of doing so. 10 years later, Sachs formulated his rule of rectangular section, declaring that in all tissues, however complex, the cell walls cut one another, at the time of their formation, at right angles. Schwendener had found in the final results of cell division a universal system of orthogonal trajectories, and this idea Sachs further developed, introducing complicated systems of confocal ellipses and hyperbolae, and distinguishing between paraclinal walls whose curves approximate to the peripheral contours, radial partitions which cut these at an angle of 90 degrees, and finally anticlines which stand at right angles to the other two. Reinke in 1880 was the first to throw doubt upon this explanation. He pointed out cases where the angle was not a right angle but very definitely an acute one, and he saw in the commoner rectangular symmetry merely what he called a necessary, but secondary result of growth. Within the next few years, a number of botanical writers were content to point out further exceptions to Sachs' rule, and in some cases to show that the curvatures of the partition walls, especially such cases of lenticular curvature as we have described, were by no means accounted for by either Hofmeister or Sachs, while within the same period, Sachs himself, and also Rauber, attempted to extend the main generalization to animal tissues. The simple fact is that Sachs' rule is limited to those many cases where one cell wall grows stiff or solid before another. Page 498 impinges upon it, and, subject to this limitation, the rule is strictly true. While these writers regarded the form and arrangement of the cell walls as a biological phenomenon, with little if any direct relation to ordinary physical laws, or with but a vague reference to mechanical conditions, the physical side of the case was soon urged by others with more or less force and cogency. Indeed, the general resemblance between a cellular tissue and a froth had been pointed out long before. Robert Hooke described the cells within the shaft of a feather as forming a kind of solid or hardened froth, or a congeries of very small bubbles, and Grew described a parenchyma as made by fermentation. Within the days of the cell theory, Melsons made an artificial tissue by blowing into a solution of white of egg. In 1886, Berthold published his Protoplasma Mechanic, in which he definitely adopted the principle of minimal areas, and, following on the lines of Plateau, compared the forms of many cells and the arrangement of their partitions with those assumed under surface tension by a system of weightless films. But as Klebs pointed out in reviewing the book, Berthold was so cautious as to stop short of attributing the biological phenomena to a mechanical cause. They remained for him, as they had done for Sachs, so many phenomena of growth, or properties of protoplasm, in the same year. But while still unacquainted, apparently, with Berthold's work, Leo Herrera published a short but very striking article in which he definitely ascribed to the cell wall, as Hofmeister had already done, the properties of a semi-liquid film and drew from this, as a logical consequence, the deduction that it must assume the various configurations which the law of minimal areas imposes on the soap bubble. So what we may call Herrera's law is formulated as follows. A cell wall, at the moment of its T-page 499 of Herrera's law formation, tends to assume the form which would be assumed under the same conditions by a liquid film destitute of weight. Soon afterwards, Chabray, discussing the segmentation of the Ascidian egg, indicated many ways in which cells and cell partitions repeat the surface tension phenomena of the soap bubble. He came to the conclusion that some, at least, of the embryological phenomena were purely physical, and the same line of investigation and thought was pursued and developed by Robert in connection with the embryology of the mollusca. Driesch also, in a series of papers, continued to draw attention to capillary phenomena in the segmenting cells of various embryos, and came to the conclusion, startling to the embryologists of the time, that the mode of segmentation was of little importance as regards the final result. Lastly, de Wildeman, in a somewhat wider but also vaguer generalization than Herrera's, declared that the form of the cellular framework of plants and also of animals depends, in its essential features, upon the forces of molecular physics. Let us return to our problem of the arrangement of partition films. When we have 3 bubbles in contact, instead of 2 as in the case already considered, the phenomenon is strictly analogous to the former case. The 3 bubbles are separated by 3 partition surfaces, whose curvature will depend upon the relative size of the spheres, and which will be plane if the latter are all of equal size. But whether plane or curved, the 3 partitions will meet one another at angles of 120 degrees. In an axial line, various pretty geometrical corollaries accompany this arrangement. For instance, if Fig 170 represent the 3 associated bubbles in a G page 584, the forms of tissue H Fig 171, page 501 of clustered bubbles. Plan E drawn through their centers, CC prime, C double prime, or what is the same thing? If it represent the base of 3 bubbles resting on a plane, then the line you see double prime, or it's etc., drawn to the centers from the points of intersection of the circular arcs, will always enclose an angle of 60 degrees. Again, figure 171, if we make the angle C double prime UF equal to 60 degrees, and produce UF to meet CC double prime in FF, will be the center of the circular arc which constitutes the partition OU. And further, the 3 points FGH, successively determined in this manner, will lie on one and the same straight line. In the case of 3 co-equal bubbles, as in figure 170b, it is obvious that the lines joining their centers form an equilateral triangle, and consequently that the center of each circle or sphere lies on the circumference of the other 2. It is also obvious that UF is now parallel to CC double prime, and accordingly that the center of curvature of the partition is now infinitely distant, or as we have already said, that the partition itself is plane. The mathematician will find a more elegant way of dealing with our spherical bubbles and their associated interfaces by the method of spherical inversion. 1. Take 3 planes through a line, cutting one another at 60 degrees, and invert from any point, and you have the case of 2 spherical bubbles fused, with their interface also spherical. 2. Take the 6 planes projecting the edges of a regular tetrahedron from its center, and you get by inversion the case of the 3 unequal bubbles and their 3 interfaces. 3. Take these same planes with a bubble added centrally, thus adding a spherical tetrahedron, and inversion gives the general case of 4 fused bubbles and their 6 spherical partitions. When we have 4 bubbles meeting in a plane, figure 172, they would seem capable of arrangement in 2 symmetrical ways, either A, with 4 partition walls intersecting at right angles, or B, with 5 partitions meeting, 3 and 3, at angles of 120 degrees. The latter arrangement is strictly analogous to the arrangement of 3 bubbles in figure 170.
Now, though both of these figures might seem, from their apparent symmetry, to be figures of equilibrium, yet in point of fact, the latter turns out to be of stable, and the former of unstable equilibrium. If we try to bring 4 bubbles into the form A, that arrangement endures only for an instant.
The partitions glide upon one another and intermediate wall springs into existence, and the system assumes the form B. With its 2 page 502, the forms of tissues, triple instead of one quadruple conjunction. In like manner, when 4 billiard balls are packed close upon a table, 2 tend to come together and separate the other 2. Let us epitomize the law of M-minimal areas, and its chief clauses or corollaries in the particular case of an assemblage of fluid films, as was first done by Lamarck. Firstly, and in general, in every liquid system of thin films in stable equilibrium, the sum of the areas of the films is a minimum. From observation and experience, rather than by demonstration, it follows that, 2, the area of each is a minimum under its own limiting conditions, and further that, 3, the mean curvature of any film is constant throughout its whole area. Null. When the pressures are equal on either side and in other cases proportional to their difference. Figure 172. A. An unstable arrangement of 4 cells or bubbles. B. The normal and stable configuration, showing the polar furrow. Less obvious, very important, and likewise subject, but none too easily to rigorous mathematical proof, are the next 2 propositions, both of which have been laid down empirically by Plateau. 4. The films meeting in any one edge are 3 in number. 5. The crests or edges meeting in any one corner are 4 in number, neither more nor less. Lastly, and following easily from these, an arrangement of cells in actual physical contact by means of their intervening boundary walls. We find these general principles in force. We must only bear in mind that for their easy and perfect recognition, we on page 503 must be able to view the object in a plane at right angles to the boundary walls. For instance, in any ordinary plane section of a vegetable parenchyma, we recognize the appearance of a froth precisely resembling that which we can construct by imprisoning a mass of soap bubbles in a narrow vessel with flat sides of glass. In both cases, we see the cell walls everywhere meeting by threes. At angles of 120 degrees, irrespective of the size of the individual cells, whose relative size, on the other hand, determines the curvature of the partition walls. On the surface of a honeycomb, we have precisely the same conjunction between cell and cell of 3 boundary walls meeting at 120 degrees. In embryology, when we examine a segmenting egg of 4 or more segments, we find in like manner, in the majority of cases, if not in all, that the same principle is exemplified. The 4 segments do not meet in a common center, but each cell is in contact with 2 others, and the 3 and only 3 common boundary walls meet at the normal angle of 120 degrees. A so-called polar furrow, the visible edge of a vertical partition wall, joins or separates the 2 triple contacts, precisely as in Fig. 172b, and so gives rise to a diamond-shaped figure, which was recognized more than 100 years ago in a newt or salamander by Rusconi, and called by him a tetracetula. That 4 cells, contiguous in a plane, tend to meet in a lozenge with 3-way junctions and a polar furrow between the cells, is a geometrical theorem of wide bearing. The first 4 cells in a waspiest nest shew it, neither better nor worse than do those of a segmenting ovum, or the ambulacral plates of a sea urchin, or the oosphere of a Oedogonium, giving birth to its 4 zoospores. Going farther afield for an illustration, we find it in the molecules of a viscous liquid under shear, where a group of 4 on page 504 molecules is supposed to slip from one lozenge configuration to an opposite one, passing on the way through the simple cross or square, a configuration of higher energy and less stable equilibrium. The solid geometry of this 4-celled figure is not without interest. If the 2 polar furrows, the one above and the other below, run crisscross, the whole is a more or less flattened and distorted spherical tetrahedron. If they run parallel, then it is a 4-sided lozenge with 2 curved quadrilateral faces and 2 bilateral faces, each bounded by 2 curved edges, like the lists of an orange. Figure 173. Examples of the polar furrow. A. Pollen grains, tetrads of Neodia. B. Egg of hookworm, ankylostoma. C. First cells of a wasp's nest, Pelesis. D. 4-celled stage of Volvox. E. Hair of salvia. In either case, the lozenge configuration is under some restraint to keep its 4 cells in a plane. For a tetrahedral pile or pyramid of 4 spheres would be the simplest arrangement of all.
The polar furrow and the partition of which it forms an edge are, like all the edges and partitions in our associated cells, perfectly definite in dimensions and position, and to draw them to scale and projection is a simple matter. Taking the simplest case, when the radii of all four cells are equal to one another, let CC prime, C double prime, and C triple prime be the centers of the four cells, figure 174. The centers of U page 505 in the polar furrow. Any two are related precisely as though two cells only were conjoined. The centers of three contiguous cells, as CC prime and C double prime, are related as though three only were concerned. And the centers of two opposite cells are situated symmetrically to one another. This is as much as to say that, if there be two bubbles in contact, the addition of a third does not disturb their symmetry. And if there be three in contact, the addition of a fourth leaves the first three likewise in statu quo. Thus, the triangle CC prime, C double prime is equilateral, as we already know. The partition so bisects the side C double prime and the angle C prime C double prime. And the point O is the center of gravity of the triangle. Therefore, OP equals 1/2 of OC double prime and OO prime equals 1/3 of C prime C double prime. Figure 174, the geometric symmetry of a system of four cells. Again, in the triangle CPC double prime, where CC double prime equals RPC double prime equals the square root of 3/2 times R in O prime, the polar furrow equals 1 over the square root of 3 times R. Once again, and in the triangle SOC prime, SC equals R. And so one of the partitions equals 2 over the square root of 3 times R equals twice O prime, the length of the polar furrow. Then, as seen in vertical projection in a system of four co-equal cells, is theoretically just 1/2 that of the four intercellular partitions, and very nearly 3/5 that of a cell radius. It is worthwhile to remark that the universal phenomenon of a polar furrow gives an appearance of bilateral symmetry to every egg or embryo in its four-celled stage, no matter to what kind or class or organism it belongs. Page 506. The forms of tissues. In the four-celled stage of the frog's egg, Robber, an exceptionally careful observer, shews us three alternative modes in which the four cells may be found to be conjoined. Figure 175. In A, we have the commonest arrangement, which is that which we have just studied and found to be the simplest theoretical one. That namely, where a straight polar furrow intervenes and where the partition walls are conjoined at its extremities. 3 by 3. In B, we have again a polar furrow, which is now seen to be a portion of the first segmentation furrow by which the egg was originally divided into two, the four-celled stage being reached by the appearance of the two transverse furrows. In this case, the polar furrow is seen to be sinuously curved, and Robert tells us that its curvature gradually alters. As a matter of fact, it, or rather the partition wall corresponding to it, is gradually setting itself into a position of equilibrium, that is to say, of equiangular contact with its neighbors, which position is already attained, or nearly so, in AV. In C, we have a very different condition with which we shall deal in a moment. Figure 175, various conjunctions of the first four cells in a frog's egg. After Robber, the polar furrow may be longer or shorter, and it may be so minute as to be not easily discernible. But it is quite certain that no simple and homogeneous system of fluid films, such as we are dealing with, is in equilibrium without its presence. In the accounts given, however, by embryologists of the segmentation of the egg, while the polar furrow is depicted in the great majority of cases, there are others in which it has not been seen, and some in which its absence is definitely asserted. The cases where four cells lying page 507 of the polar furrow in one plane meet in a point, such as were frequently figured by the older embryologists, are hard to verify, and sometimes not easy to believe. Considering the physical stability of the other arrangement, the great preponderance of cases in which it is known to occur, the difficulty of recognizing the polar furrow in cases where it is very small, and unless it be specially looked for, and the natural tendency of the draftsman to make an all but symmetrical structure appear wholly so, I was wont to attribute to error or imperfect observation all those cases where the junction lines of four cells are represented, after the manner of Fig. 172, A as a simple cross. As a matter of fact, the simple cross is no very rare phenomenon, even in the frog's egg. But it is a transitory one and unstable. Viscosity and friction may enable it to endure for a while, but the partitions inevitably shift into the stable, three-way configuration. In such a case, the polar furrow manifests itself slowly and, as it were, laboriously. But in the more fluid soap bubble, it does so in the twinkling of an eye. While a true four-rayed intersection or simple cross is theoretically impossible save the transitory and unstable condition, there is another configuration which may closely simulate it, and which is common enough. There are plenty of faithful representations of segmenting eggs in which, instead of the triple junctions in polar furrow, the four cells, and also their more numerous successors, are represented as rounded off and separated from one another by an empty space, or by a little drop of extraneous fluid, evidently not directly miscible with the fluid surface of the cells. Such is the case in the obviously accurate figure which Robert gives, Fig. 175, C of his third mode of conjunction in the four-celled stage of the frog's egg. Here Robert is most careful to point out that the furrows do not simply cross or meet in a point, but are separated by a little space, which he calls the Polgruption, and asserts to be constantly present whensoever the polar furrow or Breechungslinie is not to be discerned. This little interposed space with its contained drop of fluid materially alters the case, and implies a new U page 508 the condition of theoretical and actual equilibrium. For on the one hand, we see that now the four intercellular partitions do not meet one another at all, but really impinge upon four new and separate partitions, which constitute interfacial contacts not between cell and cell, but between the respective cells and the intercalated drop. And secondly, the angles at which these four little surfaces meet the four cell partitions will be determined, in the usual way, by the balance between the respective tensions of these several surfaces. In an extreme case, as in some pollen grains, it may be found that the cells under the observed circumstances are not truly in surface contact, that they are so many drops which touch but do not wet one another, and which are merely held together by the pressure of the surrounding envelope. Figure 176. But even supposing that they are in actual fluid contact, the case from T-He point of view of surface tension presents no difficulty. In the case of the conjoined soap bubbles, we were dealing with similar contacts and with equal surface tensions throughout the system. But in the system of protoplasmic cells, which constitute the segmenting egg, we must make allowance for inequality of tensions between the surfaces where cell meets cell and where, on the other hand, cell surface is in contact with the surrounding medium, generally water or one of the fluids of the body. Remember that our general condition is that, in our entire system, the sum of the surface energies is a minimum, and while this is attained by the sum of the surfaces being a minimum in the case where the energy is uniformly distributed, it is not necessarily so under non-uniform conditions. In the diagram, Figure 176, if the energy per unit area be greater along the contact surface C prime, where cell meets cell, than along CA, page 509 of epidermal tissues, or CB, where cell surface is in contact with the surrounding medium, these latter surfaces will tend to increase and the surface of cell contact to diminish. In short, there will be the usual balance of forces between the tension along the surface CC prime and the two opposing tensions along CA and CB. If the former be greater than either of the other two, the outside angle will be less than 120 degrees. And if the tension along the surface CC prime be as much or more than the sum of the other two, then the drops will merely touch one another, save for the possible effect of external pressure. This is the explanation, in general terms, of the peculiar conditions obtaining in nostoc and its allies. And it also leads us to a consideration of the general properties and characters of the superficial or epidermal layer. While the inner cells of the honeycomb are symmetrically situated, sharing with their neighbors in equally distributed pressures or tension, and therefore all tending closely to identity of form, the case is obviously different with the cells at the borders of the system. So it is with our froth of soap bubbles. The bubbles or cells in the interior of the mass are all alike in general character, and if they be equal in size, are alike in every respect. As we see them in projection, their sides are uniformly flattened and tend to meet at equal angles of 120 degrees. But the bubbles which constitute the outer layer retain their spherical surfaces, just as in the cells of a honeycomb, and these still tend to meet the partition walls connected with them at constant angles of 120 degrees. This outer layer of bubbles, which forms the surface of our froth, constitutes after a fashion what we should call in botany an epidermal layer. But in our froth of soap bubbles, we have, as page 510, the forms of tissues. A rule, the same kind of contact, that is to say, contact with air, both within and without the bubbles. While in our living cell, the outer wall of the epidermal cell is exposed to air on the one side, but is in contact with the protoplasm of the cell on the other, and this involves a difference of tensions, so that the outer walls and their adjacent partitions need no longer meet at precisely equal angles of 120 degrees. Moreover, a chemical change, due perhaps to oxidation or possibly also to adsorption, is very apt to affect the external wall and lead to the formation of a cuticle. And this process, as we have seen, is tantamount to a large increase of tension in that outer wall, and will cause the adjacent partitions to impinge upon it at angles more and more nearly approximating to 90 degrees. The bubble-like or spherical surfaces of the individual cells being more and more flattened in consequence. Fig. 177. A froth with its outer and inner cells or vesicles. Lastly, the chemical changes which affect the outer walls of the superficial cells may extend in greater or less degree to their inner walls also, with the result that these cells will tend to become more or less rectangular throughout, and will cease to dovetail into the interstices of the next subjacent layer. These then are the general characters which we recognize in an epidermis, and we now perceive that its fundamental character simply is that it lies outside, and that its physical characteristics follow, as a matter of course, from the position which it occupies and from the various consequences which that situation entails. In the young shoot, or growing point of a flowering plant, botanists, following Hanstein, find 3 cell layers and call them dermatogen, peribulum, and plerome. The first is an epidermis, such as we have just described. Its cells grow long as the shoot grows long. New partitions cross the lengthening cell and tend to lie at right angles to its hardening walls. And this epidermis, once formed, remains a single superficial layer. The next few layers, the so-called page 511, of epidermal tissues, peribulum, are compressed and flattened between the epidermis with its tense cuticle and the growing mass within. And under this restraint, the cell layers of the peribulum also continue to divide in their own plane or planes. But the cells of the inner mass or plerome, lying in a more homogeneous field, tend to form space-filling polyhedra, 12 or perhaps 14-sided, according to the freedom which they enjoy. In a well-known passage, Sachs declares that the behavior of the cells in the growing point is determined not by any specific characters or properties of their own, but by their position and the forces to which they are subject in the system of which they are a part. This was a prescient utterance and is abundantly confirmed. We have hitherto considered our cells or our bubbles as lying in a plane of symmetry and have only considered their appearance as projected on that plane. But we must also begin to consider them as solids, whether they lie in a plane, like the 4 cells in Fig. 172, or are heaped on one another, like a froth of bubbles or a pile of cannonballs. We have still much to do with the study of more complex partitioning in a plane, and we have the whole subject to enter on of the solid geometry of bodies and close packing, or 3-dimensional juxtaposition. The same principles which account for the development of hexagonal symmetry hold true, as a matter of course, not only of cells in the biological sense, but of any bodies of uniform size and originally circular outline, close packed in a plane. And hence the hexagonal pattern is a very common occurrence, under widely varying circumstances. The curious reader may consult Sir Thomas Browne's quaint and beautiful account, in the Garden of Cyrus, of hexagonal symmetry in plants and animals, which doth neatly declare how nature geometrizeth and observeth order in all things. We come back to very elementary geometry, the first and simplest of all figures in plane geometry, with which for that reason Euclid begins his book, is the equilateral triangle, because 3 straight lines are the least number which enclose 2-dimensional page 512, the forms of tissues. A space and 3 equal sides make the simplest of triangles. But it by no means follows that equilateral or any other triangles combine to form the simplest of polygonal associations or patterns. On the other hand, three straight lines meeting in a point are the least number by which we can subdivide or partition two-dimensional space. The simplest case of all is when the three partitions meet at co-equal angles, and a pattern of hexagons, so produced, is, geometrically speaking, the simplest of all ways in which a surface can be subdivided, the simplest of all two-dimensional space-filling patterns. So it comes to pass that we meet with a pattern of hexagons here and there, and again and again, in all sorts of plane, symmetrical configurations, from a soapy froth to the retinal pigment, from the cells of the honeycomb to the basaltic columns of Staffa and the Giant's Causeway. We pass to solid geometry and arrive by similar steps at an analogous result. Four plane sides are now the least number which enclose space, and next to the sphere itself, the regular tetrahedron is the first and simplest of solids. But its simplicity is that of a solitary or isolated figure, and tetrahedra do not combine to fill space at all, but as the partitioning of an equilateral triangle was the first step towards a symmetrical partitioning of two-dimensional space. So we draw from the regular tetrahedron a first lesson in the partitioning of space of three dimensions, and as three lines meeting in a point were needed to partition two-dimensional space. So here, for three-dimensional space, we need four. The simplest case is, as before, when these meet at co-equal angles, but we do not see quite so easily what those four co-equal angles are. For as the center of symmetry of our equilateral triangle was defined by three lines, bisecting its three angles and meeting one another in a point at co-equal angles of 120 degrees. So in our regular tetrahedron, four straight lines, running symmetrically inwards from the four corners, meet in a point at co-equal angles and again define the center of symmetry. If we make, as Plateau made, a wire tetrahedron, and dip it into soap solution, we find that a film has attached itself to each of the six wires which constitute the little tetrahedral cage, that these six films meet 3 by 3 in four edges, and that these four edges meet at co-equal angles in a point which is the centroid or center of symmetry or center of gravity of the system. G page 513 of tetrahedral symmetry. This is the center of symmetry not only for our tetrahedron, but for any close-packed tetrahedral aggregate of co-equal spheres. We meet with it over and over again in a pile of cannonballs, a froth of soap suds, a parenchyma of cells, or the interior of the honeycomb. Moreover, in the actual demonstration by soap films of this tetrahedral symmetry, we see realized all the main criteria laid down by Plateau and by Lamarre for a system minime irae. 3 films and no more meet in an edge. 4 fluid edges and no more meet in a point, just as 3 wire edges and 1 fluid edge met in a point at each corner of the experimental figure. Lastly, the symmetry of the whole configuration is such that the 3 fluid films meeting in an edge, or the 4 fluid edges meeting in a point, all do so at co-equal angles. Figure 178. A regular tetrahedron with its center of symmetry. In the plane configuration, we saw, without more ado, that the angles of symmetry were the co-equal angles of 120 degrees. But the 4 co-equal angles between the 4 edges which meet at the center of our tetrahedron require a little more consideration. If in our figure of a regular tetrahedron, figure 178, O be the centroid, and we produce an O to P, the center of the opposite side, BCD, it may be shown that the line of P is so divided that a O equals 3OP and a O equals BO equals DO equals DO. For let 4 equal weights be put at the 4 corners of the tetrahedron, A, B, C, D. The resultant of the 3 at B, C, D is equivalent to 3W at P, the center of symmetry of the equilateral triangle. Page 514, the forms of T. The resultant of all 4 is equal to the resultant of W at A and 3W at P. It lies, therefore, on the straight line of P and at the point O, such that O equals 3OPL. Therefore, in the triangle PCD, as in the other 3 similar triangles in the figure, cosine PCOD equals minus 1/3. Our tables tell us that the angle POD, whose trigonometrical value is a very simple one of cosine POD equals 1/3, has, in degrees and minutes to the nearest second, the seemingly less simple value of 70 degrees, 31 minutes, 43 seconds. And its supplement, the angle OD,
has the corresponding value of 109 degrees, 28 minutes, 16 seconds. This latter angle, then, of 109 degrees, 28 minutes, 16 seconds, or very nearly 109 degrees and a half, is the angle at which, in this and throughout every other three-dimensional system of liquid films, the edges of the partition walls meet one another. It is the fundamental angle in simple homogeneous partitioning of three-dimensional space. It is an angle of statical equilibrium, an angle of close packing, an angle of repose. In the simplest of carbon compounds, the molecule of marsh gas, CH4, we may be sure that this angle governs the arrangement of the H atoms. It determines the relation of the carbon atoms one to another in a diamond. Simplest of crystal lattices, it defines the intersections of the bubbles in a froth, and of the cells in the honeycomb of the bee. It is sometimes called the tetrahedral angle. It might be better called, for a reason we shall see presently, Maraldi's angle. The whole story is less a physical than a mathematical one, for the phenomena do not depend on surface tension, nor on any other physical force, but on such relations between surface and volume as are involved in the properties of space. If we take 4 little elastic balloons, half fill them with air, smear them with glycerine to lessen friction, place them in a bottle and exhaust the air therein, they will expand, adjust themselves together, and group themselves in a tetrahedral configuration, whose partition walls, edges, and center of symmetry are just those of our experiment of the soap films. This characteristic angle, though it leads in ordinary angular measurement to an endless decimal of a second, is nevertheless a very simple and perfectly definite magnitude. It is a strange property of number that it fails to express certain simple and definite magnitudes, such as pi, or the square root of 2, or the square root of 2, or this four-fold angle made by 4 lines meeting symmetrically in three-dimensional space. It is not these magnitudes that are peculiar, it is number itself that is so. In all of these cases, we have to import a new symbol. And in this case, when we page 515 of hexagonal symmetry, draw it not from arithmetic, but from trigonometry, and define our angle as cos minus 1/3. Nothing can or need be more precise or simpler. We may put the same thing a little differently and say that number itself fails us now and then to express what we want, although we have all the 10 digits and their apparently endless permutations at our command. In such a deadlock, we have only to bring one new symbol, one new QUentity into use, and at once a wide new field is open to us. And the plane angle of 120 degrees, we may construct a great variety of figures, plane and solid, which becomes still more complex and varied when we consider associations of unequal as well as of co-equal cells, and thereby admit curved as well as plane intercellular partitions. Let us consider some examples of these, beginning with such as we need only consider in reference to a plane. Figure 179, diagram of hexagonal cells. After Benani, let us imagine a system of equal cylinders or equal spheres in contact with one another in a plane, and represented in section by the equal and contiguous circles of figure 179.
I borrow my figure from an old Italian naturalist, Benani, a contemporary of Borelli, of Ray and Willoughby, and of Martin Lister, who dealt with this matter in a book chiefly devoted to molluscan shells.
Page 516. It is obvious, as a simple geometrical fact, that each of these co-equal circles is in contact with 6 others around. Imagine the whole system under some uniform stress, of pressure caused by growth or expansion within the cells, or due to some uniformly applied constricting pressure from without. In these cases, the 6 points of contact between the circles in the diagram will be extended into lines, representing surfaces of contact, in the actual spheres or cylinders, and the equal circles of our diagram will be converted into regular and co-equal hexagons. The result is just the same so far as form is concerned, so long as we are concerned only with a morphological result, and not with a physiological process, whatever be the force which brings the body together. For instance, the cells of a segmenting egg lying within their vitelline membrane, or within some common film or ectoplasm, are pressed together as they grow, and suffer deformation accordingly. Their surface tends towards an area minima, but we need not even inquire in the first instance whether it be surface tension, mechanical pressure, or what not other physical force, which is the cause of the phenomenon. The production by mutual interaction of polygons, which become regular hexagons when conditions are perfectly symmetrical, is beautifully illustrated by Bernard's tourbillons cellulaires and also in some of Leduc's diffusion experiments. In these latter, a solution of gelatine is allowed to set on a plate of glass, and little drops of weak potassium ferrocyanide are then let fall at regular intervals upon the gelatine. Immediately, each little drop becomes the center of a system of diffusion currents, and the several systems conflict with and repel one another, so that presently each little area becomes the seat of a to and fro current system, outwards and back again, until the concentration of the field becomes equalized and the current ceases. When equilibrium is attained and when the gelatin layer is allowed to dry, we have an artificial tissue of EPIG 517, one of hexagonal symmetry 580. An artificial tissue formed by colored drops of sodium chloride solution diffusing in a less dense dot solution of the same salt. After Leduc, Fig 181. An artificial cellular tissue formed by the diffusion in gelatine of drops of a solution of potassium ferrocyanide. After Leduc, page 518, hexagonal cells, which simulate an organic parenchyma very closely. And by varying the experiment in ways which Leduc describes, we may imitate various forms of tissue and produce cells with thick walls, or with thin cells in close contact, or with wide intercellular spaces, cells with plane or with curved partitions, and so forth. James Thomson, Kelvin's elder brother, had observed nearly 60 years ago a curious tessellated structure on a liquid surface, to wit, the soapy water of a wash tub. The eddies and streaks of swirling water settled down into a cellular configuration, which continued for hours together to alter its details. Small areolas disappeared, large ones grew larger, and subdivided into small ones again, with few and transitory exceptions, 3 partitions, and no more met at every node of the meshwork. And, as it seems to me, the subsequent changes were all due to such shifting of the lines as tended to make the 3 adjacent angles more and more nearly co-equal with one another. The obvious effect of this being to make the pattern more and more regular hexagonal. In a not less homely experiment, hot water is poured into a shallow tin and a layer of milk run in below. On blowing gently to cool the water, holes, more or less close packed and evenly interspaced, appear in the milk. They show how cooling has taken place, so to speak, in spots, and the cooled water has descended in isolated columns. Bernard's tourbillons cellulaires, set up in a thin liquid layer, page 519 of Bernard's experiment, are similar to but more elegant than James Thomson's tessellated patterns, and both of them are in their own way still more curious than M.B. Leduc's. For the latter depend on centers of diffusion artificially inserted into the system and determining the number and position of the cells, while in the others the cells make themselves. In Bernard's experiment, a thin layer of liquid is warmed in a copper dish. The liquid is under peculiar conditions of instability, for the least fortuitous excess of heat here or there would suffice to start a current, and we should expect the whole system to be highly unstable and unsymmetrical. But if all be kept carefully uniform, small disturbances appear at random all over the system. A current ascends in the center of each, and a steady state, if not a stable equilibrium, is reached in time when the descending currents, impinging on one another, mark out a cellular system. If we set the fluid gently in motion to begin with, the first cell divisions will be in the direction of the flow. Long tubes appear, or vessels, as the botanist would be apt to call them. As the flow slows down, new cell boundaries appear, at right angles to the first and at even distances from one another. Parallel rows of cells arise. And this transitory stage of partial equilibrium or imperfect symmetry is such as to remind the botanist of his cambium tissues, which are, so to speak, a temporary phase of histological equilibrium. If the impressed motion be not longitudinal but rotary, the first lines of demarcation are spiral curves, followed by orthogonal intersections. Whether we start with liquid in motion or at rest, symmetry and uniformity are ultimately attained. The cells draw towards uniformity, but 4, 5, or 7-sided cells are still to be found among the prevailing hexagons. The larger cells grow less, the smaller enlarge or disappear. Where 4 partition walls happen to meet, they shift till only 3 converge. The sides adjust themselves to equal lengths.
The angles also to equality. In the final stage, the cells are hexagonal prisms of definite dimensions, which depend on temperature and on the nature and thickness of the liquid layer. Molecular forces have not only given us a definite cellular pattern, but also a fixed cell size. Solid particles in the fluid come to rest in symmetrical positions. If they be heavier, they accumulate in little isolated heaps, each in end page 520, the forms of tissues, the focus or axis of a cell. If they be lighter, they drift to the boundaries, then towards the nodes, where they tend to form triradiate figures like so many triradiate spicules. But if they be in very fine suspension, a curious thing happens. For as they are carried round in the vortex, the lowermost layer of liquid, next to the solid floor, keeps free of particles, and this dust-free coat, rising in the axis of the cell, and descending at its boundary walls, surrounds an inner vortex to which the suspended particles are confined. The cell contents have, so to speak, become differentiated into an ectoplasm, and an analogy appears with the phenomenon of protoplasmic rotation, where the outer layer of a cell tends to be free from granules. Figure 182. Bernard patterns in smoke. A at rest. B under shear. When bright glittering, particles are used for the suspension, such as graphite or butterfly scales. Beautiful optical effects are obtained, deep shadows marking the outlines and the centers of the cells. Lastly, and this is by no means the least curious part of the phenomenon, the free surface of the liquid is not plane, but each little cell is found to be dimpled in the center and raised at the edges in a surface of very complex curvature. And there is a curious pulsation in the flow, especially when waxes are used, G page 521-1, of Bernard's experiment. Ringing the changes on Bernard's experiment, we may use unstable layers of various liquids or gases, or even a thin layer of smoke between a hot plate and a cold figure, 182. The smoke will form waves and folds and rolling clouds. Then, with increasing and more symmetrical instability, polygonal or hexagonal prisms. In all these configurations, we may deform or shear by sliding one plate over the other. Familiar cloud patterns, as of a dappled or mackerel sky, can be imitated in this way. When the hexagonal prisms have been developed, it is found that a steady shear deforms them into a well-known curvilinear tessellated pattern, figure 183. And this may be sheared again into hexagons, oriented in an opposite direction to the first. The very same pattern occurs now and then in organisms as a deformation of what is normally a pattern of hexagons. Figure 184, page 525-506, the forms of tissues chitch. We learn from these experiments of Bernard and others how similar distributions of force and identical figures of equilibrium may arise through different physical agencies. We see that patterns closely analogous to those of living cells and tissues may be due to very different causes, and we may be led to scrutinize anew with an open mind various histological configurations whose origin is doubtful or obscure. The hotness shells of certain water fleas, Cladocera, are beset with a roughly hexagonal pattern, and each little chitinous polygon is supposed to correspond to, and to be formed by, an underlying hypodermis cell. But we presently discover that the existence of these hypodermis cells is merely deduced from the polygons themselves, and from a coincident E-page 523 of hexagonal symmetry. Change is from a more to a less probable configuration, the entropy is diminished, and if we apply no further pressure, the tension of the films adjusts itself again, and the system recovers its former symmetry. Cells seem diamond-shaped, but looking closer, we see that each is in contact, usually, with 6 others. They are not rhombs or diamonds, but elongated hexagons, pulled out long by the growth of the vessel and the elastic traction of its walls. The sides of each cell are curiously waved, and a simple experiment explains this phenomenon. If we make a froth of white of egg upon a stretched sheet of rubber, the cells of the froth will tend to assume their normal hexagonal pattern, but relax the elastic membrane, and the cell walls are thrown into beautiful sinuous or wavy folds. Figure 186. Sinuous outlines of epithelial cells. A. Endothelium of a blood vessel. B. Epidermis of impatiens. C. Epidermal cells of a grass, Festica. The frost cells cannot contract as the rubber does which carries them, nor can the epithelial cells contract as does the muscular coat of the blood vessel. In both cases alike, the cell walls are obliged to fold or wrinkle up from lack of power to shorten. The epithelial cells on the gills of a mussel are wrinkled after the same fashion, but the more coarsely sinuous outlines of the epithelium in many plants is another story, and not so easily accounted for. The hexagonal pattern is illustrated among organisms in countless cases, but those in which the pattern is perfectly regular, i.e. page 524, the forms of tissues. Reason of perfect uniformity of force and perfect equality of the individual cells are not so numerous. The hexagonal cells of the pigmented epithelium of the retina are a good example. Here we have a single layer of uniform cells, reposing on the one hand upon a basement membrane, supported behind by the solid wall of the sclerotic, and exposed on the other hand to the uniform fluid pressure of the vitreous humor. The conditions all point and lead to a symmetrical result. The cells, uniform in size, are flattened out to a uniform thickness by uniform pressure, and their reaction one upon another converts each flattened disc into a regular hexagon. An equally symmetrical case, one of the first known examples of an epithelium, is to be found on the inner wall of the amnion, where, as Theodor Schwann remarked, die sechseckige Plättchen sind sehr schön und groß. Figure 187, epidermis of Giardia. After Goebel, in an ordinary columnar epithelium, such as that of the intestine, again the columnar cells are compressed into hexagonal prisms, but here the cells are less uniform in size. Small cells are apt to be intercalculated among the larger, and the perfect symmetry is lost accordingly. But obviously, wherever we have, in addition to the forces which tend to produce the regular hexagonal symmetry, some other component arising asymmetrically from growth or traction, then our regular hexagons will be distorted in various simple ways. Thus, in the delicate epidermis of a leaf or young shoot, we begin with hexagonal cells of exquisite regularity, on which, however, subsequent longitudinal growth may impose an equally simple and symmetrical deformation or polarity. Figure 187. In the growth of an ordinary dicotyledonous leaf, we see reflected in the form of its cells the tractions irregular, but on the whole longitudinal, which growth has superposed on the tensions of the U-page 525 partition walls, figure 188. In the narrow elongated leaf of a monocotyledon, such as a hyacinth, the elongated, apparently quadrangular cells of the epidermis appear as a necessary consequence of the simple form to the leaf as a whole. In all these cases alike, however, the rule still holds that only three partitions in surface, view, or plane projection meet in a point, and near their point of meeting, the walls are manifestly curved for a little way, so as to permit the triple conjunction to take place at or near the co-equal angles of 120 degrees, after the fashion described above. Figure 188, epidermal cells from leaf of Eladia canadensis. After Berthold. Briefly speaking, wherever we have a system of cylinders or spheres associated together with sufficient mutual interaction to bring them into complete surface contact, there in section or in surface view, we tend to get a pattern of hexagons. In thickened cells or fibers of bast or wood, the sclerenchyma of vegetable histology, the hexagonal pattern is all but lost, and we see in cross-section the more or less circular transverse outlines of elongated and tapered cells. Looking closer, we see that the primitive cell walls preserve their angular contours and show much as usual an hexagonal pattern with only such irregularities as follow from the unequal sizes of the associated cells. But when these primary walls are once laid down, the secondary deposits which follow them are under different conditions, and these obey the law of minimal areas in their own way. By filling up the angles of the primary cell, and by continuing to grow inwards in concentric and more nearly circular rings. While the formation of an hexagonal pattern on the basis of ready formed and symmetrically arranged material units is a very common, and indeed the general way, it does not follow that there are not others by which such a pattern can be obtained. For instance, if we take a little triangular dish of mercury and set it vibrating, either by help of a tuning fork or by simply tapping on the sides, we shall have a series of little waves or ripples starting inwards from each of the three faces.
And the intercrossing or interference of these three sets of waves produces crests and hollows, and intermediate points of no disturbance, whose loci are seen as a beautiful pattern of page 526 hexagons. It is possible that the very minute and astonishingly regular pattern of hexagons, which we see on the surface of many diatoms, may be a phenomenon of this order. The same may be the case also in Arcella, where an apparently hexagonal pattern is found not to consist of simple hexagons, but of straight lines in three sets of parallels, the lines of each set making an angle 60 degrees with those of the other two sets. We must also bear in mind, in the case of the minuter forms, the large possibilities of optical illusion. For instance, in one of Abbe's diffraction plates, a pattern of dots set at equal interfaces is reproduced on a very minute scale by photography. But under certain conditions of microscopic illumination and focusing, these isolated dots appear as a pattern of hexagons. A symmetrical arrangement of hexagons, such as we have just been studying, suggests various geometrical corollaries, of which the following may be a useful one. We sometimes desire to estimate the number of hexagonal areas or facets in some structure where these are numerous. Such, for instance, see as the cornea of an insect's eye, or in the minute pattern of hexagons on many diads. An approximate enumeration is easily made as follows. For the area of a hexagon, if we call delta the short diameter, that namely which bisects two of the opposite sides, is delta squared times the square root of 3 over 2, the area of a circle being d squared times pi over 4. Then if the diameter of a circular area including hexagons, the area of that circle equals in delta squared times pi over 4. And dividing this number by the area of a single hexagon, we obtain for the number of areas in the circle, each equal to a hexagonal facet, the expression n squared times pi over 4 times 2, over the square root of 3 equals 0.907 n squared, or 9/10 n squared nearly. This calculation deals not only with the complete facets, but with the areas of the broken hexagons at the periphery of the circle. If we neglect these latter, and consider our whole field as consisting of successive rings of hexagons about a central one, we obtain a simpler rule. For obviously, around our central hexagon there stands a zone of 6, and around these page 507 of hexagonal patterns. Figure 189, a diatom, trisuration, showing pattern of hexagons times 300, from O, Prochnow, Formenkenster Natur, a zone of 12, and around these a zone of 18, and so on. And the total number, excluding the central hexagon, is accordingly, for one zone, 6 equals 3 times 1 times 2 equals 6 times 1. For two zones, 18 equals 3 times 2 times 3 equals 6 times 3. For three zones, 36 equals 3 times 4 equal 6 times 6. For 4 zones, 60 equals 3 times 4 times 5 equals 6 times 10. For 5 zones, 90 equals 3 times 5 times 6 equals 6 times 15, and so forth. If n be the number of zones, and if we add 1 to the above numbers for the odd central hexagon, then the rule is that the total number h equals 3n times, and plus 1 plus 1. Thus, if in a preparation of a fly's cornea, I can count page 528 the forms of tissues, 25 facets in a line from a central one, the total number in the entire field is open parenthesis 3 times 25 times 26 close parenthesis plus 1 equals 1951. The electrical engineer is dealing with the self-same problem when he finds he can pack 6 plus 18 plus 36 plus and so on wires around a central wire to form a multiple cable of 1, 2, and 3 concentric strands. He counts them by the same formula in the simpler form of 6t plus 1, where t is a triangular number, 1, 3, 6, 10, etc., corresponding to the number of strands. Thus, 1951 equals 6 times 325 plus 1. 325 being the triangular number of 25, 1 plus 2 plus 3 plus, and so on. Plus 25. We have many varied examples of this principle among corals, wherever the polyps are in close juxtaposition, with neither empty space nor accumulations of matrix between their adjacent walls. Favosites gothlandica, for instance, furnishes us with an excellent example. In the great genus Lithostrotion, we have some species which are massive and others which are fasciculate, In other words, in some, the long cylindrical corallites are closely packed together, and in others they are separate and loosely bundled, figure 190. In the former, the corallites are squeezed into hexagonal prisms, while in the latter they retain their cylindrical form. Where the polyps are comparatively few and so have room to spread, the mutual pressure ceases to work, or only tends to push them asunder, letting them remain circular in outline, for example, the cosmilia, where they vary gradually in size. As for instance in Sathophyllum hexagonum, they are more or less hexagonal but are not regular hexagons, and where there is greater and more irregular variation in size, the cells will be on the average hexagonal. But some will have fewer and some more sides than 6, as in the annexed figure of Arachnophyllum, figure 192, where larger and smaller cells corresponding to two different kinds of zooids are mixed together. We may get various results. If the larger cells are numerous enough, page 529 of hexagonal symmetry, to be more or less in contact with one another, for example, various monticulipari, they will be irregular hexagons, while the smaller cells between them will be crushed into all manner of irregular angular forms. Figure 190. Lithostrotion Martini. After Nicholson, figure 191. Cyathophylum hexagonum from Nicholson after Zittel. Figure 192. Arachnophyllum pentagonum after Nicholson. Figure 193. Heliolites. Afterwards, if on the other hand the large cells are comparatively few and are large and strong-walled compared with their smaller neighbors, then the latter alone will be squeezed into hexagons, while the larger ones will tend to retain their circular outline undisturbed. For example, Heliopora, Heliolites, etc., figure 193, page 530. The forms of tissues. When, as happens in certain corals, the peripheral walls or thicae of the individual polyps remain undeveloped, but the radiating septa are formed and calcified, then we obtain new and beautiful mathematical configurations. Figure 194. For the radiating septa are no longer confined to the circular or hexagonal bounds of a polypite, but tend to meet and become confluent with their neighbors on every side, and, tending to assume positions of equilibrium or of minimum under the restraints to which they are subject, they fall into congruent curves, which correspond in a striking manner to lines running in a common field of force between a number of secondary centers. Similar patterns may be produced in various ways by the play of osmotic or magnetic forces. Figure 194. Surface views of corals with undeveloped dithiae and confluent septa. A. Tamistrea. B. Commissaris, from Nicholson after Zittel. And a very curious case is to be found in those complicated forms of nuclear division known as triasters, polyasters, etc., whose relation to a field of force Hartog in part explained. It is obvious that in our corals, these curving septa are all orthogonal to the non-existent hexagonal boundaries. And as the phenomenon is due to the imperfect development or non-existence of a thecal wall, it is not surprising that we find identical configurations among various corals or families of corals, not otherwise related to one another. We find the same or very similar patterns displayed, for instance, in Synhelia oculinidae, in Philipsastrea rugosa, in Tamstrea fungida, and in many more. A beautiful hexagonal pattern is seen in the male and female cones of Zamia, where the scales which bear the pollen sacs or the ovules are crowded together, and are so formed and circumstanced that they cannot protrude and overlap. They become compressed accordingly into regular hexagons, smaller and more regular in the male cone than in the female, in which latter the cone as a whole has tended to grow more in breadth than in length, and the hexagons are somewhat broader than they are long. In a cob of maize, the hexagonal form of the grains, such as should result from close packing and mutual compression, is exhibited faintly if at all. For growth and elongation of the spike itself has relieved, or helped to relieve, the mutual pressure of the grains. Figure 195. Female cone of Zamia. The pine cone shews a simple but unusual mode of close packing. The spiral arrangement causes each scale to lie to right and to left on two principal spirals. It has close neighbors on four sides, and mutual compression leads to a square or rhomboidal instead of an hexagonal configuration. On the other hand, the scales of the large cone overlap. Therefore, they are not subject to compression, but grow more freely into leaf-like curves.
The story of the hexagon leads us far afield and in many directions, but it begins with something simpler even than the hexagon. We have seen that in a soapy froth, 3 films and 3 only meet in an edge, a phenomenon capable of explanation by the law of area minima ... But the conjunction, 3 by 3, of almost any assemblage of partitions, of cracks, in drying mud, of varnish on an old picture, of the various cellular systems we have described, is a general tendency to be explained more simply still. It would be a complex pattern indeed, and highly improbable were all the cracks for instance to meet one another 6 by 6. 4 by 4 would be less so, but still too much. And 3 by 3 is nature's way. Simply because it is the simplest and the least. When the partitions meet 3 by 3, the angles by which they do so may vary indefinitely, but their average will be 120 degrees. And if all be on the O page 532 average angles of 120 degrees, the polygonal areas must, on the average, be hexagonal. This, then, is the simple geometrical explanation, apart from any physical one, of the widespread appearance of the pattern of hexagons. If the law of minimal areas holds good in a cellular structure, as in a froth of soap bubbles or in a vegetable parenchyma, then not merely on the average, but actually at every node, 3 partition walls, in plane projection, meet together. Under perfect symmetry, they do so at co-equal angles of 120 degrees, and the assemblage consists in plane projection of co-equal hexagons. But the angles may vary, the cells be unequal, and the hexagons interspersed with other polygonal figures. Nevertheless, so long as 3 partition walls and only 3 meet together, the cells are ipso facto on the average hexagonal. Figure 196. Cracks in drying mud. A thread encircles and marks a polar furrow. From R.H. Wodehouse, we may count the cells if we please. A section of Cycus Pitiol gave the following numbers. Number of sides, 3, 4, 5, 6, 7, 8, 9. Instances, 0, 8, 97, 296, 9. The fine emulsion of an alpha plate shews a beautiful polygonal pattern which obeys the law of the triple node, and a patch of a key page 533 of hexagonal symmetry. 1,000 cells in such a plate has been found, like the Cycus Pitiol, to average out at 6 sides each precisely. The cracking of a fine varnish may illustrate, as in figure 197, the same phenomenon. A little water in the varnish tends to accumulate between the cells, interferes with their close packing, and complicates the arrangement of their partitions. The horny plates which form the carapace of a tortoise, different as the case may seem, still obey the 2 guiding principles. 1, that the polygonal boundaries meet in 3-way nodes, and 2, that the 3 angles tend towards equality, always provided that no alien influences interfere. These principles are of the widest application. The carapace of a eurypterid, the dermal armor of an old red sandstone fish like Hugh Miller's Asterolepis exhibit them at a glance. Figure 197. Cellular patterns in varnish. A. Dissolved in dry acetone. B. Containing a little water. The carapace of our tortoise is formed of a bony framework of ribs and vertebrae, overlaid by superficial plates of horn or tortoiseshell. It is these latter with which we are about to deal. They are arranged in 3 rows down the back, and a marginal row of smaller plates surrounds the others. There are normally 24 plates in the marginal series, and 5 large ones in the median longitudinal row. With these few facts and our general principles, pH 534, 518, the forms of tissues etch. In hand, how far can we go towards depicting the carapace? The 5 plates of the median row must alternate with their lateral neighbors, and 4 plates in each lateral row will accordingly be the simplest case or most probably number. If at each 3-way junction between median and lateral plates, the angles tend to equality, it follows that the median plates become converted into more or less regular, or at least symmetrical hexagons. As to the 24 marginal plates, let us put 1 in front and 1 behind, leaving 11 for each side. And let us see to it carefully. Fig. 198. Asterolepis, an old red sandstone fish, after Traquair. Fig. 199. Horny carapace of a tortoise. Diagrammatic. That the sutures between these do not coincide, but alternate with those of the lateral row.
Here we begin to meet with conditions of restraint analogous to those of the surface layer of a froth. For the long marginal cells must remain marginal, and their sides must continue to run more or less parallel, or more or less perpendicular, to the edge of the shell. Ye only in the immediate the Old World tortoises have 25 marginal plates. Those of the New World lack the anterior median or nuptial plate. This difference is a biological accident. It has neither mathematical interest nor functional significance. It exemplifies the aphorism that whatsoever is possible nature. In the neighborhood of each corner will the sides tend to curve in, so forming a notch, whose curved sides have tangents approximately 120 degrees apart. Again, just as in our projection of the surface of a froth, page 494. Already these considerations lead us to a fair sketch of, or a first approximation to, the carapace of a tortoise, but we may go on a little further. The horny plates and the bony carapace below must grow at such a rate as to keep pace, more or less exactly with one another, but it does not follow that they will keep time precisely. If the horny plates grow ever so little faster than the bones below, they will fail to fit, will overcrowd one another, and will be forced to bulge or wrinkle. Both of these things they often and even characteristically do. The wrinkles appear in orderly parallel folds, pointing to alternate periods or spurts of faster and slower growth. And the characteristic patterns which ensue are the visible expression of these differential growth rates. In all this, we assume that the plates are lying in one and the same plane or even surface, abutting against one another as they grow, and so crowding and squeezing on another into the form of straight-edge polygons. The result will be very different if they overlap. After the manner of slates on a roof, the difference is what we have seen to exist between the cones of Pinus and of Larix. The overlapping edges will be free to grow into natural rounded curves. Each plate, uncrowded and unconstrained, will stay smooth and unwrinkled. The number and order of the plates will be the same as before, but the shell will be no longer that of a tortoise, but of the turtle from which tortoise shell is obtained. A snow crystal is a very beautiful example of hexagonal symmetry. It belongs to another order of things to those we have been speaking of. For in substance, it is a solid, and in form it is a crystal, and its own intrinsic molecular forces build it up in its own way. But, as we have mentioned once before, it is an exquisite illustration of nature's way of producing infinite variety from the permutations and combinations of a single type. The snowflake is a crystal formed by sublimation, that is to say, by precipitation from a vapor without passing through a liquid phase. It begins as a tiny hexagon, the making of which tends to use up the vapor nearby. The angles of the hexagon jut out, so to speak, into regions of greater or less depleted vapor pressure, and at these corners, B page 536, further crystallization will next set in. The hexagon will tend to grow out into a six-rayed star, and later and more slowly the material for further crystallization will make its way between the rays and begin to build side growths on them. The basaltic column hexagonal patterns are by no means confined to the organic world. The basalt of Staffa and the Giant's Causeway shews a wonderful array of prismatic columns of irregular size and form, but mostly hexagonal. So also does the frozen soil of Spitzbergen. Starch sets on cooling into analogous prisms, but in a ruder fashion as on a smaller scale. And all these are due to simple forces in a simple field, namely to tension or shrinkage. In a horizontal mass or layer, imagine a sheet or sill of intrusive basalt thrust in as a molten mass between older rocks. It is gradually chilled by the cold air above or by the rocks on either side, and its inner mass, cooling slower than the outer layer, contracts slowly. Nothing hinders its vertical contraction, rather is this helped by its own weight and by the load above. But no further lateral contraction can take place without splitting the mass, once the basalt sets hard. Can page 537 of the Giant's Causeway. Contraction, however, does take place irresistibly, and it may be that long cracks appear, the strain being so far relieved. The next cracks will tend to take place at right angles to the first. But more commonly, rupture is delayed until considerable strain energy has been stored up. Once started, it proceeds explosively from a number of centers and shatters the whole mass into prismatic fragments. However quickly and explosively the cracks succeed one another, each relieves an existing tension
and the next crack will give relief in a different direction to the first. When one crack meets another, it will seldom cross it, for the strain which led to the former fracture does not extend into the new field. In short, the cracks will be found to meet one another 3 by 3, and therefore at angles on the average of 120 degrees, and the columns will be on the average hexagonal. For the making of a prismatic structure, all that is required is more or less uniform tensile strain in the 2 dimensions of a horizontal plane. Uniform tension in 3 dimensions would have given rise to a cellular structure, of which the hexagonal causeway is the 2-dimensional analog. The columnar structure is accompanied by sundry secondary phenomena. The vertical columns tend to break across on further contraction and exhibit rounded or basin-shaped ends, fitting together in a shallow ball and socket. This beautiful configuration has only lately been explained. When cooling has caused the mass to split into vertical columns, air, or it may be water, enters the rifts, and further cools or quenches the now solid but still glowing basalt. Each column tends to be chilled all round while still hot within, but the hot unshrunken mass within checks or hinders the contraction of the cooler outer layers. Thus unequal cooling causes vertical as well as horizontal tensions, and just as these last are relieved by the existing cracks, so new rifts appear crosswise to the column and relieve the vertical tensions. If the cooling come downward from above, then, at any given level, the column will always be cooler above it than below. The U page 530 and 38, the part above will shrink the more. And this will set up a horizontal shear in the interior of the column, in addition to the existing vertical tension. The principal stress, compounded of shear and tension, will be neither vertical nor horizontal, but inclined obliquely between the two. Now, in a brittle substance such as glass or basalt, an advancing fracture tends to advance at right angles to the principal tension. Where the surface of the column meets the cool air, the tension is parallel to the face, and the fissure enters at right angles to the face, that is to say, horizontally. It is for this reason that the ball and socket joint is found to have a square lip. Once inside the boundary, however, the advancing rift finds itself in a region where the principal stress is inclined, slightly, to the vertical. The crack consequently bends down. The downward tilt increases for a short distance and then approaches the horizontal again. And the opposing surfaces of ball and socket are thus defined. The crack often fails to complete its journey and leaves a core of rock unbroken in the middle of the bowl. Figure 201. 1. Diagram of the vertical and shearing stresses in a shrinking column of basalt TOO. The same in the neighborhood of the point P3, S prime resultant stress, and TT prime direction of rupture, after FW Creston. The curved sides of the basin, its square lip, its flattened center, often incomplete, are thus all explained, and whether it be convex or concave, dome or basin, merely depends on whether the cooling or quenching came from above or from below. The basin or bowl will always be a shallow one, for if at a point P within the column, the vertical tension be F, and the horizontal shear stress be F sub S, then the direction of the principal planes will be 2 phi equals tan inverse of negative 2F subs over F. So that since F and F subs are both positive, phi 1 lies between 45 degrees and 90 degrees, while phi 2 lies between 135 degrees and 90 degrees. G page 539 of rifts and crackles, and 180 degrees. Hence the rift dipping down at the angle TT will never dip at a greater angle than 45 degrees, and generally much less. Now, a spherical ball whose lip is at 45 degrees to the horizontal has a depth of the square root of 2 minus 1, all over 2, times its lip diameter, or approximately 1/5. And 1/5 of the diameter of the column is approximately the depth of the deepest bowl. The hexagonal pattern and the 3-way corners on which it is based are characteristic, as we have already explained, of a condition of symmetry or uniformity under which a partition is as likely to arise in any one direction as in any other, and no series of partitions has precedence over the rest. We have seen, figure 202. Crackles on a porcelain bowl. From H. Fukushima, in the dragonfly's wing and in cambium tissue. How different is the result when primary partitions are first established and consolidated, to be followed by a secondary and a weaker set. The crackles on a porcelain bowl look somewhat like a cellular epithelium, But the porcelain has been under strain in more ways than one. The plastic clay was first shaped upon a wheel, and potential stress energy so acquired is stored up even in the finished ware. Again, as the ware cools and shrinks after it is drawn from the kiln blades, is apt to cool quicker and shrink more than the paste below. And tension energy is stored up till the glaze ruptures and the cracks appear. Various rates of cooling and of contraction, the nature of paste and glaze, the shape of the ware, and even the way in which the potter worked the clay may all influence the pattern of the crackle. The primary crack will be perpendicular to the page 540 main tension. Secondaries will tend to be more or less orthogonal to the primary cracks. Two secondaries on opposite sides of a primary will tend to be near together, though not opposite. And spiral cracks are often to be seen, the remote effect of plasticity under the potter's wheel. The net result is that certain primary cracks appear related, more or less clearly, to the circular or spiral shaping of the clay upon the wheel, and each primary crack so relieves the tension in one direction that the secondaries tend to follow in a direction at right angles to the first. While co-equal angles of 120 degrees were likely to occur in certain symmetrical cases, leading to a simultaneous pattern of hexagons, in other cases, successive partitions or cracks tend to be at right angles to one another. And Sachs' law becomes truer of the porcelain than of the plant. In this latter case, and doubtless in many more, we are dealing not with a random pattern, but with one based on systematic and predetermined lines. The apparently confused or random pattern of a kidney bean comes under the same class of configurations, inasmuch as it also is based on underlying polarity, whose center of symmetry is in the stalk or hilus. For simplicity's sake, imagine the bean round like a pea, and its surface mapped out orthogonally by two sets of boundary lines, radial and concentric. Then suppose an asymmetry of growth to be introduced so that the round pea grows into the ellipsoid of a bean. And suppose that the whole system of boundary lines is subject to the same conformal transformation, which elliptic functions might help you page 541. The color pattern of the bean will then be found following the direction of the boundary lines, and occupying areas or patches corresponding to parts of the orthogonal system. The lines are equipotential lines, or akin thereto. If we varnish an elastic bag, dry it and expand it, the varnish will tend to crack along the same orthogonal boundaries. The bee's cell, the most famous of all hexagonal conformations, and one of the most beautiful, is the bee's cell. As in the basalt or the coral, we have to deal with an assemblage of co-equal cylinders of circular section, compressed into regular hexagonal prisms. But in this case, we have two layers of such cylinders or prisms, one facing one way and one the other, and a new problem arises in connection with their inner ends. We may suppose the original cylinders to have spherical ends, which is their normal and symmetrical way of terminating. Then, for closest packing, it is obvious that the end of any one cylinder in the one layer will touch and fit in between the ends of three cylinders in the other. It is just as when we pile round shot in a heap. We begin with three, a fourth fits into its nest between the three others, and the four form a tetrad, or regular tetragonal arrangement. Just as it was obvious, then, that by mutual pressure from the sides of six adjacent cells, any one cell would be squeezed into a hexagonal prism, so is it also obvious that, by mutual pressure against the ends of three opposite neighbors, the end of each and every cell will be compressed into a trahedral pyramid. The three sides of this pyramid are set in plane projection at co-equal angles of 120 degrees to one another. But the three apical angles, as in the analogous case already described of a system of soap bubbles, are U page 542 by the geometry of the case, co-equal angles of 109 degrees in so many minutes and seconds. If we experiment, not with cylinders, but with spheres. If, for instance, we pile bread pills together and then submit the whole to a uniform pressure, as we shall presently find that Buffon did, each ball, like the seeds in a pomegranate, as Kepler said, will be in contact with 12 others, 6 in its own plane, 3 below and 3 above, and under compression it will develop 12 plane surfaces. It will repeat above and below the conditions to which the bee's cell is subject at one end only, And since the sphere is symmetrically situated towards its neighbors on all sides, it follows that the 12 plane sides to which its surface has been reduced will be all similar, equal, and similarly situated. Moreover, since we have produced this result by squeezing our original spheres close together, it is evident that the body so formed completely fills space. The regular solid which fulfills all these conditions is the rhombic dodecahedron. The bee's cell is this figure incompletely formed. It represents, so to speak, one half of that figure, with its apex and the 6 adjacent corners proper to the rhombic dodecahedron, but 6 sides continued as a hexagonal prism to an open or unfinished end. The bee's comb is vertical and the cells nearly horizontal, but sloping slightly downwards from mouth to floor. In each prismatic cell, 2 sides stand vertically, and 2 corners lie above and below. Thus, for every honeycomb or section of honey, there is one and only one right way up, and the work of the hive is so far controlled by gravity. Wasps build the other way, with the cells upright and the combs horizontal. In a hornet's nest, or in that of Polices, the cells stand upright like the wasps, but their mouths look downwards in the hornet's nest and upwards in the wasps. What Jeremy Taylor called the discipline of bees and the rare fabric of honeycombs must have attracted the attention and excited the admiration of mathematicians from time immemorial. Ma maison est construite, says the bee in the Arabian Nights, cell on page 543 of the bee's cell. Ausonia speaks of the geometrica forma favorum, and Pliny tells of men who gave a lifetime to its study. Pappus the Alexandrine has left us an account of its hexagonal plan, and drew from it the conclusion that the bees were endowed with a certain geometrical forethought. There being, then, 3 figures which of themselves can fill up the space around a point, viz. the triangle, the square, and the hexagon, the bees have wisely selected for their structure that which contains most angles, suspecting indeed that it could hold more honey than either of the other 2. Figure 204. Portion of a honeycomb. After Willem, Erasmus Bartholin was apparently the first to suggest that the hypothesis of economy was not warranted, and that the hexagonal cell was no more than the necessary result of equal pressures. Each bee striving to make its own little circle as large as possible. The investigation of the ends of the cell was a more difficult matter than that of its sides. It came later. In general terms, the arrangement was doubtless often studied and described, as for page 544, the forms of tissues, instance in the Garden of Cyrus, and the combs themselves so regularly contrived that their mutual intersections make 3 lozenges at the bottom of every cell, which severally regarded make 3 rows of neat rhomboidal figures connected at the angles, and so continue 3 several chains throughout the whole comb, or as Réaumur put it a little later on, 3 cellules accolées, listen en vide pyramidal. Précisément semblable à celui de la base d'une autre cellule tournée en sens contraire. Kepler had deduced from the space-filling symmetry of the honeycomb that its angles must be those of the rhombic dodecahedron. And Swammerdam also recognized the same geometrical figure in the base of the cell. But Kepler's discovery passed unnoticed, and Maraldi the astronomer, Cassini's nephew, has the credit of ascertaining for the first time the shape of the rhombs and of the solid angle which they bound, while watching the bees in Les Ruches Vitrées dans le Jardin de M. Cassini, tenant l'Observatoire de Paris. The angles of the rhomb, he tells us, are 110 degrees and 70 degrees. Chaque base d'alvéole est formée de 3 rhombs, presque toujours égaux et semblables, qui suivant les mesures que nous avons prises, ont les 2 angles obtus chacun de 110 degrés, et par conséquent les 2 aigus, chacun de 70 degrés. Further on page 312, he observes that on the magnitude of the angles of the 3 rhombs at the base of the cell depends that of the basal angles of the 6 trapezia which form its sides. And it occurs to him to ask, what must these angles be? If those of the floor and those of the sides be equal one to another, the solution of this problem is that les angles aigus de rhombs étant de 70 degrés, 32 minutes, et les obtus de 109 degrés 28 minutes, sous les trapèzes qui leur sont contigus doivent être aussi de la même grandeur,
And lastly, il résulte de cette grandeur d'angle non seulement une plus grande facilité et simplicité, à cause que par cette manière les abeilles n'emploient que deux orthèses d'angle, mais il en résulte encore une plus belle symétrie dans la disposition et dans la figure. Page 545 of the bee's cell. In short, Maraldi takes the two principles of simplicity and mathematical beauty as his sure and sufficient guides. The next step was that which had been foreshadowed long before by Pappus.
Though Euler had not yet published his famous dissertation on curves maxima and minima of proprietate gaudentes, the idea of maxima and minima was in the air as a guiding postulate and heuristic method, to be used as Maraldi had used his principle of simplicity. So it occurred to Réaumur, as apparently it had not done to Maraldi, that a minimal configuration and consequent economy of material in the waxen walls of the cell might be at the root of the matter, and that, just as the close-packed hexagons gave the minimal extent of boundary in a plane, so the figure determined by Maraldi, namely the rhombic dodecahedron, might be that which employs the minimum of surface for a given content, or which, in other words, should hold the most honey for the least wax. Convaincu que les abeilles employant le fond pyramidal qui mérite d'être préféré. J'ai soupçonné que la raison, ou une des raisons, qui les avait décidés était l'épargne de la cire contre les cellules de même capacité et à fond pyramidal. Celle qui pouvait être faite avec moins de matière ou de cire, et toi celle dont chaque rhombe avait deux angles chacun d'environ 110 degrés et deux chacun d'environ 70 degrés. He set the problem to Samuel Koenig, a young Swiss mathematician. Given an hexagonal cell terminated by three similar and equal rhombs, what is the configuration which requires the least quantity of material for its construction? Koenig confirmed Réaumur's conjecture and gave 109 degrees, 26 minutes, and 70 degrees, 34 minutes, as the angles which should fulfill the condition, and Réaumur then sent him the Mémoire de l'Académie for 1700, where Koenig was agreeably surprised to find que les rhombes que sa solution avait déterminés avaient à 2 minutes près les angles que Maraldi avait trouvés par des mesures actuelles. Un tel accord entre la solution et les mesures actuelles a assurément de quoi surprendre. Koenig asserted that the bees had solved the problem beyond the reach of page 566, the old geometry, and requiring the methods of Newton. Whereupon Fontenelle, as Secretaire Perpetuel, summed up the case in a famous judgment in which he denied intelligence to the bees, but nevertheless found them blindly using the highest mathematics by divine guidance and command. When Colin Maclaurin studied the honeycomb in Edinburgh a few years after Maraldi in Paris, he proceeded to solve the problem without using any higher geometry than was known to the ancients. And he began his account by saying, "These bases are formed from three equal rhombuses, the obtuse angles of which are found to be the doubles of an angle that often offers itself to mathematicians in questions relating to maxima and minima. It was an angle of 109 degrees, 28 minutes, 16 seconds. 16 seconds, with its supplement of 70 degrees, 31 minutes, 44 seconds. And this angle of the bee's cell determined by Maraldi, Koenig, and Maclaurin in their several ways. This angle, which has for its cosine 1/3, and is double of the angle which has for its tangent the square root of 2, is on the one hand an angle of the rhombic dodecahedron, and on the other is that very angle of simple tetrahedral symmetry which the soap films within the tetrahedral cage spontaneously assume, and whose frequent appearance and wide importance we have already touched upon. That the true theoretical angles were 109 degrees, 28 minutes, and 70 degrees, 32 minutes, precisely corresponding with the actual measurement of the bee's cell, and that the bees had been proved to be right and the mathematicians wrong, was long believed by many." Lord Brougham, page 547, helped notably to spread these and other errors, and his writings on the bee's cell contain, according to Glaisher, striking examples of bad reasoning, as are often to be met with in writings relating to mathematical subjects. The fact is that were the angles and facets of the honeycomb as sharp and smooth, and as constant and uniform
As those of a quartz crystal, it would still be a delicate matter to measure the angles within a minute or two of arc, and a technique unknown in Maraldi's day would be required to do it. The minute hand of a clock, if it moved continuously, moves through 1 degree of arc in 10 seconds of time, and through an angle of 2 minutes in 1/3 of a second. And this last is the angle which Maraldi is supposed to have measured. It was 80 years after Maraldi had told Railmore what the angle was, that Boscovich pointed out for the first time that to ascertain the angle to the nearest minute by directed measurement of the waxen cell was utterly impossible. Yet Railmore had certainly believed, and apparently had persuaded Koenig, that Maraldi's determinations, first and last, were the result of measurement. And Fontenelle, the historian of the Academy, epitomizing Koenig's paper, speaks of les mesures actuelles de Maraldi, of the bees being an error to the trifling extent of 2 minutes, and of the grand merveille of their so nearly solving a problem belonging to the higher geometry. Boscovich, in a long-forgotten note rediscovered by Glaisher, puts the case in a nutshell: mirum sen Maraldus, ex observation angulum estimasse intra minuta, quad in tam exigua mol fury utique non poterat. Is out satis pata ex ipsa jus determination. Affirmatse invenis angulos circiter 110 degrees at 70 degrees. Nec minuta eruit ex observation, sed ex equalitate angulorum pertinentium ad orbos, ed ad trapetia, ad quam habendam geometria ipsa, docuit requiri illa minuta. Indeed, he goes on to say the wonder is that the angles could be measured even within a few degrees, variable and irregular as they are seen to be, and as even Railmore knew. Page 548d. The old misunderstanding was at last explained and corrected by Leslie Ellis, and better still by Glaisher in a little-known but very beautiful paper. For these two mathematicians showed that, though Maraldi's account of his measurements led to misunderstanding, yet he had really done well and scientifically when he eked out a rough observation by finer theory, and deemed himself entitled thereby to discuss the cell and its angles in the same precise terms that he would use as a mathematician in speaking of its geometrical prototype. Many diverse proofs have been given of the minimal character of the bee's cell, some few, like Maclaurin's, purely geometrical, others arrived at by help of the calculus. The following seems as simple as any. A BCDEF is a right prism upon a regular hexagonal base. The corners B, D, F are cut off by planes through the lines a C, C, E, A, meeting in a point V on the axis the VN of the prism, and intersecting B, B, D, F, F in X. The volume of the figure thus formed is the same as that of the original prism with its hexagonal ends. For, if the axis cut the hexagon of BCDEF in N, the volumes a CVN, a CBX are equal. It is required to find the inclination to the axis of the faces forming the figure 205G page 549 trihedral angle at V, such that the surface of the whole figure may be a minimum. Let the angle NVX, which is the inclination of the plane of the rhombus to the axis of the prism, equals theta. The side of the hexagon as a B equals S. Then a C equals 2S cosine 30 degrees equals S times the square root of 3. And from inspection of the triangle LXBV, Vx equals over C9 theta. Therefore, the area of the rhombus VOAXC equals S squared times the square root of 3 over 2 C9 theta. And the area of Bx equals S over 2 times the quantity 2h minus 1/2 of the x cosine theta equals over 2 times the quantity 2h minus 1/2 as cotangent theta. Therefore, d of area over d theta equals 3s squared over 2 times the quantity 1 over c9 squared theta minus the square root of 3 cosine theta over c9 squared theta. But this expression vanishes, or d of area over d theta equals 0 when cosine theta equals 1 over the square root of 3. That is to say, when theta equals 54 degrees, 44 minutes, 8 seconds, equals 1/2 of 109 degrees, 28 minutes, 16 seconds. Such then are the conditions under which the total area of the figure has its minimal value. The following is in substance Maclaurin's elementary, but somewhat lengthy proof
of the minimal properties of the B cell, using no higher geometry than was known to the ancients. Let a BCD represent one half of a right prism, to which one of the three rhombs, a ECE, is fitted. Let O be the center of the hexagon, of which a BC are adjacent sides. Join a C and OB intersecting in P then, because a OC equals a BC, and B equals OE. P 550I, the solid AECB, equals a ECO, whence it appears that the solid content of the whole cell will be the same, wherever the point be taken in BB, and will in fact be identical with the content of the hexagonal prism. We have then to inquire where E is to be taken in BB, in order that the combined surfaces of the rhomb and of the two trapezia may be a minimum. Because EE is perpendicular to a C and P, the area of the rhombus equals PE multiplied by a C, and the area of the two trapezia equals the quantity AA plus EB multiplied by BC. The total area in question, then, is PE multiplied by a C plus 2BC multiplied by BB minus BC multiplied by BE. But BC multiplied by BB is constant. So the question remains, when is PE multiplied by a C minus BC multiplied by BE at minimum? Let a point be so taken in BB, at BL is to PL as BC is to a C. From the center P in the plane, PBE describe the circular arc ER, meeting PL in R, and on PL let fall the perpendiculars ESBT figure 206. The triangles VSLBT LPB are all similar. Therefore, LS is to LE as LT is to LB as LP. And by hypothesis, as BC is to a C, hence LT minus LS is to LB minus LE, as BC is to a C. Therefore, ST multiplied by a C equals BE multiplied by BC. And consequently, PE multiplied by a C minus BE multiplied by BC equals PE multiplied by a C multiplied by the quantity PE minus T. But PE equals PR. Therefore, a C multiplied by the quantity PR minus S equals a C multiplied by the quantity PT plus RST, page 551. But a C and PT do not vary while RS varies with the position of E. Accordingly, a C multiplied by the quantity PT plus RS, or PE multiplied by a C minus BE multiplied by BC, is a minimum when RS vanishes, that is to say, when E coincides with L. Therefore, a LCI is the rhombus of the most advantageous form in respect to frugality, when BL is to PL as BC to a C again, since OB equals BC, and OP equals PB squared equals 4, and PC squared equals 3PB squared, and then a C equals 2PC equals 2 times the square root of 3 times PB. Therefore, BC is to a C as 2PB is to 2 square root of 3. And by hypothesis, BL is to PL as BC is to a C equals 1 to square root of 3. Or PL is to PB as square root of 3 to square root of 2. And PB is to PC as 1 to square root of 3. Therefore, PL is to PC as 1 to square root of 2. That is, angle CLP is that whose tangent is to the radius as square root of 2 is to 1, or is 1.4235 to 1.000000, and therefore is of 54 degrees, 44 minutes, 08 seconds. And consequently, the angle of the rhombus of the best form is that of 109 degrees, 28 minutes, 16 seconds. When we have thus ascertained that the characteristic angles of the rhombs are 109 degrees, 28 minutes, 16 seconds, and its supplement 70 degrees, 31 minutes, the cosine of which latter angle is 1/3, the construction of a model is of the easiest. Figure 207, construction of a model of the B cell. On a D, make a B equals BC equals CD. I let a F equals a D meet the perpendicular BENF. Then the angle BF, whose cosine equals 1/3, or whose tangent equals 2 square root of 2, equals 70 degrees, 31 minutes, 44 seconds. Complete the rhomb a DGF and repeat 3 times as indicated. Make a developed hexagonal prism with sides a BBC equals BF. Cut away angles BB prime A, BB prime C, etc. equals BF old, and attach together. Page 552. the forms of tissues, a soap bubble or soap film, assumes a minimal configuration instantaneously, however small the saving of surface area may be. But after learning that the bee's cell has undoubted minimal properties, we should like to know what saving is actually obtained by substituting a rhomboidal pyramid for a plane base in the hexagonal prism. It turns out, after all, to be a small matter. The calculation was first made by Maclaurin and by Euler, in both cases briefly but correctly. Euler stated that the whole amount used in the bee cell was to that required for a flat-top prismatic cell of equal volume as 25 plus the square root of 6, or 27.45, to 28. The saving being thus a little more than 2% of the whole quantity of wax required. Glaisher recalculated the values, taking the cell part by part, assuming with Euler that the radius of the inscribed circle of the hexagon is to the depth of the prismatic cell, when the latter has the same capacity as the real cell, as 1 1/5 to 5, then taking the side of the hexagon as unity. We have for the same depth, viz., the longest side of the trapezium in the real cell, the value 25 times the square root of 3 over 12, and then, to 3 places of decimals, area of the 3 rhombs, 9 over 4 times the square root of 2 equals 3.82. 6 triangles. 3 over 4 times the square root of 2 equals 1.061. 6 sides of the equivalent prismatic cell, 25 over 2 times the square root of 3 equals 21.651. Hexagonal base, 3 over 2 times the square root of 3 equals 2.598. The whole surface of the real cell, accordingly, equals item 1 plus item 3 minus item 2 equals 23.772. Page 553 key. And that of the flat-bottomed hexagonal prism equals 3 plus 4 equals 24.249, and 24.249 over 23.77. 2 equals 102 over 100, or a little more, so that the saving in the former case amounts to about 2%, as Euler had found it to be. Glaisher sums up the matter as follows. As the result of a tolerably careful examination of the whole question, I may be permitted to say that I agree with Euler in believing that the economy of wax has played a very subordinate part in the determination of the form of the cell. In fact, I should not be surprised if it were acknowledged hereafter that the form of the cell had been determined by other considerations, into which the saving of wax did not enter, that is to say, did not enter sensibly. Of course, I do not mean that the amount of wax required was a matter of absolute indifference to the bees. The fact of all the dihedral angles being 120 degrees is it is not unlikely the cause that determined the form of the cell. This last fact, that in such a cell every plane cuts every other plane at an angle of 120 degrees, was known both to Klugel and to Boscovich. It is no mere corollary, but the root of the matter. It is, as Glaisher indicates, the fundamental physical principle of construction, from which the apical angles of 109 degrees follow, as a geometrical corollary. And it is curious indeed to see how the obtuse angle of the rhomb and its cosine minus 1/3 drew attention all the while, but the dihedral angle of 120 degrees of the rhombohedron, and the inclination of its 3 short diagonals at 90 degrees to one another, got rare and scanty notice. Darwin had listened too closely to Brougham and the rest when he spoke of the bee's architecture as the most wonderful of known instincts, and when he declared that, beyond this stage of perfection in architecture, natural selection could not lead. For the comb of the hive bee, as far as we can see, is absolutely perfect in economizing labor and wax, the minimal properties of the cell, and all the geometrical reasoning in the case postulate cell walls of uniform tenuity and edges, which are mathematically straight. But the walls, and still more their edges, are always thickened. The edges are never accurately straight.